It has been almost exactly a year since I published my first YouTube video, and incredibly, I'm here using the exact same intro sequence, swapping out SolarWinds headlines for Log4j headlines, which just goes to show that time is a flat circle, the field of cybersecurity is a reflection of the absurdity of life, and to even begin coping in it, one must imagine Sisyphus happy. Happy New Year, everybody. It's 2022, and thanks to this new reality of life with COVID, more than ever, people around the world are taking up resolutions this year to learn something new, enter a new career field, or put off cleaning your own code by deeply examining some malware instead. In fact, since my last video, I've received several messages asking for a tutorial on the analysis of malware, along with several people also wondering if I had abandoned my channel or had straight up died. Truth be told, it took so long to make this video because, number one, I want any content I post to be of good quality, which takes a lot of time. I have 2 jobs, a wife, and kids, including a newborn son this past year. Yeah, that's him in the thumbnail. He's so handsome. Along with just everything. And so YouTube content and commenters are like number 6 on my list. But in all seriousness, I truly appreciate all of the great feedback and kind words on my first video. I really have been waiting impatiently all year to put another one out, motivated by all of you. That wait is now over. In this video, we will be diving into the world of malware analysis, or at least a small part of that world, malware configuration parsers. These are automated or semi-automated tools used to scrape essential data from malware to answer questions like, what family and version of malware is this? Where does this malware communicate back to? How does it encrypt its configuration data? Exactly how screwed am I about to be? And more. Config parsers can help us reduce the time it takes to get the most important information we need to defend ourselves against a particular family of malware. So we are going to tackle this in 3 ways. First, dynamically, using a debugging and decompilation tool called dnSpy. Then a manual but very quick way using the almighty CyberChef. And then a far more intensive but far more rewarding deep dive into writing a fully automatic configuration parser in pure Python 3, meaning we're not going to use any external libraries except for those included in Python 3. Along the way, we're going to learn a ton about this family of malware called ASyncRAT and how to analyze .NET executables in general. It will absolutely be an investment of time and energy on your part, but if you stick with me, I promise to give you a return on that investment by showing you how to build this thing from the ground up and learn a ton of cool things along the way that will help further your malware analysis skills. I'm Jeff of All Trades. Let's see if we can't master this one. Just a few important notes here before we get started. Some things you'll need to know to get the most out of this tutorial are basic programming constructs and principles, and those can come from any programming language. General concepts of program compilation, how a high-level language gets compiled down to lower-level languages and machine code. And a general knowledge of hexadecimal, binary, and decimal number systems. Now, some other concepts that are going to be nice to know and will really help you throughout the tutorial are general concepts of object-oriented programming, regular expressions, although we'll talk about all the ones we use in the tutorial here, malware analysis. I definitely recommend you read up on the basics of malware analysis and see a few examples before you get started here, although this video should help you a lot in that field. Cryptography basics, and I really do mean basics. We're going to discuss all the cryptographic functions we need in this video for our parser, but just having some knowledge ahead of time will definitely help out a lot. If you have knowledge of disassemblers and decompilers and have used them before, that will also help. And lastly, if you've had any experience with Python, especially with Python 3 and up, that will greatly assist you, although I'll try to cover all of the different constructs within Python that we use and explain the features I'm using as we go. With all of that said, thanks for watching. Check the description where I'll post updates and corrections as I find them. Leave feedback and questions for me, please, here or on my Twitter or GitHub page. And please tell me what you would like to see in future videos. I hope you enjoy this one. Hello and welcome, everybody. So glad to have you here. If you've made it this far in the video, it means you've either sat through that whole intro or you've skipped right over it. Either way, I'm not here to waste any more of your time, so we're going to get right into this analysis. And we're going to start right at the source, pun intended, of ASyncRAT. This is on GitHub under a repo called ASyncRAT C#. I will link this one in the description along with all the different links we're going to talk about throughout this video. And what we're going to do is we're just going to do a really brief overview of the features of the RAT remote access tool, or depending on who you ask, remote access Trojan. I'm sure the authors would prefer the former, but more often than not, it's used as a Trojan against unwitting victims and targets, and it's usually used to do bad things against the user's will. Regardless, we're going to start here. We're going to go over the features. I'm not going to spend a whole lot of time in analysis of the different functionality of the RAT because this video is really focused on the configuration parsing aspect of it. Basically just getting out the bare minimum we need to know where is this thing communicating to, what kind of signatures can we write that may be able to detect it, and getting the base knowledge we need out of the sample. Maybe later we can do a more full video on malware analysis and on this family or another family, but we're going to stick to the configuration parser now. So I'll spend just a little bit of time going over the functionality. We'll get to see the builder, and we'll even build our own client, which is the program that's going to be sent to your victim or your target. And that's going to be the actual sample that the configuration is going to lie in. First, I just wanted to point you to this repo because I like to recommend this RAT to enthusiasts and analysts alike who are getting into malware analysis because you can get all of the source code right here. And it has comments, it has everything you need to understand. And so typically when I have an analyst who's coming on who says they're interested in learning more about malware analysis, I'll say, hey, go download the builder for this thing. And before you look at the source code, take the builder and make exactly what we're about to do here. Make your own sample using the builder in a safe environment like a sandbox or a virtual machine or something. And then try to disassemble it and analyze it on your own. And then the nice part about this being open source is you can go right back and you can look and see through all these different files here if your analysis is correct. Or if you get, up against a wall or something and you don't understand how something works, you can go through and see exactly how it's written. So that's the first reason that I like to recommend ASyncRAT as kind of your starter malware to analyze. Second reason I'll talk about in just a bit, but let's go ahead and go to the releases here and download the zip, which will have our built builder executable. Now, I'm not actually going to click here because if you're in, fair warning to those on Windows or if you have an antivirus running, your antivirus might pick up this file because obviously this thing, like I said, is more often than not used for ill rather than good. So Windows Defender and other antiviruses have signatures for it. You might get it picked up, or even I've had Chrome or other browsers refuse to download it sometimes. So you may have to experiment with different browsers first of all. Secondly, if you're on Windows or if you're able to configure your antivirus, you might have to make an exception folder like in your downloads or something where you can download this and just tell the antivirus to say, hey, don't quarantine whatever's in this folder. I have already gone through and done that. I'm going to go ahead and open up a virtual machine that we can work in here. Technically, and I'm going to drag it over to the other window here in a second so you can see it. Here we go. Technically, we could do all this building and analysis on our host machine because we're going to be building our own kind of sample here. But I prefer to do this at a virtual machine just to keep things safe. And also I can roll it back and take snapshots and all that good stuff. So I have a Windows 7 older, as you can tell, malware sandbox machine here that I'm going to be using. So I just very quickly transferred this using a shared folder in VirtualBox to my Windows machine. If you don't know that much about virtual machines, if you're interested in setting one up, I've thought about doing a video on that. So first of all, let me know if you're interested in a whole video on setting up malware labs with virtual machines. But I will say those videos are out there. They're a dime a dozen, I think. So if you have specific questions about setting up a virtual machine and doing what I just did with the shared folders, just leave a comment and I'll get back to you on that. But when we get there and we unzip our ASyncRAT compiled folder, we're going to see a few different folders and files here. And the one we want is just this executable right here. This is our builder. So if we put ourselves in the seat of the attacker here, this is the file that we're going to get that we can watch all of our infected machines with, and we can build new malware payloads with. And the first screen you're going to see is the settings screen, which is going to say, hey, what port do you want to start on, listening on? We're just going to leave the default port 6606 7707 8808 and say start ASyncRAT. And it's here that I want to give a quick demo of the functionality. As you can see, if I right click in this window here, here's all the things that the attacker would be able to do once they got their client infected. So you can send files, you can monitor, you can look at the person's desktop, you can keylog. In fact, let's do this. Let's go ahead, if we right click here again and go to builder, we can go ahead and set a connection. By default, it's going to go back to our local host at 127.0.0.1 on any of these ports that we're going to be listening on. You can also see some of the different options that the attacker has here. There's a pastebin option to do for command and control. They can choose to install the file on the machine for persistence. You can even change, there's some anti-analysis options here. The delay before the thing is run on the victim's machine. You can change some of the metadata to make it blend in or make it seem more legit. You can even change the icon. So they've really made a lot of functionality in here, simple obfuscation. But let's go ahead and leave all the defaults. And we'll just click build here. And I'm just going to save this just so I don't mix it up with anything else. I'm just going to save it in my downloads. And it will take it just a second or two. Yes, this is not an activated machine. Thanks Windows for that. And then we're going to go to downloads and we'll see our async client.exe there. So while this program is our server, so to speak, so this is what we're watching for all of our victims, this is the file, this is the file that we would actually send to our target or try to get them to download in order to get it to ping back to us. So what I'm going to do is I'm going to open up Process Hacker first just so I can kill this process once it's started to run. But I'm going to go ahead and run it as if my machine was infected. And then you'll see it start up here. And then in my dashboard here, we'll give it a moment and looky there. We've got our first connection. And so as the attacker, I'm going to see what username my victim is using, what kind of operating system they have, what kind of ASyncRAT payload version we have, when it was installed, privileges, antivirus software, and a bunch of other metadata here. And so here, now that I have a victim, I can go in here and let's just do, it's going to be really weird, but let's just do a remote desktop, even though we're on the same machine. So it's just going to be a mirror, basically. And let's just remote desktop our own machine. And you can see I'm watching myself as both attacker and victim on my machine here. And let's do, let's do keylogger. So I'll start typing some stuff here. My VM's a little behind because I'm recording and everything too, but you can see that the keylogger is coming in. So you can see everything I'm typing. And yeah, just a bunch of scary stuff that you can do. I think there's even like a chat function in here. Yeah, so you can chat with your victim. You can blank out the screen. You can set their wallpaper. And this probably goes without saying, but please don't use this video or this walkthrough for evil. I shouldn't have to say that, but please don't try to use this payload for evil. We're doing this for education here. This is not about being bad guys. This is about beating bad guys. So let's go ahead and terminate that. And this time I'm going to actually, I didn't mean to terminate the builder there because I actually want to build a second payload. I'm going to delete this. And the second payload is the one we're actually going to use to analyze the configuration and then build our configuration parser off of. So let's go ahead. I'm just going to take this down to one port. You know what? No, let's just leave it as default, because once we build our configuration parser, we want to make sure it works with multiple ports. We'll just leave the default, except this time I'm going to use a fake website, myfakewebsite.jeffofalltrades.com. And we're going to do the plus symbol to add that, remove the 127.001, and leave all 3 ports there. Everything else we can keep the same, and we'll go ahead and build. And we'll stick this again in our downloads folder. All right. And we can close the builder from here. We shouldn't need that part again if everything's gone well. And the way we're going to check that is to start our analysis using a tool, a wonderful tool called dnSpy. I've also linked the repo for dnSpy here. It's been around for a while. And in fact, I think this repo has actually been archived. It hasn't been updated in a couple years. But it is one of the better .NET executable analyzers that I've used. There's also ILSpy and a bunch of other ones probably by now. But I've always liked dnSpy and I keep it around still. And I think some other people have actually taken on this repo and forked it and done kind of their own version of dnSpy. So it might be alive in some capacity. Maybe someone can let me know. But I still use dnSpy, even though there are other projects out there that do the same thing. And what that same thing is disassembling .NET executables. And what I mean by that is .NET executables are any executable that's made with a language that interacts with the .NET framework. This is something that gets confused a lot, is people sometimes think that .NET is a programming language, when in reality, .NET is the framework that multiple different programming languages interact with. And this brings me back to the second reason I often recommend async client as a good starter malware, is because with C#, and I've linked a little bit about this in the wiki page for C# here, unlike something like C and C++, so like in C and C++, you write your code, you compile it on a machine. When you compile C and C++ code, it gets translated to machine code for whatever machine architecture you're coding on, or compiling on, I should say. And so when you try to, as a malware analyst or reverse engineer, when you try to disassemble back C or C++, you use a tool like IDA, or you use a tool like Ghidra, and you look at assembly language, which isn't the greatest to look through. It doesn't look like the nice code that was written to actually create that executable, a high-level code. It's much harder to read. But with C# and other .NET languages, these are meant to be cross-platform. And so what they do, and forgive me to all the .NET developers and enthusiasts if I oversimplify this, you feel free to correct me, and I'll put the any corrections in the description as usual. But to put it in a very explain like I'm 5 description, what happens with C# and other languages that use the .NET framework is they get compiled to an intermediate language. I think it's actually mentioned here. If I search intermediate language, it might talk about it a little bit here. You may see it abbreviated as IL. That's actually where the IL and ILSpy, that other tool I was talking about, comes from. And this intermediate language is then whatever kind of machine you're running the final payload on, it's compiled right there as you run the .NET executable for your architecture. And so because we have this layer, this kind of middleman of this intermediate language, a tool like dnSpy, instead of bringing us back just some assembly language, it's going to bring us back a very, very close representation of what the actual code was that was written. And so if I pull up, let me go back to, I keep clicking on Chrome even though I'm in Firefox over here. We go back to this ASyncRAT repo here, and let's just go to the client program. This is the main program file. Obviously in the main source code, you actually still have comments and everything, so that's nice. But if you look in here under program, you can see, let me pull this over to this side. We'll bring up GitHub over here. Let me zoom in a little bit for both sides just so you can see, in case you're watching this on a lower resolution. I'm looking at the main function in both of these under program, and you can see that they are pretty darn close to being a one-for-one decompilation or disassembly. I guess I should say decompilation in this case, because we're not really disassembling at this point. So that's the advantage of analyzing C# and other .NET executables, is usually you can decompile them back to very high-level representation. Now, it's not always perfect. dnSpy sometimes gets stuff wrong, or sometimes might miss something, sometimes might not run right if they mess with the executable, but it's pretty darn close, and it's much better than looking at something like assembly language. So it's very nice to work with this because you're working at a much higher level. The other thing I like about dnSpy is that it has a built-in debugger. So we can actually run this and look through and put breakpoints and watch different variables here and see how values change as the program is run. We can even step through it line by line if we want to. Now, for our purposes, like I said, I'm not going to spend too much time on the different functionality. We're going to very briefly look at this main function here and kind of break down what we're seeing. And then we're going to go right into looking at the configuration and bounce over to using the debugger to actually extract values from the configuration. So let's just take a quick look at this main function here. All right, I've zoomed in a little bit here, and I'm also going to take a snapshot real quick just so we have a clean state. We'll just call it ASyncRAT. And we'll let that save real quick. Should just take a few seconds. And that way, if the machine shuts down or if we change something we don't mean to, we can roll back to this snapshot in VirtualBox. Because I'm running an unactivated Windows image here, it's going to shut down every hour. So if you see me cut or you see me restart the virtual machine, it's because it shuts down every hour or so. All right, so we're going to take a look through this main function. It's, even if you know nothing about programming, it's pretty cut and dry to follow here. So the first thing that we see is a for loop that reads in the settings.delay and in dnSpy. If you click on that, it's going to show you that in settings, in the settings file over here, that is set to 3. And then we're going to call thread.sleep 1000. Now, if you hover over sleep, you can see that that 1000 is how many milliseconds that we want to sleep for. So whatever the attacker sets this delay to, we're going to sleep for that many seconds, in this case 3. And this is a technique that is used often to either thwart malware sandboxes that are automated by making the malware wait to execute until a certain time. So maybe the sandbox tries to execute and it times out and it doesn't get to see any functionality because of this delay. Or sometimes it's there just to make sure that there's a short delay so that the user doesn't notice anything. Either way, we're going to wait for that delay. The next thing we're going to do is call initialize settings. And it looks like if this errors out in some way, if it returns an error code, we then exit. Otherwise, we're going to create a mutex. We're going to, if the settings.ante is set to true, which that is encrypted or encoded there, so we don't know what it's set to right now. If that is set to true, though, you can see it's converted to a Boolean here. We're going to run this anti-analysis function. Again, not going to get into the details here of what that entails because we're not going to do a full malware analysis here. And if the settings.install key is set to true, which again, we don't know, it's going to run the installation function. And if we're admin and BDOS is set to true, then we're going to set our process to critical or process critical.set, whatever that function is doing. I'm assuming it's setting us to a higher privileges. We're going to do that. And then prevent sleep, which we can assume means that we're not going to try to sleep after that. And then it looks like it's going to try to reach out to its command and control and initialize a connection back to the attacker, and then sleep for 5 more seconds there. So I was very deliberately vague about these different things. I'm just making assumptions here because it's been a while since I've looked at the code. And like I said, I'm not too concerned about the other functionality. What we're most interested in here is this settings.initialize settings function here, because As you might have gathered as we were going through that main function, you can see that since I clicked on there, we're now in the settings class over here. I don't know if I can zoom in this side in the belt over here, but at least I can zoom in the main window. Excuse me. As you might have assumed from all the different settings we were already reading, this is where the configuration lies in this client. And so you can see right off the bat, when we call initialize settings, we're going through, we're getting a key. We are setting up an AES 256 cipher. So that's an encryption algorithm that we're going to talk about in a lot of detail in just a little bit. And we're going to use that AES key in that cipher to decrypt all the rest of these weird looking settings that are in our settings class here. So these are all encrypted and encoded, and that's why they all look very strange and not human readable right now. At least most of them, like this one right here is in plain text. You can see that it will install in the app data folder here. But the rest of them are all encoded. And so this is the crux of our video right here, this section here, because this configuration tells us the hosts, which is the server that that the attacker is hosting, that he's going to be listening on, or she, and the ports that they're going to be listening on, as well as what version of the payload we're looking at, what the install setting is that we saw used there, the mutex we're going to create, abbreviated MTX, the certificate that's used for C2 communication, all this stuff that you're very much interested in if you're a malware analyst in order to build good detection of this stuff and figure out what other network traffic you should be looking for if you are infected. It's all right here in this encrypted configuration. And so this is where we're going to focus our time here. Now, the awesome part of dnSpy, aside from it being a really nice decompiler, is that it has a built-in debugger here. And what that means is we can set breakpoints. We can look at the program and go through it line by line and see how these things change. And it's super simple in dnSpy to do that. In fact, let's just set up a breakpoint right here at the start of initialize settings. We can right click and add breakpoint, or you can press F9 on your keyboard. And then we go up here to this green start button here and click start. It's going to ask us to make sure that we're pointed at the right assembly. Sometimes if you run dnSpy, sometimes this box may be blank. If it is blank, go through in this menu here at the ... and make sure you select the client that you built here and make sure it's pointed to the right executable. Otherwise, it won't start at all, of course. It'll just be like, I don't know exactly what I'm running. Please tell me what to run. So this is pointed at the right executable. Let's go ahead and click OK. And it's going to run here, and it should stop right as we get to this line, and we can see this arrow indicating that we are stopped right here. So the first thing we're going to do is dynamically extract the values from this configuration. And this is by far the easiest way to do it, but it requires the manual effort of going through here, setting up these breakpoints, knowing where to set them up, and actually extracting the values as they're decrypted out of the configuration, which if you're analyzing a ton of these samples, it's not very efficient to keep opening them up in a sandbox, keep looking to the configuration and doing it this way. But it is fast. If you only have a couple to analyze, you can do it this way. And it's the easiest way by far. So let's just break this down while we're here, what's going on with the key, and then how that key is being used to create this AES 256 object, and then how that is used to decrypt all these other functions here. So the way we're going to do that is, first, we can see that settings.key, which is down here, if you click on it, it's another encoded string there, is first converted from base 64. That's what this weird encoding is that you see here. If you've ever worked with any kind of base encoding, you probably recognize that schema. It's usually made of uppercase, lowercase letters, 0 through 9, and then padding is indicated by equal signs. So at the end, you might see 1 or 2 equal signs here. That usually means you're looking at either base 64 or some other base encoded string there. It's even more obvious though to us here because we can see it's calling from base 64 string, so we know this is a base 64 encoded string. So the key value is first converted from base 64, and then passed to utf8.getString, which basically means cast that to Unicode UTF-8 string. If you wanted to go in and see all these different functions being used, if you just want to go beneath the surface here, we have 3 options up here in the debugger view. We have step into, which is actually going to take me into each function as I step through the code. So if I click step into here, it's going to take me into from base64 string because that was the first function that was called. And we can step over at this point, which means skip over going beneath the surface and basically just step to the next line. And we can also step out if we need to. So let's step over to the end of from base64 string just as an example. And you can see down here, we can see all the local variables, the global variables defined down here. We can modify them. We can set watches on them if we want to keep track of their values as they change. And that's the beauty of using a debugger like dnSpy, is we can keep track of everything as it happens. Let's go ahead and step over this, and we see that the final result is going to be passed into this helper function convert.fromBase64 character pointer. Let's go ahead and step out. And we're on the same line because we've only called one of these functions. We're going to call the getString next. We could hit step in again, and we can see the result of getString. And we can see that it returned this string right here. Now it's still not, it's still gibberish because this is just a key, an encryption key that's going to be used. So it doesn't really have to make sense. It's going to be passed into the cipher object right here. And that cipher, the AES 256 cipher, is going to be used to decrypt all these other values right here. So to see the values of the ports and the hosts and everything, what we can do is step into this decrypt function right here. And we can see here's the input. So this is the ports string, and you can see it's base64 encoded. And you can see that it's first, again, converted from base64, and then sent to this .decrypt function. So we'll step into that. Well, first we're going to step into from base64 string again. Let's step out of there and step in again. And we're going to end up in this decrypt function right here. So we're going to dig into this decrypt function in detail in just a little bit. So I'm not going to go into the details yet. We just want to kind of step through here and get to the end so we can see what the result is going to be. In fact, let's set a breakpoint at return result, and let's just hit continue, and that'll continue the execution of this until that line. Excuse me. And we can see that result is a byte array right now. So it hasn't been converted to a string yet. It's just a array of bytes. So let's keep going here. And lastly, we're going to call getString, which is going to convert those bytes into a string. So let's go in here, and we're just going to step over a couple times, and we can see the result that was returned, which is, let me see if I can get this to come up. Do I have to click edit here? Oh, I guess you can't. I'm sorry. It's a return value, so you can't edit it. But if that's a little too small for you, it basically just says the ports that we saw from the builder 6606, 7707, 8808. And so our first part of the configuration, the ports, has been decrypted. And that is one way we can get those values. It's just by setting that breakpoint. Let's go ahead and we're going to set another breakpoint in, let's go to getString. And let's set a breakpoint right here instead. And that way, we can go ahead and delete this one by right-clicking and doing delete. We can continue all the way to here, hit step over, and then we can go and see what all these values are going to be. So there you can see the host string, which was myfakewebsite.jeffofalltrades.com. We can continue again. We're going to see what's this one going to be? This is the version 0.5.7b, etc., all the way through the configuration. So this is false. This is if we step out here, that is the install boolean there. And so we're seeing that boolean value being decrypted there. We're going to go through there and do that for each of these different settings here. As a malware analyst, I'm really mostly interested in the host and ports because that's going to tell me where the attacker is living, what I should look for in my network traffic if I'm infected by this so that I can see if it's actually calling out. and putting that on my block list or making signatures for detection and network signatures. But there's also a lot of other good stuff here you could put into detection signatures. Any one of these would be good to know, just so you have more information about what to look for. If you know the mutex, and let's say you're curious if you have other machines in your environment that have been infected with this, you can decrypt that mutex and go hunting for that mutex on other machines to see if they're infected. You can see if they're using a paste bin. You can see if they set up different features of this. You can see the certificate they're using for HTTPS communications. That's all great stuff, and it's all right here in this configuration, and that's why we're spending so much time analyzing this piece of this particular malware payload. So I'm going to stop debugging there. We talked through so far just how to dynamically, using dnSpy, go through the configuration and really quickly pull out those values without actually, running it in a unsafe environment. Like I wouldn't want to run this on a different host, because when you run the debugger, it's actually running the program as well. So we wouldn't run a risk that. We pulled it into our sandbox, our virtual machine. We dynamically analyzed it in our debugger here, and we pulled out those values. Again, low level of effort up front, high payoff, but not very repeatable, not very efficient if we're trying to analyze multiple of these samples. So next, what we're going to do is take a look at CyberChef and take a deeper look at this AES 256 decryption algorithm to see if we can build a recipe that we can reuse over and over again for this malware family to do the same kind of configuration analysis. All right, I am back in my Firefox browser and I'm staring at the beautiful CyberChef. This is a tool that the Government Communications Headquarters of UK released several years back now, I guess. 5-something years ago maybe now. And it's only gotten better since they open sourced it. I'm really appreciative that they open sourced it. Any InfoSec professional should have this in their toolkit. They call it the Cyber Swiss Army knife. And it is, and it also has a ton of other data manipulation value. You can go to the GitHub repo here for CyberChef. They also have a live page where you can interact with it online. You can download it and you can run it locally if you have concerns about using it online. You can run it and set it up yourself. But it is just a wonderful tool. Like I said, it has several different operations for data manipulation and InfoSec related things, malware analysis related operations, forensic stuff like that, or just coding and data manipulation in general. And we're going to use a lot of these operations to do a quick recipe, as they call it, which is just a line of different operations strung together that we can save and reuse over and over again to decrypt or parse these configurations from ASyncRAT payloads. So the first thing we're going to do is let's go back here. And before we build our recipe, we really have to understand what's going on under the hood here with this AES 256 cipher and all this decryption stuff going on here. So let's start. We already saw that we converted the key from base64, convert that to a string first, and then we send that into this AES 256 function. So if I click on that, we can see over here in my assembly explorer, we are now in a different file and class called client.algorithm. And within there, there's a, that's the namespace. Got to make sure I use my right verbiage here. Client.algorithm is the namespace. The class is AES256. And you can see this if you go back to the ASyncRAT payload, the ASyncRAT C# repo under client and algorithm, just like we saw in the Explorer there. And here's the AES256 file right here. And it looks, again, very similar to what we have in dnSpy right here. Now, we're going to break this down piece by piece, and I'm not going to try to keep it as simple as possible without getting into the depths of the very nitty-gritty details of the AES 256 implementation and algorithm. If you're really into that stuff and if you're into cryptography, I will link the AES Wikipedia page, which has all of the details your heart could desire about the algorithm. But for now, let's try to keep it as simple as possible as we walk through this. So we see here that an AES 256 object is initialized with a string called master key. And that's what we saw, is that key value from settings is decoded from base64 and then sent to this function. And if it's null, we get an error message, but if it's not null, we go through and we send that value to a function called RFC2898 derive bytes, along with a value called salt, which is hard-coded right here, and a number right here, which if we hover over the function here, we can see the declaration, which tells us that the last number of 50,000 is iterations. What the heck does all this mean? What is RFC2898? Did I just give an order to kill all the Jedi? No, it's actually a request for comments or request for change. I actually can't remember which one it is for RFC in this scenario, but it's one of those two. And if you search, let's just actually do it right here, RFC2898. Excuse me. You'll see right away, first of all, you'll see the original RFC right here. And you'll see it describes PKCS number 5, password-based cryptography specification version 2.0. If you go a little farther down in the Google results, you'll see PBKDF2, the Wikipedia page, which I've bookmarked for you here. And this is the algorithm or the function that we're being sent to right now. And I'm going to mess it up multiple times just so you know. PBKDF2 stands for password-based key derivation function 2, return of the king, director's cut, final version, _final, _ do not change.exe. It's a derivation function, which basically means that it's a way for us to pass in a passphrase and come out with a cryptographic key that's going to be used for encrypting or decrypting something. Again, I'm not going to get into all the mathematics. I know my explanations are probably poor, and there's probably some cryptography nerds that are just really disappointed in me right now, but I'm going to try to keep it very high level. If you're interested, go check out the wiki where they talk very much in depth and link to the original RFC and papers and everything that talk about the implementation. For our purposes, all we need to know is that this function is used to derive an encryption key or a decryption key. And we also send, like I said, a salt, which is used in that same function as part of deriving the key, and the number of iterations, which is, again, just another parameter that goes into this function that is used to derive the key. I'm not going to get into the details, but it just specifies how many iterations to run a certain mathematical function that generates this key. Why am I going into so much depth here with this one? It's because in CyberChef, the wonderful CyberChef, we actually have, if you search PBK, a derivation function built right into the tool for us. And if you hover over it, it'll tell you it's a password-based key derivation function. It's basically right from the Wikipedia. It tells you exactly what it is, what a salt is. A salt provides a large set of keys for any given password, and an iteration count increases the cost of producing keys from a password, making it increasingly difficult to crack that key. Again, you don't need to know the details. We just need to know what is going to be required from us in order to derive this key. And it's basically those three ingredients: a passphrase, a salt, and an iteration count. Now, you'll also see in CyberChef, there's two other ingredients, so to speak, that we need for our recipe here. And that is the hashing function and the key size. Now, if we bounce back to dnSpy, we are actually given both of those things in the AES 256 class here. First of all, right here, you can see that this .key, the key size is going to be 32 bytes. That's what that means right here. In fact, if you bounce over to the full implementation, the source code, it's actually hard-coded in as a, I'll zoom in here a little bit, constant key length is 32 bytes right there. Now we have to be careful, because even though it's 32 bytes, we need it in CyberChef in bits. And so what that means is each byte is, of course, 8 bits. And I'm going to take my calculator right here, and I'm going to multiply 32 by 8. And so our full key length for CyberChef's purposes is actually 256. Oops, except my numlock doesn't appear to be on. There we go. That's better. So we have the key size. We need to know the hashing function that is actually also given to us. If we actually click into this RFC 2898 implementation, you'll see there's actually in the declaration, it tells us exactly which hashing algorithm it's using. It's using SHA-1, so that's great. We have that piece for us. We can leave that at the default. We know that the iterations is 50,000. Now we just need the salt and the passphrase. So the salt bit is interesting. Somebody noticed that I'm going to take a little bit of a detour here just to point this out because I think it's kind of cool as a malware analyst. Somebody noticed a while ago that this AES256 file, the salt value that was used in ASyncRAT, wasn't unique. It's hard-coded right here, and you can actually find it in other malware samples such as QuasarRat. It's the exact same file, in fact, and the exact same salt. So it looks like whoever created ASyncRAT basically took this right out of Quasar, or maybe vice versa. I'm not sure exactly. Odds are this was stolen multiple times over and mutated for each malware that it's ended up being in. But this salt value is hard-coded. It's not unique. And there's no guarantee that it will stay the same even between ASyncRAT payloads. But we're going to ignore that for now. We'll come back to that later. For now, we just want to get this salt value out of our payload here so that we can put it into our CyberChef recipe. Now, when you look at this in dnSpy, unlike the source code where you can see it's nicely in hexadecimal format, it's going to be in decimal format in dnSpy. And so we have to clean this up a little bit to use for CyberChef. And we can actually use CyberChef to do that cleanup. So let's do that. I'll open up another window here. All right, we have a new tab open here. Let's go ahead and paste in our decimal salt value here. And the way we're going to convert this is just two easy operations. We're going to do from decimal. And we're going to tell it that our delimiter is going to be a comma because these are all separated by commas. You're going to see some gibberish here because this is just the raw value of those bytes. What we want to do is do a second operation called toHex. And we're going to also, let's go ahead and condense this down without any space into just a single string. So what we've done is actually, let me leave the space there just for a moment so I can show you that CyberChef has taken each of these values that are separated by commas, it's removed the comma, and it has translated them to their hexadecimal representation. And so if we pull open the ASyncRAT implementation, we can see that it shows up just like it does here, BFEB1E, etc., etc. Just like that, BFEB1E, awesome. Last thing we're going to do is just take out the space and click copy here and pull this into our recipe for deriving the key here. Now, the salt, again, is not guaranteed to be this for every single payload. So you can see how this is a little less efficient than our last option we're going to talk about, which is the fully automatic Python parser, because we're still going to have to go into the payload, do a little bit of analysis, make sure we have the salt correct, and then do this kind of translation and pull out the key value and the iterations and all that good stuff. But again, if you don't want to build a fully automatic parser, if you just need a pipeline that you can reuse over and over again, this is sufficient. So the last thing we need is our passphrase, which we saw. That is in the, go back here, settings.key value here. So let's go ahead and copy this value. We're not going to do any kind of manipulation here in dnSpy. We're going to actually do all of our manipulation in CyberChef over here. Oops, and I shouldn't, well, yes, I should actually. So you'll notice that, for example, I can put it in here and I can actually, I don't even have to translate it from base64. I can just tell it that this is in base64 format by clicking on that menu. And you should see my key value pop out right here. So how do we know we're doing this all correctly? How do we know that we got our salt correct and all this good stuff? Well, we can go back here. Let's go ahead and go to AES256 and let's set a breakpoint when this .key is initialized right here. So let's set a breakpoint right here. So this is actually calling the RFC 2898 derived bytes function, which is essentially what we're doing in CyberChef. And what we want to see here, oops, there's my first breakpoint. Let's go to the second one. What we want to see is if the result of this operation results in the same byte array as our CyberChef recipe that we saw right there. So the way we do that is we look at what derived bytes here has returned. It's a byte array. If we click on the arrow here, we can break this open and we can see C1, A4, 11, 18, etc., and hex, C1, A4, 11, etc. All the way down, we can verify that we have the same key value, which we do. The last three are F08916, F08916. So we know that this part is working well. But all we've done so far is derive the key. And to be honest, if I'm a malware analysis like the majority of them, I'm going to be lazy and I don't want to open up a bunch of different tabs for CyberChef and use one tab for deriving the key and another tab for doing all of my decryption stuff. So we're going to use a cool list of CyberChef operations here to kind of cheat and make this all one big recipe for both doing the key derivation and the decryption. The way we're going to do that is using an awesome feature called registers. So what I'm going to do here is I'm going to use a register command right here. And I'm going to go back and let's go ahead and stop our debug session here. I want to take a few of the settings, strings, the encoded and encrypted strings down here. So let's just take hosts and ports, probably the two most interesting. I'm going to put those right beneath the key in our CyberChef input box here. And what we're going to do is we're going to use a register to store these different values of input and separate them so that we can run the key derivation on our first value, but we can run decryption on the rest of the values we paste in here so we don't have to create multiple tabs or multiple recipes for doing derivation versus decryption. Let's see what that looks like in practice. So for the register operation, we just need to specify a regular expression. I did mention this at the start of the video that it is very, very essential that you have some knowledge of regular expressions to know what's going on here. So if you don't know what regular expressions are, please check out some of the links in the description on my current video or past videos that talk about those, or just Google regular expressions. And there are a ton of courses and just quick blogs out there to get you up to speed. But basically, we need to create a regular expression that is going to capture and separate our key input from our encrypted string input. The way I'm going to do that is I'm just going to add a double new line here, and I'm going to use that as kind of my delimiter for what I put in my register. So let's go ahead and deactivate this derivation operation here by just clicking this red circle with the line through it. And let's focus on the register operation here. So I want to capture, using parentheses, everything before the new line, double new line that is, and then put that in my first register. And you can see that it's just captured everything before that new line, which is just this, and then everything after as a separate line of input there. And actually, we may not even need the double new line. I think it'll just work just based on that first new line. Yes, it does. So let's just keep it there, keep it simple. This sequence right here, again, not to get too deep into regular expressions, it just means dot means any character, plus means one or more times, and then the question mark is a marker for being non-greedy, which just means read up to the first new line and then capture everything before that in this first register, R0, and then read everything after that first new line, so after that first line, and store it in R1. So now we've successfully separated our key value from the other values that are going to be our encrypted configuration settings here. And the reason we want to do that is because we want to run the derive operation on the key, but not on any of the other values. So let's go ahead and in our passphrase here, we're going to put the value of our first register, which has the passphrase, R0. And we want to make sure that, again, matches up to what we expect it to be. And we're also going to store that that derived value in a different register so we can save it for later when we actually do the decryption. So for that one, it's just going to be a simple, I don't even need the question mark. Actually, I can just take everything there, I think. Why am I getting a syntax error? Okay. Sometimes you'll get some random errors in CyberChef, by the way. You may just have to click bake again if it doesn't seem to make sense, and a lot of times that'll fix the issue. If it stays there, you probably need to check something in your recipe or in your operations. But looks like that one was just kind of a hiccup because CyberChef is auto baking all the time. So sometimes it has a few hiccups there. So now we've taken our derived key value and we've put that into our a third register, which is R2 since we started at 0. And we're just going to save that away for now. So now we want to run the rest of the operations on our encrypted strings here, because what we're going to do in CyberChef is rebuild this AES decrypt function that we see right here. So before we get into the details of that, let's go ahead and set us up to work separately with each of these inputs. Each line is a new input. And the way we're going to do that is first we have to clear out any output we have so far. So we're just going to take .star, which means 0 or more characters, and replace it with nothing. That's going to clear out our output. The reason we're doing that is because we want to replace it with the value of our saved register up here, which is everything beneath the key right there. Sorry about that. I had to cut away for a second because I forgot that you need to make sure that you have multi-line matching checked here for your register as well as dot matches all. And then for your find and replace, you want to have all these unchecked. That will replace it so that you have everything in our register 1, which is just these 2 lines, back into our output box, which is going to become our input for the next operation. So the reason we went through this find and replace shenanigans here is because we want to clear out that box of everything from the key derivation function, store that away for later, and then replace it with these 2 lines so we can start doing operations on those. So before we go any further, now that we have that all set up, let's go back to our virtual machine and take a deeper look at this AES 256, not the encrypt function, but the decrypt function here. And I'm just going to set a breakpoint at the start here and click start. And we're going to wait till we get brought up to that function. All right, sorry about that. Of course, as soon as I click start, the VM decides to shut down right then. Due to that non-activation of Windows, it shuts down every hour, like I said, and that just happened to be the time that I was clicking start, so that was fun. But now we're back, we have our breakpoint set, and again, just as a reminder, in the settings, after we derive our key, we pass in each of these settings values to the decrypt function within the AES 256 file. And this outer decrypt function takes a string as input and then converts that from base64, which returns a byte array, and that gets sent to a inner decrypt function. That's where we set our breakpoint right here. And this is also going to return a byte array, which is then converted to a string right here. First thing we do is check that our input is not null. And remember, this is the now decoded base64 string. So this is the decoded bytes from there. As long as it's not null, we're going to pass that into a memory stream. And then you're going to see a bunch of metadata set up here for the AES cipher. Now, again, I'm going to talk a little bit more in detail about the cipher mode, CBC, cipher blockchaining, and the padding mode, PKCS7 here when we get to our Python parser, just on the surface to explain a little bit about those. But I'm not going to get too deep in the weeds about the actual AES 256 algorithm or its implementation. Just know that this is setting up a very specific implementation of the AES 256 decryption algorithm. And all this metadata is required so that the program knows exactly how to decrypt the data that we're working with. So we need to pass in the key size, the block size. If you don't know what that is, again, go look up CBC or check out the link that I posted in the description for AES, and I'll explain what CBC is and why that block size matters, the padding and everything. But you'll notice again, this is in now back to bits. Instead of bytes, this is a 256-bit key, which we already knew, that's 32 bytes. Block size is 128 bits or 16 bytes. CBC mode, PKCS7 padding, and then we're passing in the key that we derived before. Again, you don't need to worry about what's kind of going on under the hood. This is just setting up our cipher here. Now, the first thing we're going to do with our memory stream, which contains our input string, is we're going to create this hmac SHA-256 object, and we're going to run this compute hash function here. What the heck does that mean? HMAC, or keyed hash message authentication code, or hash-based key message authentication code, however you want to say it, is a type of message authentication code, just as it says in the name. It's basically just a hash function, and it's used to verify that the data that we're looking at has not been manipulated. So before we get too deep into that, let's take a look first at this implementation, and you can do this just by Googling the compute hash name or going to docs.microsoft.com and going there and searching. And you can see in the docs that it computes the hash value for a specified region of the specified byte array. And so we pass in a buffer that contains the data that we want to hash. It might also have other data in it. And so we pass in an offset as well to tell it exactly where in the buffer that we want to begin hashing data. And we give it a count of how many bytes we want to hash in that buffer. So let's take a look at the implementation in ASyncRAT here. So we pass in memory stream.toArray. So we're taking our input, that base64 decoded string. We're converting that back to an array to pass into compute hash because it expects an array. And then we say the offset is 32. So we're skipping the first 32 bytes of the data, and we're going to hash up to memory stream to array.length. So that's the length of our input string minus 32. So basically what that's saying is we're going to start at the 32nd byte in this buffer, this input string, and we're going to read all the way to the end of that string, and we're going to hash that. Now, why are we starting at the 32nd byte? Why are we skipping over 32 bytes to do that hashing? Well, let's keep going here and we'll see. So the result from compute hash is stored in a variable byte array called A, and then we initialize a new byte array of size 32, so 32 bytes. We then take our memory stream, which again, remember, this contains our input, which is the base64 decoded string from settings, and we call that read function, which takes in a buffer, an offset, and a count, just like the hash function, except what this read function is going to do is read in from this memory stream into this byte array, which is simply called array here. We're going to start at offset 0, so the very start of the stream, and we're going to read the size of array.length, which is just 32 bytes. So we're going to read the first 32 bytes of our input string into array. So let's break this out a little more. I got my input byte array right here. This is in hex, so this is actually 64 bytes in length. So we're reading the first 32 bytes, which is 0 through 31 here, into array. And we can confirm that by, let's go ahead and execute down to that line, and let's take a look at the contents of array. And oops, I need to go one more actually. And we can see that it is df through 3f, which is the exact same as the first 32 bytes of our input string here. And then remember, we computed a hash over everything after those first 32 bytes. So what the heck is going on here? Let's break it down. What is happening in this implementation is that we received a 64 byte input. We read the first 32 bytes into this array here, and now we're checking that against the HMAC hash that we computed up here. So what we're doing is we're seeing that the first 32 bytes of these encoded strings are actually a hash. And what we're doing is as the program is running in real time, we're computing that hash again over all the data after the hard-coded hash, and then comparing these two hashes to make sure they match. Why are we doing this? It's to make sure that no one has tried to change the decrypted or the data about to be decrypted before we actually try to decrypt it. This is just a way to ensure that the data has not been manipulated by prefixing a hash to the
encrypted data, and then calculating that hash at runtime right before it's decrypted to make sure that no one's trying to manipulate it and that it is the data we expect to be decrypting. So that's all that's going on. So what we know now is that the first 32 bytes of every single one of these encrypted strings is going to be an HMAC hash. So we don't need to worry about those. For our purposes of building our configuration parser, we don't need to worry about hashing it. We're just going to assume that no one has tried to manipulate the data during runtime, because the only person who would have done that would have been us. But I wanted to walk through that in detail so you understood that those first 32 bytes are not part of the actual encrypted data. They are just a hash that's being used to confirm the integrity of the data. So that's what all that piece is about. Now we move on. We define another array called array2, and it's going to be 16 bytes in length. Here is a very important distinction. So we called read up here, and we're calling read again. The difference between accessing like a byte array versus a memory stream object like this is when we called read up here on this memory stream, we read in those first 32 bytes, we changed where the cursor, so to speak, in this stream is. So when we call read again, we're actually starting from the same spot from where we left off reading the last time. So we are now 32 bytes into our input string right after the hash, and we're now reading the next 16 bytes. We are not starting from the beginning of the memory stream. We are starting from 32 bytes into the memory stream. I want to make that clear. So we're reading the next 16 bytes. So basically, if I break open input, we're looking at 32 through 47 in that array. And we can confirm that after we do this line. We can look at the contents of array 2 and confirm E3 through 2D, which is what we saw in, I forgot to actually look at the values right here, E3 through 2D right there. So we're now looking at the next 16 bytes, and then we pass that in, and we use that value to initialize this AES crypto service provider.iv. What the heck is that? The IV, or initialization vector, is another piece of, I'm going to use the term metadata. I'm sure cryptography experts are going to maybe not like the term metadata for that, but it's basically another parameter that we're passing in that we need to know for our AES decryption. In fact, let's bounce back and catch up with CyberChef here, because we left off, we had our encrypted and encoded strings here ready to go. What I'm going to do here is I'm going to find an operation here called fork. And if you read the description for fork, what this is going to do is split all of our input data up by a delimiter and run every single operation after the fork on each individual delimited data that we set. So for example, I think it's easier to explain if I just put this down here. We're going to set our delimiter to new line, which means each line here, and it looks like there's 3, there's actually only 2. This is just wrapping over to the next line. So this line and this line are our 2 lines here. Forking them means that each of the subsequent operations after fork, so if I just do, let's just do a find and replace maybe. And let's do, we'll replace each, we'll just say find anything and replace it with foo. So what the fork is going to do is, oops, I think I need to take off, I think it's global match that's causing that. Yeah, global match. It's called, you'll see 2 foos here because it called it twice, once for each line that was in our input here. So forking means that each subsequent operation is going to be run on each line, not on the input as a whole, if that makes sense. What that means for us is when we get here, we want to first base 64 decode our values. I could have just used this for example. It's probably self-explanatory. That's going to give us a bunch of gibberish, but basically it's base 64 decoding each of these strings. If we turn those to hex here, we'll see the same values that we saw in our dnSpy debugger. I'm not going to go back and look at them for certain, but you can see they're here. So this is our first decoded string, and this is our second one. But what we really want, we take out 2 hex. We do want to keep from base 64 there though, because we do want to decode each of them. We then going to go to type in AES Decrypt, and sure enough, CyberChef has an operation for that. And you'll see here that this also requires some ingredients before we can decrypt these strings. The first is our key, which we captured all the way back up here. When we did our key derivation, we stored the value of that derivation in R2. So let's replace that with the value of R2. And that is going to be in hex, so we'll leave that right there. Again, it's telling me invalid key length, but that's because it might have a error there. You don't have an IV left. So this is the initialization vector. This is the guy we're getting from array 2 here. So that's going to be, again, everything from the 32nd byte of our input data through the 47th byte, or basically the 16 bytes after the HMAC hash. So with that in mind, let's go ahead and do a find replace, or actually not a find replace. Let's do a register here before we get to the AES decrypt, because we need to capture from our input array here that IV value. And actually we do want to have a 2 hex. What we're going to do is convert from base 64. We're going to convert that to hex. Let's go ahead and remove the spacing just so we can have nice clean strings here. And we're going to skip, again, we're going to skip the first 32 bytes of our input string because we know that's the HMAC hash. However, we have to be careful again because each byte of these inputs is represented by 2 characters in hex. So 6B is 1 byte, 7C is the next byte, 9B is the next byte. Because we want to take out the first 32 bytes and ignore them, we then need to double it since each byte has 2 characters. And so we need to do .64. These curly braces in my regular expression here just mean that take the first 64 characters right there. And we don't need to capture those. We don't need to put those in a register. So I'm not going to put those in parentheses because we don't need to save them. Because like I said, we're just going to ignore the hash value there. But we do need to capture our initialization vector, which was the next 16 bytes after that HMAC hash. And so I'm going to type in parentheses so that we can capture it in a register. And again, we need to double that value of 16 bytes to 32 so we can capture the right number of characters. And if I do that, I got to click bake again because it's thinking real hard about this. You can see the 16 bytes are captured in R3. And we can then stick that into our decryption function right here. Now the last part we need, we're still getting an error because we haven't captured or separated out our actual encrypted data yet. Where does that come into the picture? Well, right after we read those next 16 bytes to get our initialization vector, we then see there's a CryptoStream object created from MemoryStream. And you don't need to know too much about the implementation details between MemoryStream and CryptoStream. Just know that this stream is going to contain the rest of our encrypted data, basically. And so we now make another new array 3. That's going to read from memorystream.length minus 16 bytes plus 1. You may be wondering, what is that calculation? I will tell you that it is going to read everything after those next 16 bytes. So basically, we read in the hash, we read in the 32 byte hash, we read in the 16 byte initialization vector, and everything else in our input is going to be the encrypted data that we actually want to decrypt. Now, you might be wondering, what is this size of this array? How is this calculated? We're taking the length of our input string, we're subtracting 16, which is for the initialization vector, and we're adding 1. I will tell you that I don't fully understand the calculation they're making here. It works functionally because you end up reading the same, you'll never read above the buffer. You won't have an overflow or anything. But I asked this question of the cryptography subreddit, and everybody was kind of stumped by it. I thought it was just me because I'm not a cryptography expert by any means, but we just didn't understand why they were subtracting 16 and adding 1. We think, at least the poster who responded to me thought that maybe they forgot to add or subtract, the initialization vector length. But regardless, all you need to know is that we're taking the rest of the data in that buffer after those first 48 bytes for the initialization vector and hash, and that's going to be what we load into this new array. So you can see down here, we now read from the crypto stream into array 3 the rest of that data, and this block copy is just performing the actual decryption, and all that is stored into array 4, which then gets assigned a result, and that's our, oops, clicked too much there, and that is our decrypted byte array of data. If anyone has an explanation for that, if this does make sense to someone who's familiar with AES and can explain why that's the case, let me know if you can explain that equation they're using to calculate that. If you go to the source code, you can see it's a bit nicer to read in the source down here. They're reading ms length minus iv length plus 1. Again, it works because the ciphertext will never be larger than this, so there's not going to be any overflow, but I just didn't understand that calculation. The vast majority of you are probably like, I don't really care. I tuned out of what you were saying like minutes ago. I just really want to continue on here. So let's get back to actually getting the decrypted result we want. So, like I said, we're reading the last bit after the first 48 bytes are read out of there. We're reading everything else in the array, and that is our actual decrypted data. This crypto stream here is actually performing the decryption under the hood. And when we go back to CyberChef here, we're going to implement that using this AES decrypt function. But what I was getting at is we first need to isolate just our decrypted data. So let's throw in a find and replace here. Or actually, we don't want to do that. We want to actually capture it in a register here first. So this is everything after everything else we've gotten from the buffer here, and that's going to be stored in a different register. I'll click bake again. And so there's the remainder of our buffer. It's going to be stored in R4, our register. Now we want to do a find and replace, and we want to make our input just whatever is in R4 because we want to run the decryption just on the encrypted part of the data. Remember, R3 has our initialization vector, so we don't want to include that. We don't want to include the HMAC at the start. We want to replace all this input with whatever's in R4. Oops, let me do that. Make sure we uncheck these two to make sure it replaces okay. And remember that this is done on a per line basis since we use fork. So this is actually the R4 for the first string that we fed in here. And this is the R4 for the second string we fed in here. So this is our encrypted byte array that we're going to pass into AES decrypt. And look at that, it's beautiful. So to recap, we have our key here. We have our initialization vector. We have CBC as the mode. The input is hex for each, and the output is raw, which is just showing this as strings. And we got all that data by going through. We pasted in the key value that's encoded and encrypted. We pasted in the other encrypted and encoded values. I just did the host and the ports, but you could do all the rest of them if you want to. In fact, let's bring in something like, let's go back to settings here. Let's bring in the mutex. How about? This is the mutex that's going to be created by the executable when it runs. Oops, I need to highlight that properly. And now we can take whatever sample, we can do this exact same thing, open it up, pull out the key, pull out the salt, pull out these encrypted strings, and we can reuse this recipe and decrypt any one of those strings. We take the strings, we separate the key from the encrypted data, we derive the key using our register and our salt and all the data we get from the sample. We then go back to our encrypted data here. We fork it out so that we run operations line by line. We decode it from base 64. We convert it to hex. we grab out the initialization vector, and we first skip the hash. We then grab out the initialization vector, and then we grab out the rest of the encrypted data. We clear out our input and make sure we put just our data that we want to decrypt right there. And then we feed all of our registers into AES Decrypt, make sure our metadata is right, and we have a reproducible recipe for any sample now that we can use to decrypt this data. Pretty cool. So if you want to save away this recipe, you can click save right here, and you can save it in JSON, you can download it, you can do whatever you want. And if you want to load it, I will have this full recipe in the GitHub repo for this video. You can load it right in here, you can call it whatever you want, and you can then reuse it over and over again. Now, bearing in mind that you need to go through and you need to make sure that you have the right salt value and everything stays in correspondence with whatever sample you're looking at. But yeah, that's pretty cool. So this is a kind of, you could think of it as a step up and a step down from using dnSpy, because dnSpy is a step down because dnSpy is just so easy. You set a breakpoint, you literally just read it as the program runs, and you're able to parse out those controls. But having a recipe now that is in CyberChef, we no longer need to run the executable. We don't need a sandbox environment necessarily. We can just run like a strings command on this file and pull out these strings and derive the key and look for the salt. And we can do this all statically. We don't have to run the file at all. And the good thing is that this is reproducible. We can just load our recipe in. If we're doing multiple samples at a time, we open them up, we grab these values out. We don't have to set any breakpoints. We just throw these base64 encoded values in, and we let the recipe do the rest of the work. However, as you just saw from pulling out all that stuff, that is still a pretty significant amount of human effort just to pull out these config values. And so in this next portion of the video, if you'll stay with me, if you're still hanging in there, we are going to work on the most challenging part of this yet, but by far the most rewarding, which is we are going to create a fully automatic way to parse out these config values by, similar to what we did with the recipe here, recreating the functionality of the malware, but we need to go 100 times deeper, not 100 times deeper, but quite a bit deeper, because when we start working with an automated parser, we are no longer a human who's looking in dnSpy and pulling out these strings in this nicely laid out high-level code. We have to tell our parser exactly where in the file, how to find these things. My VM's shutting down. Sorry, it's blacking out in front of us as we speak. We need to tell our parser exactly where to find those values, exactly how to get them out of the executable, and recreate the AES decryption algorithm we've kind of pseudo recreated here in CyberChef, all from scratch. It's going to be a big challenge. It's going to be a lot of upfront work, but I promise you, if you stick with me for the rest of this video, which is going to be, this is by far going to be the longest and most intensive part. If you stick with me though, you're going to learn a ton, and you're going to get some tools to help you build configuration parsers for not only ASyncRAT or .NET samples, but the concepts we'll be going over will help you build resilient malware config parsers for any malware family. And I think it'll be a really good exercise if you're willing to, like I am right now, get a drink, get some caffeine, sit down, and come with me as we dive into this and build from scratch a pure Python parser that we can fully automate. So this is something that we can pass in multiple files, and we can run this parser against them, and it will pull out in seconds all the configuration for all those files. In fact, before we get started here, let me go ahead and pull up a demo of the finished project, so hopefully you have a little bit of motivation to get started and stick along through the ride. So I'm going to pull up another VM here, and on this VM, I have several ASyncRAT samples, real samples from attacks, from different malware repositories that I pulled down all these. One moment, it's just loading up in the other desktop window here. All right, I've got a Kali VM here, and this is just housing some of those malicious samples that I've downloaded from malware repositories. Again, I just didn't want them on my host machine, and this one has Python 3 already installed. So I have our completed config parser here and a ton of different samples in the samples folder. So I'm going to show you what this completed product is going to look like when we're done. We're going to run it on a single sample here and pass it to the JSON formatting tool that comes with Python. And look at that beauty. We've got a completely decrypted config. We've pulled out the key and the salt, and we have the config here in plain text. You can see the mutex, the ports, the hosts, everything right there. And you can even run it on multiple samples, a whole folder of samples you can decrypt in seconds. So this is the goal for the rest of the video, is to build out this beautiful JSON decrypted config, this parser Python file that can be included as part of a bigger pipeline. Like let's say you have a sandbox that runs Python, multiple like malware decoders against samples, or you have a bigger pipeline you want to bake this into. You can just import this Python file, run it against hundreds or thousands or hundreds of thousands of samples, and decode all of the different configuration strings from there. All right, with that in mind, enough of the hyping up. Let's get down to work to actually build this thing out.
All right, if you've made it this far into the video, assuming you stayed through the first part, it means you're accepting the challenge of coming along with me and building out this Python parser from scratch. And I'm really happy to have you here. I hope you've taken a minute. If you did sit through the first part of this video, through the CyberChef explanation, the dnSpy explanation, I hope you've taken a moment to take a break, get some caffeine, rest up. I've taken a full day myself. I was recording the first half of this well into the wee hours yesterday because kids, and I'm glad to be back and I'm feeling a lot better. And I hope that my explanations tend to get less lucid as the night goes on. So if you do have questions about anything we've discussed up to this point, please leave me a comment so we can clear things up. But now that I'm feeling great, I hope you are too. And we're doing this thing. Let's start by just opening up whatever your preferred text editor is. I'm going to be using VS Code. You need not use VS Code. You can use Atom, Notepad++. You can use Notepad if you want to. You can use VI if you really, really want to. To be honest, if you're using VI, I'm surprised you're here and not up in the mountains reading Linux koans to wandering wards or something. I don't know. Doesn't matter. Regardless, we're just going to make a new file in whatever your text editor of choice is. And I'm just going to stick mine in my downloads folder, and we'll call it ASyncRAT config parser. Very descriptive, very cut and dry. And I'm going to go ahead and include a shebang line here. If you're not familiar with this is just a line that shows what program, on mostly Unix environments, what program should be used to run this file. And we want to run this with Python 3. Again, we're going to be writing this in pure Python, meaning we're not going to download any external libraries to use. We're going to use some of the built-in libraries in Python 3. But I will say that while this should remain backwards compatible for every flavor and version of Python 3, it will definitely not run on Python 2.7 just because of the syntax and some of the constructs we're going to be using. So just keep that in mind, that this is meant to be run in Python 3, and you'll see down here that on my host machine, I'm running Python 3.10. I've run this, I think, at this point on 3.9, 3.8, and 3.6 without any issues, so I'm fairly certain that you shouldn't have any issues either, as long as you're running it with some version of Python 3. And the first step we're going to do before we dive back into our code and our virtual machine here is we're just going to set up a little skeleton here. So a couple things I'm going to do first are just kind of some housekeeping things. I'm going to set up a logger, and I'll explain this just in a very basic level in just a second. We are going to need to import that get logger function. And this is one of those things that causes holy wars in the land of Python and other programming languages. I am a person who, instead of doing so in Python, for those who may not know, you can do import logging and then do something like this, logging.getLogger. A lot of people prefer that syntax of using import and then specifying directly what you're importing. It makes it kind of clearer where you're getting this function from. I am one of those people who enjoys using from and then import every thing that I need, but nothing else from the modules. So if you take issue, the reason I'm bringing this up is if you take issue with my coding style, that is fine. I do a lot of infuriating things, I'm pretty sure, to kind of, professional Python programmers. I do appreciate constructive criticism if there's something I'm doing that could really be done better. But if you just hate my style for the sake of hating the way I do things, feel free to leave a comment, but I've stopped feeling feelings since like mid 2020. So it's probably going to fall on deaf ears. But if you do have something constructive to say, I'm always happy to hear tips and other good stuff about coding styles. Really into that. Anyway, let's get back to the code here. I'm just calling this function called getLogger, and you'll see I passed in this odd looking argument here called __name__. And the very broad, I don't really want to get into the details of the Python logging library, but I will link the docs in the description. You can also just Google logging in Python. This basically makes it so that if somebody's importing our script, which they may be if you're using this as part of a malware analysis pipeline that includes other scripts and other tools and stuff like that, this just gives more granular control over the logging for our particular module. And this __name__ variable basically holds the name of our module. And long story short, this sets up our own logger just for this file. So we're just making a logger and we're passing in the name of our particular module so that we can have a little bit more granular control over logging. If you want to get more descriptive than that, I know I probably kind of glossed over a lot of details that people might think are important. I think that's pretty much all you need to know. But if I did say something that's actually blatantly incorrect, please feel free to leave a comment and I will correct myself. So we'll do that, and then we're just going to make a class here. And I want to wrap all of our parsing functionality into a class because, again, I want people to be able to run this file on its own, but I also want them to be able to just import our parser code into whatever pipeline they may want to. So putting it in a class kind of encapsulates all of our parsing code together. It makes it kind of more modular so that it can be imported into other projects. Right now, we're not going to do anything with the class itself. Actually, we're going to do one thing, and that is just write a skeleton for a report function. And we'll just do something like that there. I do need to add, I think, this. There we go. And we'll just leave it as that for now. Obviously, we're going to add a ton more in just a second. But first, I want to make a little runner program, meaning that if somebody does run our script by itself, it shouldn't just include the class, but it should also contain a little program to actually do the parsing and show the user how this thing's meant to be used. So what we're going to do is, again, using a bit. If you're not familiar with Python, this may look a bit odd. We're going to use this construct here. Just a moment. I just want to set something up in my, there we go, other screen real quick. This is basically saying if name equal to main or equivalent to main here. This is a weird looking if you're not familiar with Python or haven't worked with it before. But basically what this is saying, again, speaking in generalities here, is that we're checking to see if our script is being run on its own or as part of an import. So if we're being imported, if somebody's importing this class, we don't necessarily want to run what's going to basically be our main function here. If they don't want it to run, they may just want our class, or they maybe want something from this file. Maybe they don't want to run it. They just want to import it. But by putting this if statement here with this if name equivalent to main, we're checking to see if this file is being run on its own. And if it is, we're going to run all the code that's going to be underneath here. And the first thing we want to do is set up an argument parser, one of the cooler libraries, from argparse, import argument parser. One of the cooler modules in Python. It's been around forever. It's in Python 2.7, Python 3, and it's outstanding at just making it easy to collect arguments, command line arguments from your user. And so the way we're going to use this is just make a new argument parser object, and we're going to add some arguments to it. What kind of arguments do we need? Well, we're going to need from the user one or more file paths. So we'll make an argument called file paths. And to make it so that they have to enter at least one, we're going to put n args equal to the plus symbol here. So nargs, number of args, basically tells this argument parser how many arguments we expect. We could also use something like star here, and that means that this is optional. So 0 or more could be stored for this particular argument. Plus means 1 or more. Just like in regular expressions, the plus symbol means at least 1 needs to be specified, or else we're going to throw an error message there. So we need at least one file path, which is going to be our ASyncRAT payload to parse. And then we'll add a help line here. The help line just tells the user what this argument is for. Oops. I cannot spell for the life of me. There we go. One or more ASyncRAT payload file paths. So that's great for our first argument. And the second argument we want to add is an optional one, and to specify that it's optional, I'm just going to put a tac there. Tac D is the shorthand. We can also make a kind of more verbose version of tac debug, and we'll set the action to store true, and I'll explain what that means in just a bit. And what this is going to do is enable debug logging, and I'll also talk about that in just a second. You'll notice, by the way, every time I hit save that I have a formatter, the YAPF formatter, so that every time I hit save in VS Code, it's going to format my code for me. So you may see things shift around a little bit, but the code should stay the same. So let's go over this one in a little bit more detail. Like I said, this is an optional argument that the user can either type tacd or tacdebug to activate. This action store true means that if this is specified, we're going to access these arguments by doing something like this. We'll just make another variable here called args equals ap.parseArgs, so that actually collects the arguments. So the way we're going to access file paths is something like args.filepaths. By default, you can override these names, but by default, they just take whatever name you've passed in here in the string. And the other way we're going to access this debug argument, I should say, is just by typing args.debug. And so what the store true action does is it says, if the user specifies this flag or this argument, we store true in this variable. So it's a Boolean variable. That's all that action means. So it will be false unless the user specifies that. So let's back this up here. We've parsed our arguments. Now we need to do some stuff with those arguments. So first, let's see if the debug flag was actually specified. And if it is, we're going to create a basic logging config. We do need to import this from the logging module here. And this just sets up a really simple, well, you can see right here, VS Code has these nice little hints here. It does a basic configuration for the logging system. So this basically just logs everything to standard. I think it's to standard error by default, maybe standard out. You can look at the documentation to check me on that. But it's basically just a very simple logger. We don't have to mess around with any crazy configurations, custom configurations here. It's just going to make our logger functional. And if the user specifies the debug level, we want to set the level of our debugger to logging.debug. This is actually a keyword that we need to also import from the logging module. I forgot what I was going to say there. Another thing we're going to need to... Oh, no, you know what? Actually, we shouldn't need that. I was thinking that we may need to import one other thing from here, but I don't actually think we do. I think we're fine there. No, actually there is. I know what it is now. Sorry. We need the alternative, which is the warning. So let me explain a little bit about the levels here, but first let's finish this. 10 minutes in and already all over the place, but I have been drinking some energy drinks here to get pumped up for this, so I'll use that as my excuse. Here we go. All right, so if the user tells us that they want debug logging, we're going to set the level of our logger to debug. If they don't, we're just going to set it to a lower level, which is warning, or a higher level, depending on how you look at it. And to explain this, I'm going to go to the Python logging module documentation here. So this is just right on the docs.python.org site. And you'll see this nice little table here talking about logging levels. So the way the logging module works is you set a default level, And everything at that level of logging and above in this table and a numeric value will get logged. So if I set my logger to informational, for example, it means I'll get every informational logging message, plus every warning, every error, every critical, but I won't get any debug messages. On the other hand, if I set it to debug, I get all of these. So any kind of messages I'm going to receive in debug mode. And then if I set it to warning, which is the alternative we set up for our parser, I'm only going to get any warnings or errors or critical exceptions that happen. So basically, we're offering the user a way to turn on some extra verbose debugging logging, and we're going to use this actually as we build out our script to make sure everything's working as intended here, and to also log any errors or anything that comes up there. So with that taken care of, the next thing we need to do is just handle all of the different files that are going to be passed in through args.filepaths. I'm going to wrap this in a try except block. If you're not familiar with that, or exception handling in Python, I would read up the docs about that. But basically, try except block allows us to try to do something in Python. And if something goes wrong, we catch, it's called catching the exception. And that allows us to gracefully exit our program and print a nice message to the log to make sure that our program just doesn't crash. So for each file that the user specifies, we want to pass in that file path to the parser object, to the parser class, and make a new parser object. I'll explain that in just a moment. And we want to call the report function. So we're going to print the decrypted config from that report function. Right now, we just kind of made a skeleton here. So we're going to accept any type of exception, and we're going to send that to our logger with an exception level of logging. So specifying logger.exception means we're going to send an exception message to the logger. And I'm going to use that little F I just typed there means that this is a formatted string. And what that means is I can just stick, using the power of curly braces, I can just stick a variable name in here, and that variable name will be replaced with whatever values in that variable. So what that means is whatever file path I am currently trying to open or work, it'll say exception occurred for that file name. And this exe_info equal true will print a nice little stack trace to our user to show them exactly what went wrong with that file. And now that we've caught that exception, we can gracefully just continue on and skip that file and just report the exception to the user and continue on with whatever other files, if there are any, that the user specified. And that is it for our logging program. That is all we need for this to be successful. The hard part is just making this one line work. We have to build out our parser class and then build out our report function, which is later on going to actually print the decrypted configuration contents to the screen. All right, hopefully you're still with me after that. If we want to test this actually real quick, let's do this. Let's just we're going to make a constructor here in a little bit anyway. So let's just make that a pass, and we'll go ahead and put in that we're going to send the file path to this object. I'll explain this constructor here in a second. All this means right now, though, that you need to know is that we're passing in a file path to a specific instance of an ASyncRAT parser, but we're not going to do anything with it right now. We're just going to make a little quick test here. And let's go ahead, instead of a pass here, let's just print report. And we'll just test to make sure that our runner program is working as we expect. And within VS Code, we have this cool little built-in terminal. So I'm going to use that and just run Python ASyncRAT config parser. Let me just run it without any arguments here, and you're going to see that I get an error, and that's because it's saying, hey, dummy, you said you wanted one or more file paths. You didn't give me one, so I'm showing you how to use this thing. Our user, with the magic of arg parser, can also type tag H, and they can get a nice description showing our help messages about each one of these arguments. That's why we love argument parser. Very nice module to use. So let's do it properly this time. Let's type ASyncRAT. We're just going to feed it itself, basically, as a file. We're just passing in a dummy value for the file name. And you can see, hey, ASyncRAT parser report takes 0 positional arguments, but you actually gave one. So let's see what that was. Dot report here. Oh, you know what? I think it's because I created a new object there. So let's do this. Let's add a self here. I'll explain the self stuff in a minute. That can also be something very confusing with Python. So let's just add that self keyword and see if that works. And it does. Okay. So yeah, we see that our function is working. It says print report. And then it also printed none. Why did it print none there? So he said print report. We're going to do some debugging here. So we printed report. Oh, it's because I see. I've done something very redundant here in my report function, and I'm actually glad I did this. It allows us to do a little bit of troubleshooting together. I'm already printing the result of report. It's redundant to print a print statement, so I actually need to return the string report here. And now we can see that I just get the output I expected. All right, so now we're through me bungling that up. Let's go ahead and just, actually we can leave this the same for now. Let's go ahead and start to build out our ASyncRAT parser class. As we do that, I want to talk, before we get into the parsing functionality, I want to just take a little detour and talk for those of you who may just be starting out in Python. First of all, let me get rid of this terminal so we have a little more screen space. Talk about object-oriented programming a little bit in Python and what this self keyword is all about. So when we declare a class like this, we can have class variables and class functions like this that can be referenced anywhere. So for example, if I make a dummy list right here and I just make a blank list, I can, in my main runner function here or anything else, I can say, well, actually, let's put something in here. Let's put the number 1 in this dummy list. And let's just do, we'll comment this out for now and say print ASyncRAT parser.dummy list. And notice I didn't pass in anything to ASyncRAT parser. I'm purely accessing this variable that's in the class. Shouldn't have closed my terminal so early. Let's go ahead and run that just as an example to show you what this looks like. And it prints the list. So that is a class variable that's going to be available whether I create what's called an instance of this class, a particular object of this class, or not. I can access that no matter what. But when I create a constructor here, let's say I also make a dummy list in my constructor equal to, we'll say whatever we pass in here. So let's say DL, and we'll make it whatever we want and then run a program in a second. We can say right now it's equal to DL here. And so what I'm going to do down here is also pass in FP and let's just make 1, 2, 3, a list of the numbers 1, 2, and 3. And let's print out what that object is .dummy list. And let's see what happens. So you'll notice that I created a new object, but, oh, what I forgot to do is use the self keyword here to assign this particular object its own dummy list. So this is actually going to overwrite this class dummy list right here. So if I run it again, now you see that it's been overwritten by whatever I passed into this particular object. So hopefully that wasn't too confusing. What I'm trying to demonstrate here is that you want to use the self keyword to make variables that are going to be specific to each particular instance of this parser object. What that means practically is that as we create a new parser for each payload we're analyzing, we don't want to share variables amongst the payloads because each payload is going to be a little bit different. So what we don't want to do is something like, let's do this actually. Let's take out this self.dummy list and let's just say dummy list dot append 2 here. Or let's do ASyncRAT parser dummy list append, or actually we can even use the self keyword here. These are basically equivalent at this point. Self.dummy list append 2, and let's this time create 2 objects. We don't need this argument anymore. We're just going to create 2 objects here, and we're going to print dummy list each time. Let's run that. So what happened? The first time we printed, we get 1 and 2 because we had at the start, dummy list just had the number 1 in it. And then when we created our first object, we appended a 2 to that array. But when we created our second object, even though we're referencing self here, it's using this class variable up here. And so it appended another 2 to that same list. And the problem is that if I create another, or if I access any other dummy list, like let's do this instead. Let's create 2 objects like this. And B will be the same thing we just did. And let's say b.dummy_list.append 3. And let's print just a.dummy_list here and see what happens. Oops, what have I done here? I don't need these right here. I need to take this off. There we go. Now we get 1, 2, 2, 3 in, oops, I meant to, yeah, in a.dummy_list. Yeah, I did that correctly that time. So when we created one object, we started with this list with the number 1 in it. When we created a second object, or when we created one object, it appended 2. When we created a second object, it appended 2 again. And when we appended just to the B object, the number 3, we then print a.dummy_list, and what the heck? It also has a 3 in it. This is a detour just to explain the dangers of not using the self keyword in order to make particular instance variables. So basically what I'm saying is we don't want to modify all of the instances of our class at once. We want to use self to only modify one particular instance. So the way we do that is do something like this, where we do self.dummy_list equals, we'll do something like this, a blank list, and then self.dummy_list.append, and we'll throw in another argument here called n, and we'll just add that. And let's do one last experiment here, and then I promise I won't bore you with any more experimentation here. We'll do ASyncRAT parser. Well, let's create 2 objects again here like this. Oops. fp1 b equals ASyncRAT parser fp2 print a.dummy_list print b.dummy_list. And let's go ahead and run that and see what happens. And now we see that we get our expected result here, which is that A has a dummy list that only has the number 1 in it. B only has a list with 2 in it. Everything is as it should be in our world. I know that was a long tangent. I'll put a timestamp in so that those who don't care about this at all can skip over that. It's probably too late if you watched this far, sorry. But I do think that was important to go over so that people aren't confused about why we're using the self keyword if you've never experienced this in Python or another language before. So with all that said, let's delete all of this back and get back to doing what we came here to do, which is write this malware config parser. ASyncRAT parser is not defined. Oh, I think it's because I overwrote my constructor here. But it's actually the constructor we're going to work at next. I just wanted to make sure we cleared up any errors here, and we're back to working. So let's go ahead and exit our terminal. We'll close this out. And let's get to work on actually making a functional constructor here. Now, for the rest of this time that we start working on this parser, some of the feedback I received in my last video is that for those of you who are coding along with this at home, you would have preferred to have a little bit of time to kind of think through the problems we're going to solve on your own. So what I'm going to try to do is leave some room here. The kind of process I'm going to use is we're going to write the pseudocode and think through how we want to solve a problem. We'll write some pseudocode as a placeholder for the real code. I'll give you an opportunity to pause the video so that you can go through and try to solve that code yourself or implement it yourself. And then we'll go over my particular solution for implementing the pseudocode that we write. Your code at the end of all this doesn't have to match mine perfectly. In fact, if you come up with more efficient ways to do things or better way to do things, that's awesome. But I am going to give you my implementation, of course, and you'll get the full output in the GitHub repo in the description of the video and all that good stuff. But If you do want to hone your skills, it's a really good way is just to take a look at the problem first, try to solve it yourself, and then see what works for me and see if what you wrote also works. And the first thing we're going to do is do something with this file path that we're passing into our parser. First, let's go ahead and store it in a instance variable called file path. Just pass it in like that. We'll call it the same thing. And then, of course, the first thing we're going to want to do with that file path is read something from it, right? So let's make another instance variable called self.data. And let's write a function for this. Let's just call it get file data, rather, not file path. There we go. And so let's go ahead and write a little declaration for this. Define get file data. And you'll notice, just like the report function below, that I'm going to pass in the self keyword here. And what that's going to do is it's going to give us access to all of our objects instance variables. If I don't include that, then I don't get access to self.filepath or self.data. So I want to make sure I'm passing that into all of our functions here that need those items. And I'm going to type in the pseudocode here. So what we want to do is open the file path and read in the binary data, log an exception if something goes wrong opening the file. So this is just a very quick little function to kind of get you used to the style that we're going to be using. Again, I'm writing some comments here that have some pseudocode about what we want to accomplish. And so at this point, I would invite you, if you're coding along at home, to pause the video and take a stab at actually implementing this. And I'll give you a moment to do that, and then we'll move on and actually implement it. All right, so let's go ahead and implement this. I'll just leave the comments there just for reference here. I'm going to go above and beyond. You don't need to do this part, but I'm going to do it just so we can kind of trace again through our code and make sure everything's working as intended. I'm going to make a little logger message here, a debug message. So this will only show up if the user has specified the debug flag. And I'm just going to say reading contents from, and then I'll pass in our self.file path here. And so that'll print to our log that we're reading in contents, and so we know exactly where we are in the code when that log message is displayed. Now the part about logging an exception if something goes wrong, we want to put this in a try except block again. We're going to try to open the file path, and we want to make sure we specify the flag RB, so R meaning read, and B meaning binary, because we don't want to open this as a text file. We want to read the binary contents of it. We're going to be working with bytes here. So we want to make sure we specify those flags, and we'll just open it as an object called FP, and we'll say data equals, fp.read. And if something goes wrong, no matter what that something is, we're going to say accept exception as E. And so I'm going to pause here for a second to talk again about things that start Python holy wars. Typically, I will admit that when you're writing Python programs, you typically want to get as specific as you can with exceptions. You generally don't want to use a generic exception here. You might make an except case for a file not found exception or a file corrupted exception or whatever. In this case, for our parser, this will be the case for many of the exceptions. I'm going to leave this as the generic, just top level exception class. And the reason I'm going to do that is because I'm going to use a cool new-ish feature of Python 3 called exception chaining to actually pass custom exception messages no matter what exception was encountered. We could spend some time building out different exception cases to make more specific exception logging messages, but for our purposes, it's just not worth the squeeze to go into that. So what I'm going to do here is I'm actually going to go up here and declare a new inner class called ASyncRAT parser error. And I'm going to put the word exception in the class parentheses here. This means that it's going to be a child class of the Python exception class that allows it to have all the behavior of every other Python exception. And we really don't need to do anything else with it. We just need to put the pass keyword there. And because this inherits everything from exception, we can treat it just like any other Python exception. Why am I doing this? The reason I'm doing this, you don't have to do it this way, but the reason I'm doing it is because I like to raise custom exceptions throughout our parser that are going to put in to our log some error messages that are very specific to what we're trying to do with the parser,
but we're going to use that cool feature exception chaining to actually display not only our custom exception message, but why that exception was caused. What do I mean by all this? Let's look at an example. So let's use a custom exception message here. This is error reading from path, and then we'll say again our file path here. Oops. Path. And we're going to say, oh, I need to close my curly braces there. Raise our custom exception from E, which is our exception that we caught here. E can be whatever caused this exception. It could be a file not found exception or some other file related or input output related exception. And the reason I'm using that from E is because that is going to allow us to chain these two exceptions to say, hey, E happened right here. Here's the type of exception E is, and it directly caused this custom exception. And this custom exception has a message that'll show you exactly where we were in our parser that this problem was caused. So let's go ahead and finish out this function real quick with a debug statement. If it is successful, if we don't run into any exceptions, we're going to say successfully read data. And then we'll return data, and that will, of course, get stored in our self.data object. Also, it's giving me a squiggly here because I need to include the self keyword to make sure that I'm getting the correct function here. So let's go ahead and test this. The way we're going to do that, let's go ahead and open up a terminal. I keep opening new terminals. I don't really need to do that. Let's run this. And we're going to run it with the debug flag just by clicking tacd there. And again, we're just going to feed it itself just as a test here. Actually, we're not going to feed it itself. Let's feed it a non-existent file this time just to trigger that exception to show you what that exception training looks like. So I'm just going to add an underscore file here. When I run it, we're going to see a very detailed message here. So what happened? First of all, take note that our logger is printing the custom messages we wrote right here in our logger debug statements because we specified the debug flag. And then we get an error message here. Exception occurred for ASyncRAT config parser. Hey, file not found error. I didn't find this file that you specified. Now look at this phrasing here. The above exception was the direct cause of the following exception. And it's there that we see our custom ASyncRAT parser error, which shows, hey, I had an error reading from path ASyncRAT config parser file.py. Now in this case, these two errors are very similar to each other. So we could have probably gotten away with just catching a file not found error and printing that to the user. But later on, we're going to use our custom exception class to print very bespoke error messages to our user that are very specific to what our parser was trying to do, that the generic exceptions may not do a good job of explaining. So it's just a way, this whole Python exception chaining rigmarole, you may call it, is just a way to be more verbose to the user about where the error occurred and what exactly happened to cause an exception in our parser file here. So with all that out of the way, hopefully you had an easy enough time. You didn't have to do all the custom stuff that I did here, but hopefully you got this piece right, just reading in the binary data from the file. And I would say if you did struggle with that, you may want to take some time to just familiarize yourself a little bit more with Python before we go further, because it will get more complex from here. But hopefully, even if you don't, hopefully you still are able to hang in there, because I'm going to do my best to explain all this different functionality here. All right, so we're off to the races. We got data from our file. What the heck do we do with that data exactly? Well, now we need to bring back up our ASyncRAT payload that we generated in the first part of this video. All right, that is all loaded up now. Let's get back to the settings class and take a look at this section. So when we were looking at dnSpy and CyberChef, it was very easy for us as humans to navigate here and see exactly where the config is being decrypted, right, in this function. The tricky part of this whole Python parser building project is that we need to tell the machine how to do the exact same thing when it's not going to have this nice disassembly to go and look at. I will say there are different libraries that we could use, external non-built-in libraries like Malware Frank has a library called dnFile, which is used to help with disassembly and analysis of .NET executables. So you could use external files or external libraries to help along with this process of telling the machine how to read this config. But we are not here for that. We're here to learn. We're here to do it the gritty way, which is by scratch. And we're going to do that by creating some custom functionality to identify where this section is in the executable just based on the binary data, and then read through and recreate the kind of decryption functionality we see here using Python. But I did want to just mention that there are libraries that will help you do this if you don't feel like doing this in pure Python, if you're not limited in downloading external libraries. All right. So before we get to any kind of coding, let's revisit what we saw here in the configuration and talk through the problems we're going to have to solve along the way to decrypting these values. So the first thing we already nailed is step one, we need to actually identify where this config begins in this file. Let's talk about that a little more. In order to see what this is going to look like to our Python parser, which is the binary data, let's go a little bit deeper from this high-level code down a layer of abstraction to the IL instructions. So if I right-click here in dnSpy and go to Edit IL Instructions, I get this kind of very similar to assembly language-looking instruction set here. So this is basically what dnSpy is translating into this nice higher-level language for us. These are the actual intermediate language commands and ops being run here. So you can see that each op has an opcode and an operand, which explains, or an operand that goes along with the opcode, I should say. What the heck do all these opcodes look like on disk? Well, they're going to have different hex values followed by their operand. So if we go one layer deeper here, let's go to just see what, for example, this settings.ports equals decrypt settings.ports looks like. Let's go to right click and show instructions in hex editor, and dnSpy is going to do us a solid and highlight exactly where in the hex of the file. Actually, let me go back and redo that because I zoomed in a little bit, threw off my viewport there. There we go. It's going to show us exactly the lines or the bytes that include those instructions. So how do we translate these byte hexadecimal representations into those instructions and operands? Well, we can take a look at the glorious Wikipedia page of CIL, or Common Intermediate Language Bytecode instructions. Let's take a look at, for example, when we went back here and did edit IL instructions, we saw a LDS field. Oh, actually, let's start here. LDS FLD settings.ports, call virtual decrypt, STS field settings.ports, LDS field AES 256, blah, 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 LDS field. You see this same pattern occurring over and over again. We LDS FLD for one of these settings, the configuration settings name, the name of the variable here, host, ports, version, install, all this good stuff. We call the decrypt function using call virt, and then we STS FLD, which means we store a value in hosts using the return value from that, the call to decrypt, basically. So what the heck does that all mean? Let's take a look. We'll focus in on the ports for now. So let me just go ahead and right click and reset that view here. Let's look at LDS FLD in the wiki page here for CIL instructions. And of course, I'll link this in the description as well. So first of all, from left to right, we can see that the leftmost column here shows the hexadecimal opcode for this operation. So LDS FLD is equivalent to 0x7e in hex, 7e. And then we pass into LDS field a field, and that's going to be an address that we pass in to that LDS field here. So push the value of the static field onto the stack. So when we look at the hex code here for these instructions, like right here, let's go to edit, or not edit field, sorry, to hex editor rather. we can see, hey, there's the 7E that indicates the LDS field instruction. And let's take a look at some of these other instructions here. So right after that, we see a call vert and then an STS field each time. So call vert, if I can spell it, it's going to be a 6F and then STS followed by a method. STS FLD is also going to be 80 followed by an address for a field as well. And sure enough, if we go in here, we go to instructions in hex editor, we see 7E, so that was our LDS field, followed by 4 bytes for an address, followed by 7E, followed by 4 bytes, followed by 6F for that STS field. Am I getting that right? What is the, I don't want to mix up my ops here. Call vert, sorry. Call vert. And then the 0x80 is going to be the STS field, which is what we see right after this call to call vert, or this operation for call vert. All right, so now we know kind of at a very basic level how to kind of translate these IL instructions into the hexadecimal representation that we're going to see on disk here. How does this help us exactly? Well, the reason it helps us is because, let's go down to where these are actually defined down here. If we do the same thing where these different values are defined, keeping in mind that these are the encrypted values on disk, let's take a look at what these instructions look like. So each initialization looks like an STS FLD, or I'm sorry, I really should start from the top here. The load string, or LDSTR, loads in a string that is hard-coded in the executable, and the STS FLD loads that string into a particular variable name here. How does that help us? Well, if we look at what that looks like in hex, first of all, we need to look at the opcode for LDSTR, which is 72. We know that STS FLD at this point is 80, and we can see that represented right here. 72 for the load string followed by 4 bytes, and 80 for the operation of STS FLD followed by 4 bytes. Now, the load string operand, if you look right here, is going to be, as we saw in the intermediate language, that's going to be our hard-coded string. That's the address to that string. And for the STS field operator, that has an operand of the address to that field. What is that? What exactly is located at those two addresses? Let's take a look at that next. So for the load string, we expect at that address that's going to be the hard-coded string, which for ports is going to be this base64 encoded string that begins with 3+n. Let's take a look at what sits at this address here. And we do need to be careful. If you haven't heard about Endianness, or know what that means, and that's ENDIAN, Endian, and Endianness, what that means is that for different architectures and sometimes different programming languages, you have different Endianness for how addresses are represented in hexadecimal or on disk in code, etc., etc. All this means for us, to put it very simply, is let's pull up a new file here. There are generally 2 types of Endianness: little Endianness and big Endianness. And what this means is, if we're looking at the address 0x77, or let's use something like 1, 2, 3, 4, 5, 6, 7, 8. Let's pretend that's a valid address. If we're using big endian notation, we would see this on disk and represented as 1, 2, 3, 4, 5, 6. Remember, every 2 digits or 2 hexadecimal characters represents 1 byte. So each one of these, 1, 2 is 1 byte, 3, 4 is 1 byte, 5, 6 is 1 byte, 7, 8 is 1 byte. So if we go up and look at the wiki page for Endianness here, yes, there is a page for everything. We can see that in big endian systems, the most significant byte of a word is at the smallest memory address, and the least significant byte is at the largest, and it's the reverse for the little endian. The least significant byte is at the smallest address. What that means here is that in big endianness, this is the most significant byte. That's going to be on the far left as we're reading it left to right. And in little endian, we're going to reverse this, and it's going to look like this on disk, because the most significant byte is now going to be at the higher address, which is further to the right here. Hopefully that explanation makes sense. All it means is that we need to read the addresses kind of in reverse here. So if I see this in little endian, which is what we're going to be working with in these files, I need to mentally make sure I know that this means 0x, 1, 2, 3, 4, 5, 6, 7, 8. Except I want to maybe use 6 and not 9 there. Hopefully my explanation was, my half-assed explanation, I'll admit it, was enough to explain that concept to you. If not, please check out the links in that Endianness article so that you can get that in your head, because it's going to be important for our analysis here. So going back to this operand that we're loading the string in from, we need to read this as 700000F. That is a virtual address that we want, actually a relative virtual address. And while we're on that topic, we're going to take a short, I promise it's going to be a quick little detour, because somebody actually called this out from my last video. I didn't spend a lot of time talking about what I meant by virtual addresses and relative virtual addresses and offsets, and those concepts are going to be very important here. So I do want to take a moment, and I will share with you in the description a link to this nice blog that kind of lays this out very nicely. So virtual addresses allow us to kind of abstract away physical memory, and they are just memory addresses that are referenced by an application. We're going to see that when a program is loaded into memory, it receives kind of its own virtual address space to map itself to. A relative virtual address is basically an offset calculated using virtual addresses. So each file is going to have an image base address, and a relative virtual address is going to be a virtual address minus that image base. So the example given here is that an application is loaded into memory having a base address at 0x400000. And let's say we're looking at a virtual address at 0x401000. The RVA is going to be 0x000100. So we're basically just subtracting the image base from that virtual address to get the relative virtual address. And when we talk about file offsets, we're really just talking about physical memory. And this is what our parser is going to be working with. It's literally talking about, if I'm talking about the 0th offset of a file, it's the very first byte of that file. If I talk about the first offset, or the number 1 offset of the file, I'm talking about the first byte. So I wanted to make sure those concepts were clear before we go any further, because it's the 700000F is itself a virtual address we're going to be looking at here. All right, so now that we talked a little bit about virtual addresses and relative virtual addresses and offsets and all of that, hopefully it's clear at this point. If not, please take some time to read that blog post, and I think he does a great job of laying it out. Let's try to verify that that string is stored at that particular address to make sure that our hypothesis here is correct. So let's just take a snippet of this string. We'll copy it. We'll open up the hex editor again, and let's just search for this in the binary code here. Make sure you're set to string UTF-8. And let me take this down. All right, so what am I missing here? Do I need to go to string Unicode? I do. I need to change that to Unicode, actually, because it's not stored as a UTF-8 string, where basically those are two different character encodings. And they are separate because in Unicode strings like this one, you'll see null bytes in between each character like that. And you won't see that with UTF-8 encoded strings there. Anyway, the most important bit of this is I just searched the value of that ports string there, the encrypted string. And we can see dnSpy highlights this whole section, which shows us the value. And looky right there in the hint, you'll see that hashtag US, which we'll come back to in just a moment. And we'll see the address 700000F, which is what we saw in that load string operand. So our hypothesis is correct. It's loading the string from that offset in the file. Now, I made an oopsie already right there. I said offset. Our Python script wants the offset that 70, we can't just say, hey, Python script, go grab the string at 70000000F, because that is a virtual address. It's not an offset. So we're going to need to figure out how to convert that to an offset for our parser. That's one thing we need to keep in mind here. You also may notice that there's a section here that's highlighted, and then there's 2 bytes before that that are highlighted and a byte after that that's highlighted. So let's take a moment to talk about what's going on here and what is this US identifier that we see here. And I've linked a couple of articles about this. This one here from redgate.com, this one from Code Project, that talk about this construct that's kind of specific to .NET executables, and that is streams, storage streams, and other types of streams. All but one of these are heaps, which are unstructured binary data. And you can see there in .NET, there are a number of predefined streams. There's one called the metadata stream, or I call it #tilde. I'm sure .NET developers would cringe at that. Like, he doesn't even know that we actually call it, I don't know, #Swinton or something. I don't know. I'll usually refer to it as metadata stream or storage stream. This stores information on the types, methods, fields, properties, and events in the assembly, so in our executable. And the metadata stream has predefined contents and structure. The strings, #strings, which we're going to see this guy in just a little bit, spoiler alert, is a heap where all the namespace, type, and member names are stored, like variable names. And then we have this US or user string heap. This stores all of the strings that are used in code directly. So all of the hard-coded strings are going to be in this US stream here. I'm not going to talk about these two because for our purposes, we don't need to worry about GUI ID or blob. But the US, the strings, and the storage stream are going to be very important concepts here when we get into digging into our parser. And we're also going to need to know a little bit about the metadata tables. These are in the storage stream here, the #tilde stream, as I like to call it, or storage stream. I'll just say storage stream. The metadata section is organized into 45 tables, which are binary arrays of predefined structures containing information on various aspects of the metadata. Each entry in a table is called a row. And well, this is all probably going to sound very confusing right now. We'll come back to that in just a little bit. But I want to highlight that we're going to be becoming intimately familiar with the string stream, the US streams, and the metadata tables here. But for now, let's go back to our code here and focus on what we just found out. And that is that this US stream is going to have all of our actual encrypted data values. That's great because if we can tell our parser where these are located in this stream, we can parse out the encrypted data, which of course we need to decrypt it and turn it into something usable to our user. Now you'll also see that dnSpy, like I said, is highlighting these 2 bytes before this section here with the string and the 1 byte after. Now the 1 byte after is just a terminal byte, and if you hover over it, it'll tell you that. But what about these 2 bytes here? These are length bytes. And if it wasn't for a random comment on this code project link that I will link to you all as well. Let me see if I can find it again. There we go. I just had to reload the link there. There's a comment here that says, great article, blah, blah, blah. And then he says, hey, one little correction. If the, let's see, the first byte is null, being followed by a 7-bit encoded integer, which tells the length in bytes of the next Unicode string, and then another special byte, blah, blah, blah. Here's the important part. If the length of a string exceeds 127 bytes, 2 bytes will be used to encode its length. And so we take this, we subtract 0x8000 from it, and then we read in the length from those 2 bytes. If it is less than 127 bytes, you'll only see 1 length byte here, and that'll just be the length of the string that follows. Why is it done that way? Well, because these are Unicode strings, they're going to have, like I said, null values in here. So we can't just read a string in until we reach a null value, because we'd only read 1 byte and then we'd hit a null value. You'll see, you might see in a lot of other programming languages how you read in a string and it basically the function stops whenever you hit the null value. It doesn't work with Unicode strings because they have null values interspersed within them. So we have to know the length of the string in order to know how much data to read here. And so what that commentator was saying is that if this string is above 127 bytes, which this one is, we're going to see 2 length bytes, not just one. So like this first string, the SHA-256, it's short enough that you see there's only 1 length byte and it's 0D there in hexadecimal, which is a length of, what is that, 10, 11, 12, 13? I should know that off the top of my head, but I don't. I have to count on my fingers like a little child. And then you have the value of the string. So on these long strings, you're going to have 2 length bytes. And this first byte, if the most significant bit of this byte is set, is basically telling us that we're going to have 2 length bytes. What do I mean by that? Let me take out my programming calculator here, and I'll show you exactly what I mean here. I know this seems like another detour, but I promise you this is vital to our parser because we need to know exactly how to parse these strings out of this US stream here. So let's type in ATB1, and that is our 2 length bytes there. Let's look at the representations of these 2 bytes here. In fact, let me just take the AT1 right here. And you can see that in hex, by the way, this is in my second language, which my computer set in, which is Swedish. If you're using, hopefully you're using a calculator in your own language. If you're not, if you're seeing this, you may want to contact the nearest yellow shirted person. That's the IKEA employee. They can help you navigate the Swedish calculator, but yours should say something like programming calculator. If you're using the regular calculator, you just need to go up to the menu, switch over to programming mode, and you'll see these different registers for hex, decimal, octal, and binary here. So what I want to point out is that in the binary representation, hexadecimal 80 has just the most significant bit at the very leftmost bit here set to 1. Why this is important and what this commentator was saying is that we need to, when we have the full value like 80B1, oops, let me try that again, 80B1, we need to first check to see if we're looking at a 2-byte length by checking to see if this value has that most significant bit set. If it does, we need to then subtract 80 and get, oops, wait, what did I do? Oh, I know what I did. 80B1, we need to subtract 8000 to get the true length, which is just B1, or in decimal 177 bytes. Hopefully that makes sense. To recap that one more time, if a string is more than 127 bytes, we're going to see 2 length bytes precede it. The first byte, if the most significant bit is set, and the way we can check that, well, we'll go over it later, but the way we can check that is just doing a quick AND against it like this. And we'll see that it's set. Oops, did I hit equal there? Sorry, I confused myself there and doubted myself, but I was right. Later on, and I'll rehash it when we get there because I know this is a lot of information for right now, starting out, is we're going to take whatever value is in that first length byte, and we're going to AND it, bitwise AND, oops, not add A, but bitwise AND it with 80 in hex. And if it's anything other than 0, we know that this is going to be a 2-byte length value that we need to check. If, for example, the first byte, let's just say it was like this first string here where the length byte is just 0D. If I tried to just AND the hexadecimal D with 80, we get 0 back. So we know that we're only going to be looking at 1 byte for the length there. So this 80 kind of functions as a flag for us, and that's why when we look at both length bytes together, we need to subtract that 8000 from that full 4-byte value because we want to get rid of that flag bit and get the true length, which is 177 or B1 in hexadecimal. So the function, if you see 2 length bytes, the function of that first byte is just to tell us, hey, this is a long string and you should expect 2 length bytes instead of just 1 here. Hopefully that all made sense. Again, sorry for taking the detour, but it's very vital that we understand that about these strings in the US stream here. And we'll come back and rehash all that when we get to actually parsing that in our parser. All right, so that tells us everything we need to know about these strings that we see here. These are the hard-coded strings that are being assigned to these variables here, which are our config values. Here is the kicker here, though. When it comes to the actual config value names, we could assume that these are all going to be the same in every version of ASyncRAT, but actors like to rename these and call them something else, and so these might not actually be called ports and hosts for every single sample. They might be called something else. So it's also vital that we take a look at the address where that field is being populated, and we see that after the 80 here, which, if you remember, let's travel back to our list of instructions. That's the STSFLD instruction. That's followed by the address of that field, which is the ports field. That is stored in a different address space at 04000001. So let's take a look at where that value is stored just by searching for the word ports. This one is going to be a UTF-8 string, and because it doesn't have any null bytes there, we can search for that directly, and we see, if we hover over it, it is indeed located at, in the parentheses there, you see it, 04000001. Awesome. So you might think, oh, the string stream operates kind of like the US stream, where we're going to have a length byte and a null byte. No. It's more complicated than that, thanks to the way the .NET executables are laid out. You'll notice that there are no length bytes here because there's just a terminating, because these are not Unicode strings, these are just null byte terminated strings here. So we don't need to know the length, but you'll notice one other twist in the myth here, and that is that these addresses, unlike, I don't think I actually properly pointed this out, so let's go back to our US stream real quick. You'll notice that if I go to the next string here, it's at position 70000C2, which basically these are all sequential strings. So the first one is located at 0x70000001. That's the very first spot of the US stream, because the US stream starts at 0x70000000, lots of zeros. But in the US stream, all the strings are just one after the other, bum, 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 and the addressing is really kind of easy to understand, because you're just, the first string starts at 0x or offset 1 from the start of the US table, which is 0x70000001. The next one is that offset of the US stream plus whatever length of strings we've read already, and it's kind of logical to go down the stream that way. In the string stream, however, the stream, let's go back. I should just search it here. Let's go back to where ports was defined here. You'll notice that this one is at 0x40000001. And you would think, oh, well, that must mean the string stream starts at 0x40000000, and that the next string will just be, since ports is 5 characters long, so 5 bytes long plus a null byte, you'd think it would be at 0x04000007, because that is 01 plus 6 bytes for this, and the next one should be there. But you'll see that it's actually at 0x0a, something completely random. And the next one is another one that's almost completely random. It's the next one actually in the strings table, or the field table, which is 0x04000002. That doesn't make a lick of sense on the surface. And this all has to do with, again, the anatomy of these .NET executables and how the streams are represented in memory. So like I said, the US stream, kind of straightforward. I'm going up here, by the way, in dnSpy. Let's go up to the top here. If you didn't see this before, you'll notice when you open up your executable, you have this PE block here that you can open up in the Assembly Explorer. And you can actually see that dnSpy is breaking out these different storage streams for you. So we have our metadata storage stream here, and then we have a table stream, and then we have all of these different streams we've been talking about, like strings, and the US stream right here. Now, here's where things get complex with the string stream in particular. If we want to pull out what these different variable names are and present these to our user without assuming that they're going to be the same every time, we need to basically take that address in the strings table, like 0x, what was this one? 04000001. We need to be able to go tell our parser which offset in the file that address lives at. And that is being made complicated by the way the string stream is laid out, because it's kind of randomized everywhere like we saw. The reason it's kind of random, or the way that we can kind of work around that, is because it contains not just those fields, but also all different stuffs, and it's a heap, so all the addresses are kind of all over the place. But the way we can get those fields and where they are in an offset in the file is by taking a look under the storage stream, looking at the table stream, and looking at the field table here. The field table, you'll see, starts at 0x04000001. That's our port string that we saw there. That is the virtual address right there. And unfortunately, we can't just tell our parser, hey, go out and get the value at that virtual address, because it needs an offset of the file. What does that mean for us? Well, we need to take this virtual address, look it up in the field table here, and when we look at this offset value, this is not an offset in the file, but an offset from the start of the strings stream, to make things just even more complicated here. So what we'll need to do to pull out these different values like ports, host, version, install, etc., is read in from our operands in the hex that we saw there what address we're getting the field from, reference this table, this field table here, look up the offset of that from the start of the strings stream, add that to the start of the string stream, which the string stream itself has its own offset from the start of the metadata table, which we'll talk about later, how to calculate all that. But basically, we need to take that offset, add it to the start of the string stream, and then read in the string that's stored at that location to actually get the names of all these different config items. Are you still with me? Do you still actually want to do this?
Are you sure about that?
I know that there's a fire hose of stuff about .NET executables, but we're going to revisit all of this as we go. I just wanted to point out that we're going to have to deal with a lot of major .NET isms and hurdles here to actually do something as simple as just reading in the encrypted value here and what variable name in the config that value corresponds to. It's not going to be as easy as we did in CyberChef and dnSpy, where we can plainly see, the value is this and the variable it's being assigned to is ports. We got to tell our parser how to read our file and how to do all those offset calculations from virtual addresses to offsets to read in this data. Whew, that was a lot. I'm going to take a drink here. Let's regroup and review real quick. All we've done so far is kind of talk through our issue here, which is we need to tell our parser first. In fact, let's go ahead and make some pseudocode here back in our file. It's been a while, I feel like, since we've been in our file here. So let's lay down the steps we have here. Let's start backwards, actually. So the last step we need is present decrypted config to user. Before we do that, well, we need to, I don't need the asterisk, I guess here. We need to first find encrypted values, or I'll say encrypted config values. Those are stored raw in the file. I'm using offsets. And I should say not just values, but also keys, I'll call them as well. So ports, hosts, install being keys, and then those encrypted strings being the values. So we need to find those, identify where those are in the file. So I guess another step is find start of the configuration, initialization, which is just that section where all of those variables are being initialized right here. We need to tell our program how to do that. We need to map the encrypted, or I'll say to get those encrypted config keys, we need to map addresses from the configuration to their string values. And then we need to decrypt the encrypted, and I'll just add encrypted string values, decrypt the encrypted config values and map them to their string. That's a better way of saying this. Map them to their strings, or their, keys. And then present that decrypted config to the user. So I was trying to work backwards a little bit there and walk you through the different steps we're going to have to take to get to our end goal, which is present a decrypted config to our user. And we saw just by looking at the streams and how the .NET executable is laid out that this is going to take some conversion work to tell our parser how to read these values in and how to decrypt them. The decryption part by itself is going to take some work to, in fact, I've kind of oversimplified this bullet. We're going to need to create or recreate the AES decryption algorithm used by the rat, and then use that to decrypt the encrypted config and then present that to the user. Like I said, this is a challenge, and this is going to take some work, but I promise you, if you stick with me, I know it's kind of a brain melt. Take breaks as often as you need to. Pause the video, come back, take some time to read the links if you get confused and need more time to kind of study the .NET assembly and how it's laid out. And when you're ready, we're going to go ahead and move forward with trying to fulfill each one of these bullets in code here. All right, if you're ready to take the plunge with me, let's break these out one by one. I changed the wording here to configuration section because configuration initialization is happening right now. Doesn't roll off the tongue very much. So let's start with our first objective, find the start of this configuration section. What I mean by that is we want to tell our parser how to find, and again, our parser is going to be seeing this binary data here. So we have to tell it, how do we find this configuration section where all of these different configuration variables are initialized with these encrypted strings here. So to review, we looked at the IL instructions here, and they follow a pretty clear pattern. Load string, STS field, load string, STS field. The only deviation here is down here for the value of, which one is it? HWID. We're going to see that actually, oops, I didn't mean to go to the hex editor, but rather the IL instructions. That's going to be a load null, which gets stored in that field. So that's the only one that's going to be a little bit different looking because there's going to be that load null operation done right there. The rest of them, we're going to follow that pattern of LD, STR, STS, FLD. And then at the very end, there's a return, which is, if we go back to our instructions and look up the return opcode, it is, if I can find the right entry here, so I need to search RET. There we go, it was right in front of my face. 0x2a. So let's confirm that just by looking at the section in the hex editor. So really the configuration, actually let's do this. Let's start at the very top. Open up this hex editor. There we go. And let me zoom in just a little bit here so you can see that a little better and clearer if you're on a lower resolution. Hopefully I don't throw off my viewport too much. There we go. So here's our whole configuration section. We have the 7.2, which is that, again, going back to this page, 0x72. That's the load string. And then we should see 4 bytes of an address, and then STS field, 4 bytes of an address, all the way down to our return statement, which again is 0x2a. That's the portion I've highlighted in the hex editor right here. So 7.2, 4 bytes of the US stream address of our encrypted value, followed by 8.0, which is the STS FLD operation, followed by 4 bytes of the strings stream, particularly the field value for our config variable name, like ports. So this first one is ports, and here's ports value. And then that continues over and over again. You see it starts over 7.2, next one, 8.0, next one, all the way down to the end here where we see our return with that 2a operation right there. So we want to tell our parser how to find this snippet of code on disk right here. And one way we can do that is through the magic, just like we did in CyberChef earlier, the magic of regular expressions. Because this is such a unique repeating pattern, we can build a regular expression to look for this 7-2 operation over and over again, however many times there are, at least something like 9 times here. And we can use that as a pattern to look through the data in the file and identify this section here. And then once we get that section, what we're going to want to do is break out all of these addresses so that we can collect what the actual address of the string value is going to be, where the encrypted contents are going to be, as well as the value where we're going to find the name of that config variable. So that is kind of the 2 sub-objectives of this first objective we've laid out for ourselves right here. Find the start of the configuration section. I kind of undersold that one. And retrieve the virtual addresses of the encrypted values, or the config keys and their encrypted values. And then we're going to need to, again, translate or map those addresses to their actual string values. We'll get to that later. Let's focus right now on just finding where that config is in our executable and telling Python how to find it. So let's make another instance variable here called config address map, and we'll set it equal to a function called get config adder map, something like that. So let's go ahead and implement this function down here. We'll just set it right below get file data, get config adder map. I think you can also, I may be lying here, there might be a shortcut you can take to actually implement it or have it write this part for you. I'm sorry, I don't remember it at the moment, but I think VS Code might have an autocomplete there. I'm not going to use it because obviously I just don't remember what it is right now. Again, we want to pass in self so that we can access self.data up here, because that is the data we're going to be reading from in order to find this config data. And so let's pseudocode this out, and I'll give you a chance to try to solve this on your own here. So first thing we're going to do is create a regex pattern to find config initialization section. I hate writing that, but that's the best way I can use to describe that section. When we find the hit, we want to parse out each virtual address of 1, the encrypted value of the config key, and then 2, the name of the config key. So the config key here I'm talking about is, like, for example, ports or hosts or something like that. And then the encrypted value is, again, from the US stream, what that key is actually going to be set to here. So this would be our encrypted value here, and this would be our config key. That's the verbiage I'll use to kind of refer to these things. So we want the address of this along with the address of this, and we need to parse that out of the hexadecimal there by parsing it from those operations that we saw there. And what else do we need to do? We need to convert those virtual addresses from little endian format to their integer representation. What that means is I want to take something like 0x7000000f, like we saw. Actually, we saw it like this, f00000f. We want to take this and actually convert it to that, because we're going to need that representation in order to tell our Python parser how to find that virtual address. We're going to need this representation, not the little endian representation there. And I think that's about it. We can just store it in a map that looks something like this. So let's say we use our config key address and then config value address. We're basically going to build an object that makes a mapping for each config key that has both the key's address, the key name's address, I should say, and the key value address right there. So that's what we want to strive to do. I'm going to give you a minute to try to see if you can implement this on your own, and then we'll go through and do it together. So let's talk this through together here. Like I said, first we want to make a pattern where we can identify this in our binary data. And the way we're going to do that is, let's again go back and take a look at this. We know that each new config key and value pair, we're going to see this 7-2 operation for the load string operation, followed by 4 bytes for the address of the string to be loaded, followed by a byte of 80, which is the operation for STSFLD, followed by another 4 bytes for that field, and then repeat that for as many items there are in the config. And I think there's around, 18 items. We don't necessarily need to look for it 18 times, but at least, I don't know, we'll say 9 times. If we see this pattern 9 times in a row, we probably know that this is the only spot where that many repetitions of this pattern is going to occur. So my regular expression is just going to be looking for this load string operator, or the operand 7-2 in hex, followed by 9 bytes, which is just the rest of that, including the 2 addresses, which are 4 bytes each, and then the 1 byte for the operation of STS field. Look for that at least 9 times. I'm going to store that regular expression as a constant in this class. So we'll put it up here underneath our inner class here. We'll just call it pattern config start. And I'm going to put a little b here, which means bytes. That's just telling Python I'm looking for bytes here, not necessarily a string, text string. And this may look a little odd if you're not used to regular expression syntax. I'll try to break it down here so that you can understand what I'm looking at. So, like we said, we want to look in the config, which we know starts with 7-2 for that load string operation, followed by 9 bytes, followed by 7-2, followed by 9 bytes over and over again. And I'm saying I want to look for that at least 9 times. And if I find that pattern in my executable file, I know I've found the start of this config initialization section here. So this is what this is saying. This \x here just means I'm using hexadecimal representation, which is hex 7-2 here. The dot means any character. So in our case, any byte value 9 times. I'm putting this in parentheses because I want to look for that pattern of 7-2 in hex followed by 9 bytes up to 9 times or more. All right, so down here, and yes, you'll notice a continuity error. I did change this from ADDR to address map just to be explicit and make it match our variable name here. So yeah, that might have changed since you typed that in. But what I'm going to do is first, as usual, we're going to make a logger debug message here, and we're just going to say I am working on extracting the config address map at this point. That'll just tell our user what we're doing at this point in time once we reach the spot. And then we want to go ahead and make a config mappings object that's going to hold this kind of pattern of the key name address followed by the config value address. We'll hold that in what's called a tuple, which is just a collection of 2 items. And we'll put that all into a Python list. We'll get to that in just a little bit. First, we need to actually use our regular expression to look through self.data, which again contains our executable file data, and look for a match that matches our config start here. To do that, I need to do a little bit of importing here. Also, I just realized VS Code imported this by itself. Thank you, VS Code, because this is actually, I think, or no, this is not needed actually. I think I typed in exc info in the call to logger.exception here, which it thought I was trying to import that, but I'm not actually. So I'm going to remove that actually. Try to be smart, but it wasn't actually smart. So from RE, which is the regular expression module in Python built in, I'm going to import the search function. And we're going to use that to search for that pattern in our binary data. Now, actually, before we go any further, there's one very important other thing we need to import here, and that is the .all flag from the regular expression library. And I'll tell you why that's important in just a second. We're going to run search, or actually we need to store the results. So we'll say hit equals search, we'll hand it our pattern, self.patternConfigStart. By the way, I'm using self here. You could also use ASyncRAT because this pattern variable is a class variable. It's not linked to a particular object. You could type out ASyncRAT parser.patternConfigStart and it's equivalent, but I'm just going to use self because it's fewer characters here. Self.patternConfigStart. We gave it our pattern. Now we need to give it what we want to search with that pattern, which is self.data. And then we're going to put .all. Why am I using .all here? And what is .all anyway? .all is a flag in the regular expression module, which basically says that this dot that we're using in our pattern here can represent not just characters like A through Z or 0 through 9, but also it can represent space characters or new lines or stuff like that. The reason we're using .all here is because if we don't, and because we're looking at byte data, binary data here, we may have a byte that happens to be the byte character for like a new line. And by default, regular expressions do not include new lines as characters that can be matched with the dot symbol here. So if I come across a byte sequence for new line, I can't remember what it is at the top of my head. Let's just look it up. New line, hex representation. 0x0a. So if I have any byte in my executable here that is 0x0a or hex 0a here, if I don't include .all and I come across that in a pattern, it's not going to match. Since we're looking at binary data and not text data, we want to include .all to make sure that our patterns are going to match regardless of if we come across what happens to be the character code for a new line. So that's a very important differentiation when you're working with binary data, that you want to make sure you use that, or else if you do just happen to come across the byte sequence of 0a in your search here, it may fail if you don't have that specified. Hopefully that makes sense. And so once we get what's going to be returned here is a match object if the pattern is found. If the pattern is not found, it's going to just be the value, the type none. So we check if hit is none. Let's go ahead and raise a custom exception here and say could not find start of the config or something like that. And that raising that exception is going to halt the execution for this file, and it's going to just go back up, and our runner program is going to move on to the next file at that point, because that means something has happened. The file has been manipulated or obfuscated enough that we're not going to be able to extract the configuration automatically there. If it's not none, though, we can go ahead and continue, and we can say that the config start, the offset of the start of the configuration, is going to be wherever this pattern, this match was found. So in our case, we should find it in this sample at, what offset is this? If this is 0A, C0, this is C1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, which is going to be A, B, C. I'm doing it again. D. I could just honestly right click here and you can actually copy the offset. I should have just done that. And if I paste that into a file here, I can see that it was C actually, 0A, C, C. My counting was off there. That's why we have the right click copy offset there. So when we find that pattern, like I said, we want to look for where it starts. It's going to start right here, and we should get back the hexadecimal value 0xACC, or in decimal, we should get back 2764. So let's just test our program up to that point. Let's do config start equals hit.start, and let's print that value, or actually let's do a debug to stay consistent here, logger debug. Let's do, should we just keep a message? We'll save that for the end, but we'll just do logger debug config start, or let's make this a string. Let's do found config start at, and we'll probably delete this and replace it with a different debug string in just a little bit, but that's fine. And let's just stop there before we do any kind of mappings or anything. And let's just make sure that that's running. To do that, We just have to make sure this is all set up in the initializer. So yeah, everything should work fine. We do, however, need to run this against an actual file this time. So what I'm going to do is I'm going to open up another virtual machine I have, which has the sample loaded in it. Again, I just want to keep the samples off of my host machine. So I'm going to load up a second VM here, and we're going to load in our config parser and then test it within the VM using Python. One moment. All right, we are back. I've got my VM up. I've pasted in the code we've written so far, and I've copied over our async client executable into this VM so we can run it against there. I did notice too that I had a typo. You probably saw it too. If you know regular expressions, is that I put the period in my curly braces. I want this outside of the curly braces, or maybe I just fat fingered that at some point, but should be outside of the curly braces to make sure that that pattern works. Let's go ahead and run our parser against it. We need to make sure we put in the TACD to make sure we get our debug logging here. And we can see we found the config start at 2764, which is exactly where we expected to find it. So we have successfully taught our parser how to identify the start of the section. The next bit is just to get it to parse out the different addresses in between each of these instructions. So how are we going to go about that? Well, let's talk about that. First, I'm going to take out this debug message now. We will put a different debugger message there later. So we have the start of our config map here, but we didn't specify where it ends. If you remember, it ends with a return statement after all of these statements are completed. So if I go here and look at the hex editor again, you see we have that 2a, that's our return statement, and then we go into some other data or instructions right after that. So what we want to do is read everything from the start of the config up to that return statement. And what I'm going to do for this, you probably wouldn't have done it this way if you're implementing this yourself, but because we'll be reading strings from our file over and over again, I'm actually going to make a function that will read a string from a location up to a delimiter. And I'm just going to call it something like get string from offset. And so we're going to need to pass in self as usual. We're going to need where the string is starting. And then we're going to need our delimiter. And by default, let's go ahead and make the delimiter by default just the null byte, because a lot of strings we're going to be looking at are going to be null terminated, which in hex is just going to be 00. This is just notation for null byte. And that'll be our default delimiter, but we can also pass in a value for this. And for our example, that value is going to be the return, the opcode for return, which is in hex 2a. And what this function is going to do is just going to be a little helper function. We're going to try to read a string from that location doing something like result equals self.data, start at string offset, read everything from string offset to the end of the file, but partition that data by whatever we say the delimiter is, and then get whatever the first part of that partition is. What is partition? What is that all about? Let's talk about that real quick before we go any further, because that's kind of important to this whole thing working. I'm just going to run a Python shell here to demonstrate this. So let's make a string called s, and we'll just say it's abcd1 efgh. If I partition s, the string, by the number 1, or the character, I should say 1. Oops, I don't know what I did there. Partition 1. Oops, and I need to make sure I call it a character. It's going to split my string up by wherever it first encounters 1. And so I'm going to take everything that occurs before that character by simply taking the 0th element of whatever partition returns. So I get ABCD, everything that happens before the 1. In our case, we're going to pass in the return code, and we're going to get all the data from the start of the config up to the point where we encounter that return value. So that's just a little Python shortcut to cut the data down to just the data we want to look at here. And if that doesn't work for some reason, exception as E, we're going to raise a custom exception here. And we'll say could not extract string value from offset, and we want to make sure we print the hex representation of the offset to make it easier here. So I'm going to pass the offset to hex. That's just going to return the hex representation like you can see in the hint there. And we'll say with chosen delimiter and show them which delimiter we passed in there. Did I spell that wrong? What did I do wrong here? Why are you curly bracing that? Yeah, I did spell it wrong. It's an I there. And then we're going to raise that from E. We're going to do exception chaining to show what went wrong there. And if we don't get an exception, oops, from E, and if we don't get an exception, we're just going to return whatever result is. So, like I said, we're going to default to a null byte, but in this case, we actually don't want to stop when we encounter a null byte. We want to stop when we encounter a return symbol here. So how we want to write this in our get config address map function is we'll just call it parsed ops equals self.getString from offset. We're going to start our config start. We're going to go until we get to the return symbol. So we could write it like this in byte format, but I'm actually going to make a constant here because we may refer to that return code later. So we'll just call this opcode return, and we'll set that equal to 2a in hex, just like that. And it's a byte string. So instead of that, we'll say self.opcode return. And so this should return us just the block up to the return statement after our configuration here. And I've lost myself here, but I think it's this one right here. That is the end of our config, or maybe this one. Either way, we're going to read the config up to there so that we can get just the block with all those instructions with all the addresses that we want to get out of here. So once we get that, we then need to parse out all of those different virtual addresses, those relative virtual addresses that have the addresses in the string stream and the US stream of our config key values and our config key, our config key names and our config key values here. The way we're going to do that is using another regular expression object here. And the way we're going to do it is, let's go ahead and make this a constant as well. Pattern, parsed RVAs, again, a byte string. We're going to look for that opcode for load string again, but this time we're going to do a capture group, which is just parentheses, and we're going to capture the 4 bytes after that opcode for load string. So that'll get us the address in the US the US stream for our config key value, followed by hex 80, which was our opcode for STSFLD, and the 4, I need to make sure I do this, don't make the same mistake I made last time, the 4 bytes there, which are going to be the little endian representation of the string stream where our config key name is going to be stored. And so what we can do is, oh my goodness, I've been doing a bunch of incorrect or VS Code is trying to be smart and import all those things that I don't need. We're going to also import findAll from regex, which is going to return, if we find this pattern, it's going to return the values that are within parentheses here. So what this is going to look like in our config address map function is something like this. Parsed RVAs equals findAll self.pattern parsed RVAs. In our parsed ops data, again, include .all to make sure we're hitting any byte, not just, or we're hitting every byte and not excluding new line bytes, I should say. So findAll is going to return a list of values that, again, were captured in these groups here in parentheses. So basically, this is going to be the little endian representation of our different addresses there. And so let's just take a look. We'll use the debug string to make sure that this is all kind of what we want here. So for, we'll say US RVA and string RVA, the 2 different streams we're looking at in parsed RVAs. Let's just do a logger debug US RVA, string RVA first, and we'll stop there. Hey, it's Jeff from the future here. I had to cut because I realized this is going to cause an exception. I'm not printing, I'm logging a debug message, so I actually need to throw these variables into a string here. So let's use a formatted string to do something like this and show the values that we are parsing, out of the table right there. So let's try that and try running it again. You can see I was trying to debug that real quick. There we go. So now we can see the byte representation of the addresses we're reading. Now you'll notice that some of these are actually translated to characters by Python automatically. So this P is showing up there because we're reading the byte. If we go back to CyberChef, actually, we can see this in action. If I type in just the P, I always keep going to the non-live page. I want the live page here. There we go. If I type in P and convert it to hex, that is hex code 70, which is what we expect to see there. But basically, when Python renders this message in the debug logger, it's actually formatting that so that the byte becomes an ASCII character there. So if you're confused about why P and certain random characters might show up here, it's because we're seeing that hex representation of 70 converted to a character. But if we look at these addresses, these are exactly what we expect to see. The first one was 70000000F. Again, this is in little endian. And then the key name was stored at 04000001, 2, 3, etc., etc. And so you can see we're building up this map of a config key name and a config key value here. This is the address in the US stream. This is the address in the strings stream there. So everything seems to be working as we intend so far, at least. All right, so back here, let's get rid of this debugging statement. And like I said, we want to convert these virtual addresses from little endian format to their integer representation because we're going to be doing some math with them. So we need not a byte string that's in little endian format, but an integer. And to do this, I'm going to define another little helper function here called bytes. We'll call it bytes to int, and we'll pass in self, and then a byte array or byte string, I should say, and then an ordering. And by default, we'll say the ordering will be little endian, but we can change that by passing in a different value for order here. And all we're going to do is try to convert a byte string to an integer. And you can do that in Python by calling int.fromBytes and the byte string, and then specify the byte order. And we're just going to pass in whatever order was passed in by the user there. And if this goes wrong, we're going to say accept exception as E, raise a custom error again. Oh, my autocomplete is failing me. Let's try that again. Oh, it's because let's do this. It's because I haven't completed my thought up there, so it was struggling there. And we'll say error parsing integer from value, and then show it the byte string from E. And if we don't get an exception, we'll just return result. So what that's going to do for us is now, back in our get config address map, we're going to get a representation of the config value RVA by calling self.bytes to int and passing in the US RVA. And remember that we specified that by default, if we don't pass in an order, it'll default to little, so we can just not pass in an ordering because we want it to convert from little endian. We do the same thing with the config name RVA, self.bytes to int, string RVA, and we're going to do a little debug line here to say we found config item, and then we'll pass in the hex representation. This hex function, by the way, you can see it in the tooltip there, just again presents it as a nice 0x whatever instead of a raw integer value there. Config value RVA, and then, oops, need to close my curly braces there. Hex config name RVA, and we'll leave it at that. And so once we get that tuple, that two object list, basically is what a tuple is there, a collection of two or more objects really, we will put that into config mappings by calling append, and we'll pass in those two values, if I can spell them. And then at the very end here, we'll put another logging message that says, after the for loop is done, successfully extracted config address map. And we will return that map to our caller. Boom. Let's go ahead and check this in our VM to make sure our code is behaving as we expect. And we should now see, with the addition of that bytes to end function, instead of seeing the little endian, we are now seeing nice hexadecimal representation of those addresses, except I messed up my debugger statement. I think I missed a parentheses. Yep, I did. Meant to put another parentheses right there. So we'll just fix that real quick. But you get the idea. We're listing out the different addresses that we found there. Really cool. All right, we got through our first objective here. We now have a mapping of the addresses where we can find the config key names and the config values. Now comes the next part, is we need to map those addresses to their actual names, the strings that are hard-coded in the binary. And to do that, we need to do some conversions from the virtual addresses in those streams to their actual file offset on disk. And we'll do that next. All right, so we already talked about mapping the US RVAs to the US stream is pretty straightforward because it's kind of almost a one-to-one mapping. If we go back to our executable here and look at how those strings are represented in the US stream, again, let's go to the hex editor and just search for this one in Unicode, I should say. They start at 70000000. That's where the US stream starts, and then they go in order. So that one's not going to be too bad. The string stream, on the other hand, where stuff like the names of the different config keys are, like ports, is going to be trickier because, as we talked about, this is kind of a heap of all these different items, and the ones that we're looking for are all in this field table, which is located here. So what we want our parser to do is actually extract this field table, which is going to then serve as kind of a lookup table for us. We're going to take in, so let's say we have now, as we saw, the 0x40000001 address. We can then use this table map to say, okay, I have token 0x04000001. What is the offset from the start of the string stream, which is something that we can calculate in Python. Add that offset to the start of the string stream and then parse the value that is there, which is the string ports. It sounds simple enough. I mean, it's harder than parsing the US stream, but it gets complicated because the fields table is just one table that can be present here. We have to count for, when we're trying to parse out this fields table, we have to first start at the top of the storage stream, which luckily is marked with a nice flag value here, this signature, which will be the same for every sample you look at. We just have to look for that, and we know that we're at the start of the storage stream here. But then we have to iterate past all this other metadata that's in the storage stream. First, we have to iterate past all these bytes here, and then here is the trickiest part. We have to iterate past all the tables that come before the fields table in order to get there. And we don't know for each sample how many rows each of these tables is going to have, or even whether a table is present or missing. At least not right away, we're going to know that. To determine that in our parser, we actually need to take a look at a special value here called m_maskValid. In dnSpy, I'll refer to it as maskValid. And in dnSpy, it kind of lays this out in a nice GUI format, but this is telling us, this mask here is telling us which tables are present in this assembly. And you can see that the module table is present because that's checked. The type ref is, the type def is. The field pointer table is not present here, and you can see that over here in the Assembly Explorer. That's not present, so then we go straight to the field table. These numbers, by the way, are how many rows are in each of those tables. So each of those tables has a different number of rows, and each row is a different size depending on which table you're in.
So this is where the math gets complicated because we first have to calculate, okay, first of all, which tables are present in my current executable. Then we have to calculate, okay, how many rows are in each table, which that is stored here in the table stream down here. You can see it has number of rows for the first table, number of rows for the second table that's present, for the third, for the fourth. Then we need to skip past all of those tables we don't care about in order to get to the field table. So we're going to need a lot of ammo here. We're going to need to create some custom functions to kind of help us get that fields table out so we can start doing these address conversions. So there's a lot of upfront work we have to do here. Before we get to the code, actually, I want to talk about that mask valid value up here. So what is that mask valid value? What is this weird hex value that they have here? Well, let's take that, plug it into our calculator here, our programming calculator, or not. The clipboard might be broken or something. FA29F57. The way this mask works is each table that could be present in this .NET assembly, you can see there's a lot of them, gets its own bit in this mask. So this long mask is, how many is this? Something like 1, 2, 3, 4, 5, almost 6 bytes long. I count that right? 1, 2, 3, 4, 5, 6. Yeah, there's another 4 bits that are missing here because they're all set to 0. So all of these bits are set depending on which tables are present. What I mean by that is we have to read right to left here, and we'll read, let me rephrase that. When we read right to left here, and when we read top to bottom here, it's the same representation. So this rightmost bit represents if the module table is present. So if that's 1, then that table is present. So that is 1, so module is present. Type ref is 1, so that's present. Type def is 1, so that's present. Field pointer is not checked here, and that's because that's set to 0 based on the value in this mask. So what we need to do is check the mask to determine which tables are present, and then we need to check within the table stream to parse out all of the number of rows here. And this is all in the, if we open this up in the hex editor, it doesn't look pretty. Let me see if I can open it up here like this. It doesn't look pretty, but this is what our parser is going to see. So we need to tell it how to parse out these number of rows. So each value containing the number of rows is 4 bytes long. And you can see how that's represented. So yeah, you can see this is going to be kind of a pain to do, but I promise we'll get through it working together. So let's make a helper function here to get our table map first. So this is actually just getting a map of the tables that are present in the executable. And we'll again make a function called get table map here. And let's go ahead and implement that below. All right, so we'll just put this right underneath get config address map function. We'll say get table map. And this table map is just going to tell us which tables are present in this executable and give us the calculations we need to skip over all the irrelevant data so we can get to the fields table in the next step. So the first thing we're going to need to do, well, first I'm going to make a little logger message here that says extracting table map. You don't need to do that if you don't want to. I'm going to, and then we need to do some pseudocode here so that if you want to try to do this on your own, you can play along. So first we need to extract the mask valid value from the portable executable. Then we need to get the start of the storage stream, and we'll use that as the offset to work off of in order to get down to our field table. So the storage stream starts with this magic value right here, remember that. And then we're going to start adding, skipping past all the bytes past that offset, get the mask valid value, and then calculate how many more bytes we need to skip based on how many tables are present and how many rows they have. So to do that, let's say get start of storage stream and calculate offset to tables stream. Then we'll say for each table in the executable, calculate or extract number of rows and calculate how many bytes of data to skip over to get to field table there. And actually, we don't even need to calculate how many bytes to skip. Let's just extract the number of rows and size of each row here. We don't even need to worry about getting to the fields map until the next function that we're going to write. So if you're daring enough to take this on your own, I recommend you pause the video right here and take a stab at it. All right, so let's take a stab at this. We're going to first retrieve the mask valid value. And to do that, I'm actually going to write a helper function. Let's do mask valid equals self.get mask valid, and we'll just write that right underneath here. The reason is that this is going to be kind of an involved set of operations in themselves, so we'll just separate that functionality out into its own function. And so we'll make another logger debug message here, extracting m mask valid, stealing the syntax from dnSpy. I'm just going to call it m mask valid value. Too many periods there. And the first thing we need to do is find that value, which we will need to first find the start of the storage stream, which again, we just need to look for where this signature is, and then skip over all this stuff until we get to the table stream and get to this value here. So this is at offset 3C70. The storage stream starts at 3BFC. So there's quite a lot of bytes we need to skip over there. So the first thing we need to do is just identify where the storage stream starts. And to do that, I am actually going to write another custom little function here to help out getting those offsets, because we're also going to do this with the strings stream and the US stream. We're going to need to find where they start. So I'm going to make a new function called getStreamStart. And we'll pass in a representation of the stream we want to get, which is just that for the storage stream, it's just that hash tilde. For the US stream, it'll be hash US. For the string stream, it'll be hash strings here like that. Hash tilde is what we want. In fact, I'm going to go ahead and make some constants here. We'll just call these stream identifier, I spell it right, storage equals byte. Looks like this. Stream identifier strings equals byte hashtag strings. And lastly, stream identifier US equals byte hashtag US, just like that. And we'll be using these later on, but for now we'll focus on the stream identifier storage, and we'll pass that to our soon to be written function getStreamStart, like so. Stream identifier storage. So to calculate the start of these streams, we need to go back here. Like I said, the storage signature starts here. This is kind of showing the start of the metadata section. And then if you look beneath that in the storage header, you'll see some flags, and then the storage stream begins, and you'll see this offset here in the data where the storage stream begins. And same thing for the string stream. They all start with their offset in the file. So that's kind of nice. We need to be able to extract that offset. So first, we need to find the storage stream signature. We need to find where this value begins, skip over these bytes until we get to where the streams are defined, and then we can parse that value. You can see it right here in the hex editor from the first 4 bytes where that identifier is. So here's the storage stream identifier on disk. It's in these bytes right here, where you can see that hash tilde and then 2 null bytes. And then we find that in the file and then go back, what is that, 8 bytes, and we can find the offset. So let's break this down here. Kind of getting into layers of functions here, getStreamStart, self, and then stream identifier. And what we want to do first is find that metadata header offset. Let's go ahead and write a little function for that as well. I know I'm getting function happy here, but it's important to try to break this out as much as we can so that we don't have a bunch of code all in one block at a time. So before we do anything else, let's define that. And what we're going to do here is use regular expressions again. So we'll go up here and define another constant pattern
for that metadata section. So pattern CLR, which is common language runtime metadata start, and we'll look for that pattern, which was, go back up here, 424A5342 in hex. But remember, we got to look for it in little endian format in our data on disk. So we need to reverse that to 42534A, oops, 4A42. That's going to indicate where this storage signature starts here. And once we find that, so let's do similar to what we did before, we'll make a variable here to hold the hit or the regex result here. So self.data.find self.pattern CLR metadata start. Now you'll notice here I'm not actually using, I said regex, but even though we're setting up a pattern here, I'm not actually using regular expressions. I'm using data.find. And the reason I'm doing that is regular expressions, I should use that module when I have capture groups or maybe wildcards here. But since we're not looking for like random characters, since we're looking for a very discrete string, we can just use data.find to find this byte string. And I think it works actually a little bit more efficiently than regular expressions because we're using it that way and we're not trying to find any wildcards this way. So let's go back here. If hit in this case equals -1, because unlike the regular expression module, this is not going to return none. This is going to return -1 if it doesn't find it. Otherwise, it's going to return the offset where it does find that pattern. If it returns -1, we need to raise an error here and say could not find start of CLR metadata header. Otherwise, we're going to return hit, which is going to be the offset of that pattern. So now that we have that mini function written there, we can now go back here and we're going to say hit equals self.data.find stream identifier. And what that means is we're just looking for that hash tilde in this case for the storage stream, or hash strings or hash US in the data. And we're going to use our patterns that look like this to look for those bytes in the file. And again, if it's -1, we're going to say raise self.ASyncRAT parser error could not find offset of stream, and then show them the stream identifier. All right, and then stream offset. If this is successful, then we want to get the offset equals the bytes to int of, remember, it was back here in the hex editor. If I look at where this is, when we find the stream identifier, so this hash tilde, for example, we want to go back past these 8 bytes here, and we want to read from the start of that stream identifier -8 to the start of that stream identifier -4. So 4 bytes right here. So let's type that out as such, self.data stream offset, or what did I call it? Hit -8 through hit -4 to get the bytes at that location. And then we want to convert those bytes. So like here again, we're looking at little endian format. So this is 6C0000, which is just 6C, which means the offset is at 0x6C in the file. And that's going to be the integer that we want to parse out of those bytes there. So we're just going to pass that to bytes to int to get the integer representation, and then return the metadata header offset plus stream offset. Why the metadata header offset? I didn't make this very clear when I was first talking about it, but that stream offset is not from the start of the file. It is from the start of that metadata header, this signature right here. So if we look here, we can confirm that by looking at the offset 6C. So that stands at, or the storage stream should start at, let's see, 3BFC plus 6C, 3C, 6, 8 is where it should start. And if we go down here, we sure enough see that the first thing in the storage stream, which is the table stream, starts at 3C68, the offset in the file. So that offset is not from the start of the file again, it is from the start of the metadata header that we pulled out there. That's why we needed to gather that first. All right, with get stream start defined, we can now get back to our further layer, our outer layer here, the get mask valid function. And let's go ahead, now that we have the storage stream offset, we know that the mask valid is going to be an offset that is equal to storage stream offset plus how many bytes? Let's see. So mask valid is 3C70, which is, it's easy math, but I'm going to use the calculator anyway. It's just 8 bytes ahead of the start of the storage stream. So we're going 8 bytes ahead of here to the mask valid key here. Plus 8. And then again, we want to convert those bytes when we parse the mask valid, which is 8 bytes in length in total. We want to convert that to an integer. So we're going to say self.data from the mask valid offset to mask valid offset plus 8. So we're reading from 3C70 to 3C78 basically, which is the start of the next piece of data here. And that will get us the integer value of the mask valid so that we can start looking at that and seeing if, or seeing which tables are present based on that mask. So last thing we need to do is just debug and say, hey, we extracted the following M mask valid value, and we'll give the hex representation of that value here. And we'll check all this in just a moment once we finish our get table map function. So once we get the mask valid, we are finally starting to be in business for getting the rest of our table map here. Now, we're going to cheat a little bit, and if you're working on your own implementation, you probably didn't do this. If you did, kudos to you for doing your research. But like I said, we need to know not only from the mask valid table which tables are present and how many numbers of rows there are for each table, which we can get from right here, but we need to know how big is each table row in each of these tables, and it varies depending on what table you're looking at. You can see some have more columns than others. So how do we figure that out? We could be painstaking and look through each of these, but we don't have all of them present here, so we wouldn't know. The easier answer is just to go look it up online on the internet, where it's documented in several places. So I actually found this in some random blogs. Some people have remarked what each row size is. You can also look at the dnSpy source code and the .NET table sizes C# file here, and you'll see the calculations for calculating these row sizes. They can get kind of tricky for each table in here. So I would recommend that you just steal right from me in this case. I went ahead and made a replication of the tables and their sizes, and I'm going to put it in a Python dictionary. I'll show you what that looks like here. Copy it over from my project. And we're just going to store this as a constant up here called table map, or map table, I should say. And what I've done here is I've initialized some values here for each table that could be present in the assembly. I've just added a row size element for every table up through FieldRVA. Why up through FieldRVA? We'll see later on that this, for our parser, is actually the last table that we need. We don't need anything down here, and honestly, the math for calculating these tables row sizes gets more and more complex for some of these tables. So I just omitted them because our parser doesn't need it, and it's kind of more work than is needed on our part for this parser. I just got the row sizes for the ones that we needed, and we'll store those in this map table object, and then we'll create a copy of this and populate it with how many rows we find for our particular executable. But this is already initialized with how many, or the size of each row in bytes for each one. So each row in the module table, for example, is 10 bytes. Each one in the type ref is 6 bytes, etc., etc. So let's go back down to our function here, and let's create a copy of that map for use in our particular instance of our parser. Why are we making a copy like this? I'll explain. Because going back to what we said, oops, I missed an assignment there. Going back to what we talked about at the very start of all this, when we talked about class versus instance variables, if we were to make modifications and store the number of rows in this particular variable called map table directly, we would change that for every single instance of our parser class, and we don't want to do that. So what we do is we take a copy of that dictionary, and we do so by using the .copy operator. So we're not just taking the dictionary itself and changing that. So now we have a copy of the table map. What we want to do is populate it with how many rows are actually present in our current executable. To do that, we first need to calculate the start of the table row section, which is in the table stream. Once you get past all this data here, we get to how many rows are in each table here. So let's talk about the math there. First, we need to find the start of the storage stream offset, or the storage stream again. So we store that in storage stream offset equals self.get string or start. Yeah, there we go. And we'll use self.pattern, or not pattern, stream identifier storage to get the start of there. Then we need to find the start of the table section, the table stream, and that is going to be at 3C68, or I'm sorry, we want to get the start of this part here, 3C80, which is the start of the table rows from 3C68. So let's do that math real quick. That's going to be 18 in hex or 24 bytes in decimal. So we need to take that, and to get to the table start where the rows are going to be, we need to add 24 bytes to get to where the rows are going to be. And then we're going to iterate through each of these fields here that show these different number of rows in each table. And we need to check to make sure that a table is present before we're checking how many rows might be in that table. If it's not present, which we're going to check the mask valid value to check if it's present. If it's not present, we don't need to worry about it. It's going to have 0 rows, so we don't need to factor that into our calculations for getting to the field table. So the math gets a little complex here, but see if you can follow along. For table in table map, which again is our copy of this guy up here. So we're going to iterate through here for each table that could be present. And you'll notice that these are all in order in our map here. So module is the first one, type ref, type def. That is purposeful, I should say, because now we can use the index of each of these table names in our map here. So modules index is 0, type ref is 1. We can use that to check against the mask valid value. So again, if you remember, our mask valid was A0, let me see if I can retype it here, A093FA29F57. We can AND that again with 2 to the index of whatever table. So 2 to the 0 is the ones place. So that's this guy right here. 2 to the 1. So type ref is index 1 in our table, or yeah, our table map here. 2 to the first power is this pot right here. And so if we AND our mask with 2 to whatever index that table is in our table map, we should be able to see whether or not that equates to 0. If it does, that means the table's not present. If it is 1, then we'll see like this. Sorry, didn't mean to AND 1 there. We wanted to AND 0 there. AND 1, 2 to the 0 is 1. We see that that's 1, which means that the module table is present. If we do that AND 2, we see that type ref table is present. If we do that AND 4, which is 2 to the second power, we see that the type def table is present, etc., etc. So to code that out, what that's going to look like is for each table in our table map, we're going to see if mask valid and bitwise AND, which is just the ampersand sign, and 2 to the power in Python is just 2 asterisks. That's the exponent operator. And we're going to do a little bit of manipulation here to get the index of our current table. So the manipulation I'm doing here is taking the keys from the table map dictionary, which are just the names of the tables themselves. And then for whatever particular table name we're on right now, we're going to find the index. So for the module table name, for example, that's going to be at index 0. We're going to take that, look for it in the list of keys, and find out which index it is. And for that one, it's going to be 0. We're going to raise that to we're going to raise 2 to that power, compare it with the mask valid, and we're going to do that for all the table names in our table map. Next, we need to then find the row count. And to do that, we actually need to get our current offset. So let's start the current offset at table start, and we'll increment that as we iterate through each of these row counts. So right now, if we go back to the visual representation, we are starting right here. And if this table is present, we want to get that row count right there. If you remember in the hex view, those row counts are actually 4 bytes in length. So we need to parse the integer from those using bytes to int, just like so. First, let's get the row count in byte format by going to self.data at our current offset and current offset +4. That'll get us the current row count in little endian format, and then we'll convert that using bytes to int row count packed, just like that. And then we'll say that in our table map, and again, this is our personal copy for this instance, for this particular table we're looking at, we'll create a new value called number of rows, or numRows, and we'll set that to row count right here. And then we'll make a little debug message to say found row count rows for table. And we'll increase our current offset by 4 bytes to skip over the one we just read and get to the next row count there. Ooh-wee, that was a lot. So if the table is not found, if that first condition in our if statement is false, we just want to set table map table numRows to 0. And that'll make sure we can skip over those. And of course, if anything goes wrong, we want to catch that exception as E, raise a custom exception here saying could not get counts from tables, chain the exception here. And then if everything goes well, we wanted to log a debug message successfully. Oops, let's try that again. Extracted table map. Woo, that was a doozy, huh? If you're still here, I commend you. We made that work, and now we're going to test it to make sure that everything is working as we expect. And then I'll probably cut away for a minute because I need to get some sleep after all of that. But first, let's check our current code to make sure it's working, and I'll be able to sleep well knowing that we've done everything right up to this point. So let's copy this in here. Oops, I've got my terminal blown up there. We'll clear out our window, and let's go ahead and run this on our file again. Look at that. Oh, it's so beautiful. So our config address map is working just fine. We've extracted that. We already knew that was working fine, but we've added our parentheses there, so that's working. Our debug messages is working. We successfully extracted our mask valid value. And look at this. If we do a one-to-one comparison here, makes me so happy after all that work. Right. Oh, you know what? We spent so much time on that my VM shut down again. Let me pull it up here. All right, there we go. Got it all pulled back up. And we can see we've got a nice one-to-one matching with exactly what dnSpy found for each row count right there. We've skipped over all the tables that aren't present because we used the mask valid correctly. It's just a beautiful sight to see.
So now all that work was done just so we could get a mapping of which tables are present, how many rows they have, and what size those rows are, because the next thing we're going to do is iterate through each of these tables, skip over the ones we don't care about until we get to the field map here. Then we're going to extract this field map. Oh, my VM's going to blink real quick. Try again. There we go. Then we're going to steal this field map, and we're going to use this to look up the values in the addresses that we took away from our config, and that's going to map to the config key names. So much work just to get the key names, not even the decrypted values, just to get the names of the configuration keys here. But it will be worth it in the end, I promise. I will see you all in a quick cut for you, but I am going to go sleep, and tomorrow we'll pick back up with getting the field map. Congratulations on making it this far and sticking with it. I hope everything is making sense for you so far. And through the magic of editing, we are back right where we left off after implementing our get table map function. So let's very quickly, 10 seconds, recap why we're doing this. So far we've completed our first objective, which is to find the start of the configuration in our ASyncRAT payload and get the addresses, the relative virtual addresses at least, of our config keys and their values from that mapping. And now we're working on actually mapping those addresses to their values on disk. But we took a look at the config keys and saw that they are stored in this field table here. And so we created this get table map function in order to be able to tell how many tables are going to precede our field table here and how many rows they have, because the next thing we're going to do in order to start translating the addresses we got from the configuration here is we're going to make a copy of this fields table. And we're basically going to just insert our address here or use that as a query parameter and get back the offset of that value of that field from this name column here. By the way, just a quick note here, it's a little confusing with the naming here. This offset column in this table is not the offset from the string stream start. This is actually the offset just in this metadata section here. It's actually the name column that we're most interested in because this value is the offset from the start of the string stream that we saw earlier. And we have a function now, thanks to the work we did, well, in my world yesterday, but for you just a little bit ago, we have that get stream start function. And so what we're going to end up doing is using that and adding these offsets to get the value of these fields here. If you go down in dnSpy, if you actually open up this fields table and go here, it actually explains it a little better in the notation here that says, hey, even though they call this name, this is the string stream heap offset from the start of that. So this is the value we're interested in. To get there, we had to do a little bit of work to get the table mapping, and now we're going to put that to use because the next step is to actually get a copy of this fields table for our parser. And to do that, we're going to have to, well, let's just pseudocode it out right here. First, let's go ahead and make ourselves another variable right here. We'll call it fields map equals self.get fields map, and we'll go ahead and start implementing this function. Let's just put it right here above get table map. We can always reorganize later, and we want to make sure we send in self. So let's pseudocode this out. To get the fields map, we're going to need to first find the start of the fields table. We'll probably write a helper function for that. And that helper function is going to need to, if we look at how this table stream is laid out here, we're first going to need to find where the table stream begins, or I guess a better way of putting that is where it ends, because we're going to have to skip through all this metadata that we already looked through. Starting at the module table, the first table here, we're going to need to skip over the rows in each of these tables until we reach our fields table here. And then once we get there, so let's get back to our code here so I can start writing this out. So skip to start of fields table. And then once we get there, we need to iterate over all rows in the fields table and capture their, or I should say, use their offset
to get their value in the strings stream. So it sounds simple enough, but it's going to require a little bit of, again, some mathematical work for us to do those calculations, find the start of the fields table, and then iterate over all the rows and capture those values there. So for those of you daring enough to do so, I'm going to give you a minute to just think through this and try to implement it on your own. And then in just a moment, we'll cut back here and we'll implement it together. Hi, it's Jeff from the future. Actually, we're not going to cut yet because I just realized I pretty much wrote the same thing twice here. I wasn't very helpful in my pseudocoding for this helper function. I said find the start of the fields table and then skip to start a fields table. That's pretty redundant. So let's try to put more detail here. So to find the start of the fields table, like we talked about, we need to first find the end of the tables stream here where this ends, this metadata section, and the module table begins. And then we need to skip over all the tables we don't care about using the table map we just got. So let's try to break that out a little more before I cut you loose to try to implement this. So we know that to find end of the table stream metadata, we knew that that was the storage stream offset plus 24 bytes because that's all the number of rows for each table. Or I'm sorry, that was up to this point where we saw the mask valid and then the M sorted, and then right here will be 24 bytes from the start of the storage stream. And then we need to iterate through each of these row size values. So basically for each table that is in our assembly, we need to iterate 4 bytes over. So let's denote that. So storage stream offset plus 24 plus, make a new line here, plus 4 times number of tables present. And I think that'll get us, until we reach the fields table. That's a little bit nicer to see that we need to put a little more effort into this finding the start of the fields table function, this helper function we're going to write here. Then we're going to iterate over all the rows in the fields table, use their offset. I think everything else will stay the same, but I did want to just clear up what that helper function is going to entail rather than just saying, oh yeah, just find the start of the fields table. I believe in you. You probably could have figured it out, but hopefully that helps. Now I'll let you cut away and try to implement that with that extra hint there. All right, so we are back. Let's go ahead and implement our helper function here first. I'm going to call it get table start, and I'll do self. And actually, we also want to pass in the table name that we're looking for. We'll make this generic so that we can find any table with this, even though for right now, we're only going to use it to find the start of the fields table. So just like we pseudocoded above here, we want to find the start of the storage stream again. And we know how to do that now because we've just done that in our table mapping function. We're going to use our self get stream. Oh wait, why is it? Oh, I know why it's complaining. I need, again, a pass keyword or something there to make it think that I've done something already. And we'll use self.stream identifier storage. That'll get us the start of our storage stream offset. And then our table start offset, which is where our module table is going to begin right here after we get through all of this row size data here, is going to be equivalent to this equation up here. So we're going to take that storage stream offset, add 24 bytes to skip to where the number of rows begins right here. So that'll bring us right here. And then we need to skip over each of these for each table present in our assembly. And like I said, we already have that in our table map. So all we need to do here is 4 bytes, because each size is 4 bytes for that measurement, plus the length of however many tables are present in our assembly, which we can get from our table map. So the length of each table for every table in our table map, self.tablemap, make sure you include self there, if that table is present. And the way we check that is just saying if table map table, which is the name of the table, if the number of rows there, which we set in our get table map function, is greater than 0. So that will get us all the way past here because we're skipping over 4 bytes for each table that's present, and that'll get us all the way to the bottom of here into the start of our module table. So once we get to the start there, we will then iterate through until we get to the table that we're looking for. So to do that, what we need to do is say, let's just start with table offset equals our current offset here. We're going to use that table offset as kind of an iterator. Need to spell that right, first of all. And then we'll say for each table in our table map, let's first check to make sure if the current table is the one we're looking for. If that's the case, we want to break, and we'll return that later. Otherwise, we need to check to see if we've gone too far. So if row size is not in our current table map for this table, that means that we've actually gone too far than we want to. What do I mean by that? Well, the way we've set up our table map here, if you remember, is we implemented, or I implemented, the row size for each of these different tables up to a certain point, because FieldRVA, which we'll talk about a little later, spoilers, is the last table we'll actually need to use for our parser. So if we get to this entry right here, this entry does not have a row size because I just didn't care to calculate it. So if row size is missing here, that means we've already skipped through all these tables here and we've gone too far. We've gone past the point where we should have found the table we needed. This is very bespoke to our parser. Obviously, if we were creating something that was more generic and we needed to know the row size for all of these, we would basically just check to see if we were on the last table that's valid. But since we're only looking for tables that are at or before the FieldRVA table, I'm just going to use the presence of this key in our dictionary as a sort of flag to tell me, hey, if I reach an entry that doesn't have row size defined, it means we've gone too far and there's probably something wrong with what we're doing. So let's go back down here and we'll just raise an error or an exception if that happens. Invalid table offset found. All right, otherwise, if we haven't found the table we wanted by now, the next thing we need to do is just skip past whatever table we're on right now. And the way to do that, of course, is to just set our new offset to, or add to it, the number of rows, or the size of each row, I should say, times the number of rows that are present. So we have our row size times self.tablemap num rows. So for example, if my iterator is starting at the start of the module table, we know now with our table map that the module table has one row, and we know that it is of size, what is that? 10 bytes. So we skip 10 bytes times 1 to get to the next table, which will be, not that VM, but this one, the typeref table, and that one has 155 rows, each a different size, and so we skip past all those until we get to the table we're looking for. That's what we're doing here. So with that all said, let's go ahead and finish out the case that we found our table, in which case we just want to return table offset, which is going to be the start of our table, assuming we found it right here. So hopefully all that makes sense. Again, we're finding the start of the table section here. We're iterating through the tables until we get to, in this case, we're going to send in the field table. And once we find that, we break from our loop. And wherever the offset is standing at that point in time is the offset in the file where this fields table is starting. So basically this first row right here. And then now that that's written, we can now get back to working on our get fields map. So now we're going to use the data we just collected from get table start to iterate through the fields table now that we know where it starts, and collect all the values we're interested in, which again is just the offset of those values from the string stream, which is stored in this name column right here. Before we get started there, I'll show you what those actually look like in the hex editor so you can see each one of these rows is 6 bytes in length. The first 2 bytes are flags. The next 2 bytes are the ones we want. That's our name value. So in this case, the offset from the string stream is 188A0 bytes away from the string stream start. And then the last 2 bytes are just the signature right here. So it's really these 2 middle bytes that we're going to be extracting for each row here.
So as usual, let's go ahead and start by making a little debug message to say where we're at, extracting fields map. And let's go ahead and make a list similar to what we did with the table map, or the config map actually, is we're going to put a bunch of tuple objects. I think I called it tuple earlier. I also say tuple. I don't know what the recommended pronunciation of that is, and I frankly don't care, but you'll probably hear me go back and forth just so you know. But we're going to make a collection of two objects, and that's going to be the field offset and then the field value. So we're actually going to find the value from that offset by creating another helper function, which we'll talk about in just a moment. But for now, let's focus on just getting through and iterating through the fields table. So first we need to find the start of the fields table, and we'll use our new function for that, get table start, and we'll say, let's go ahead and make a constant here just to keep things clean. We'll say table name or table field, and we'll just set that to field. So now we can just say table field, and then we want to get the start of the string stream, because that's what we're going to use those offsets to add it to the start, and that'll get us to the point where our string value is. So string start, we'll say self.get stream start, and we already made the designation for that. That's just stream identifier strings. So we have those two items, and then we want to start at the start of the fields table. So that's our current offset. Then we need to iterate through each row in the fields table and collect that offset value, and then use that offset to collect the string value from the string stream. So let's do that by doing, we'll just say for x in range self.table map table field. So we're looking at the table map. We're getting the number of rows from that table map for the field table. And so we'll say for each number basically and number of rows, so this is just iterating through the number of rows in that table, we're going to try to extract a field offset. And the way we do that, if you remember again, we're looking for the 2 middle bytes of each of these rows, which are 6 bytes in length in total. Field offset equals, and we need to convert that from little endian to integer, self.data cur offset plus 2, which is going to bring us to, if our current offset is at the start of the row here, we need to skip over the first 2 bytes, which is our flags, to get to here. And then we want to go and read over those 2 bytes. So from current offset plus 2 to current offset plus 4, basically. If I can do an underscore. 4, just like that. And then we're actually going to get the value for that particular field by adding that field offset to the string start. And like I said, we'll use a helper function for that, but we don't need to write one. We actually already have it. We want to use our get string from offset, string start plus field offset. So let's review real quick how this one works here. This function get string from offset. If you remember, we set the delimiter, the default delimiter to be the null byte. And because of that, when we go down to where this is going to appear in our assembly here, remember in the string stream, these are UTF-8 encoded, and so they don't have null bytes in between. They're a string followed by a null byte to indicate the end of the string. So that's why we're using that delimiter of the null byte, because we can basically just start at this offset, read data until we encounter a null byte, and then return that data back as what we want. So that's what we're doing there. And let's get back to our fields map function. So once we have that field offset and the field value, we want to go ahead and increment our cursor by using self.tablemap self.table field. So getting the size of each row and the field table. And of course, as usual, if something goes wrong, we'll go ahead and raise a custom message here that says, we'll say error parsing field table, like that. And then we'll go ahead and also put debug messages here to say, I found this field as we go through and loop through here, and we'll print the offset. Oops, I didn't mean to use a curly brace there. Field offset, and then field value. And that should be just fine. What have I done here that I'm getting squigglied? Like, that does make sense syntactically, I think. Oh, no, it does not. I forgot to actually include my raise right here. That's better. So that debugging message will help us as we iterate through the field table to make sure that we're finding valid values as we go there. So then we, of course, want to actually add that to our fields map. And we'll use field value and then field offset. And then at the end of all this, we'll just make a debug message that says successfully extracted fields map. And then we'll return it. All right, and let's go ahead and test this before we go any further. So the result we're expecting is that we should now have a map after this that basically brings in the offset here, which is this guy right here, and the value of the string located at that offset in the string stream. So we should see ports, host, version, install, blah, 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 all the way through to the end of this fields table. So let's go ahead and check to see if this is working by opening up our Kali VM or wherever you're testing your code here. Let's make this a little smaller, save our new code, and let's go ahead and run. All right, looks like we have an error, and it looks like a simple one. It looks like I just maybe forgot to do something here. So line 243 and get table start. Oh, yep, I see it right there, line 243. I just forgot to include self.tablemap table and then num rows, not just table map num rows. We need to access the table by its name there. So we fixed that. Let's go back to here, update our code, try to run again. Look at that. We see now, we could again do a one-to-one comparison if we wanted to. That, in fact, let's go ahead and do it. Just for gigs here, we'll pull up the field map and we can see that we are now parsing the correct offset right here and the correct string stored at that offset right there. So that is awesome. We now have a successful way to, from our config address mapping that we got earlier, we can now translate these config key values using our field map there. That is pretty cool. Pat yourself on the back, and let's get right back to work and now working on getting the rest of the data we need. All right, so we are still on our second objective here, but we are finally on the last step. So we did all this prep work to get our table map and our fields map, and now we can actually translate our config here, and we'll make a little helper function here, and we'll go ahead and implement this, or at least pseudocode it out, and then I'll give you a chance to go through and do this, and we'll talk over it here. All right, let's go ahead and set that right here, wherever you're most comfortable, and we'll say get translated config, set it up just like the others, self, and let's pseudocode this out. So we're going to first, for each config key name and config key value in our config address map, which we collected, for each config key name, translate the string, or the fields, I guess I should say, FieldRVA to the value of the key in our field map. And then for each config value, we are going to want to use a helper function to get the string from its position in the US stream. And remember, that one's going to be a little bit easier because those are all sequential. So we just need to write a little helper function to actually go to the US stream, find the start of it, which we can already. We have that get stream start function.
and then figure out how that address maps into that stream, and then pick up the string that is located at that location. Now, what we do need to account for, let's go ahead and pseudocode this out so we remember, is check length byte or bytes to see if it is a long string, and check length. And what I mean by checking if it's a long string is seeing if we need 1 or 2 length bytes. And then read Unicode string at that location using the length. Because remember, those are not null terminated per se. They all have null bytes within them. And so we need to use the length to actually read in the value from that string. So once we do that, then we just want to return a translated config where the addresses are now mapped to string values. And this time we're not going to use tuples. We're just going to do something like this, where translated config key equals value. So for example, translated config ports is going to equal whatever that encoded string is. I'll just go ahead and pull it from the machine here. It's got to equal that string. So that's our goal here. This is what we want at the end for each key and value in our config address map that we pulled out there. We need to translate those addresses to their actual string representations, just like this. So take a moment or several moments and see if you are willing to go through and try to implement this on your own. And if not, or if you get stuck, check on back here in just a moment and we'll do it together. All right, so let's take a stab at this. I'm going to start by making our helper function for translating the config key address to its value, the relative virtual address to its value. So we'll call this strings_rva to strings_val. And we're going to pass in self and a strings_rva. And so if you remember, in our config address map here, we're going to have these values, these 0x04 addresses from our config or the settings section where we pulled them from. So our goal here is to translate this relative virtual address into an index that we can index into our fields map and get the value out of here. Well, the cool thing about this is that these are all just sequential. So you got 1, 2, 3, 4, 5, blah, 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 all the way down. So to find our offset in the fields map, we'll just say fields map offset equals the RVA minus the base address for the strings or the field table, which is 0x04000000, and then subtract one more because that address is going to start at 1, but our fields map index starts at 0, if that makes sense. So we need to subtract that 1 off. That'll give us, so for example, if we're looking for the address to ports, that RVA is 0x04000001. So our fields map offset is going to be 0x04000001 minus 0x04000000 minus 1, and that's going to be equal to 0. And so we're going to, the ports value is going to be fields map 0, just like that, because our fields map, again, the ports is the first value in our fields map, so we need to subtract that extra 1 off to get that 1 off the address there. Hopefully that makes sense to you.
Why, hello there, it's Future Jeff, and I had to time travel back here to prevent you from making a mistake that I'm making currently in this video. I must have been super tired when I wrote the strings_rva to strings_val function because I made it super inefficient in the first pass of this video. So I'm coming back here to tell you the correct way to do this. So I'll explain to you why this is inefficient or redundant here. This math all checks out. This is how we get our index in the fields table. But for some reason, I had it in my head that we needed to get the offset from the fields table and then redo that calculation to get that fields value from the string stream. Well, if you remember, we already did this in the get fields map function. We already did this calculation. We pulled every field from the fields map. So we don't need to get the start of the string stream again. Get rid of this. We don't need to get string from offset again because it's all in our fields map object already. If you remember, this fields map has our value and our offset, and for some reason God knows why, I was getting the offset from our fields map table and then adding that to string start and then getting the string at that location, when in reality we already have the value. It's in the fields map already. So we just have to get the 0th element instead, and that is our string val. Or I should say strings val, I guess, to keep consistent. So this is the proper way the function should be written, and this should work just fine. And I'll overwrite the bit of the video where we wrote that function. You may still see it in other snippets of the video, but hopefully this helps. You will see me future Jeff one more time before the video ends to fix another issue when we get to our get AES key function. But everything else, I'll try to put just little hints and tips in the video for when I maybe misspeak or say something that could be easily corrected or will be easily corrected later on. All right, sorry about that. Please continue to enjoy the rest of the video. So that's cool. We got our first way to kind of get the translated address for those config key values. Let's go ahead and write a little bit of our get translated config function now. Again, we're going to run a debug message here. Translating configuration addresses to value. We'll say that. And then we'll say our translated config is going to be a dictionary. And for each US string RVA and strings RVA in our config address map, we'll go through here and try. The field name is going to be self.stringsRVA to stringsval. And we're going to pass in that RVA. And then the next thing is the field value for the config, for this particular config key. And we'll write a helper program called USRVA to USVal for that. And this one's going to be a little bit different than our strings RVA function because the US stream again functions a bit differently as we wrote up here. So let me go ahead and just make a quick little fake dummy except here just so we get our autocorrect will work, and then we'll start making our function USRVA to USVal here. And we need to pass in the USRVA. So to get these strings out of the US stream, if you remember the stream, I'll try to find it on disk or in the hex editor here so you can see. And let's just go to the start here. So it starts right here, and it starts with the at the virtual address 0x700 70000000 blah 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 blah. You get it. It starts there, and then we launch into the first length byte for our first string in this table, and then the string itself, and then a null byte, and then another one. 2 bytes, 2 length bytes for the next long string, and then another null byte, etc., etc. So what we want to do here is first find the start of that US stream, and we're going to use our same get stream start with our stream identifier for the US stream. Then we want to check the length byte, or first we need to find the length byte offset. So the length byte offset is going to be our RVA minus that base of the US table. And we actually haven't defined this yet, so let's go back up and define it just like we did with the strings base here. We'll say RVA US base equals 0x7000 1 2 3 4. Let's go back right here, and we'll say RVA US base, and then we want to add the start of the US table. I didn't mean to open a terminal there. So where does that get us? So that is, for example, let's say our first string is 0x70000001, which it should be, and that is the value for ports. Like we saw, let's go all the way back to when we first parsed the config and looked at these and looked at the values here. That is this guy right here. And sorry, it's not 01, it's actually 0f. It's going to be our ports string value, which is this string right here. So let's say that's our first one. So what we're doing here is finding the length byte by saying, let's do this. Length byte offset equals that address minus the base address for the stream plus the file offset where US starts. And that's going to get us, in this case here, let's go to the hex editor
and go actually find that string to check it in Unicode. That's going to get us right to the start here where these first two length bytes are, because this is actually the offset or the virtual address of 0f, and this is going to be 1 0 and then 1 1 and blah 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 blah, etc., etc. All right. So with that, now that we know where the length byte starts, now we need to start thinking about the differences we talked about when there's one length byte versus two. So if you remember, if there are two length bytes, that leftmost bit is going to be set like this. And so what we need to do is check if that's set and then subtract 80 in hex from here to get our full length. Again, for this example, let's just take a look here. So our total length byte value is going to be 80b1, but that 80 is really just serving as kind of a flag. So we're going to subtract hex 8000, and we get our full length, which is b1 in hex, or 177 bytes in decimal. All right, so with that in mind, let's do it like this. If the integer version of what's at that length byte offset, because remember, if we're referencing something in self.data, it's going to return a byte, so we need to cast that to an integer to compare it. And we bitwise and that with 0x80. That means we're looking at first of all, we're looking at two length bytes and we're looking at a longer string. So let's go ahead and make a val offset here that says 2. And that is just saying that we need to skip over 2 bytes to get to the actual start of the string, 2 length bytes. And the size itself is going to be, let's see, it's going to be the combination of these 2 bytes here, but cast to an integer. Now notice here, this is not in little endian format per se. If we read it in little endian format, we'd actually get the value b180, which is a completely different and very long length here. So we're going to use our bytes to int function, but we need to use big endian so that we read it in just as it says right here as 80b1. So we have to be a little bit more careful here than we were earlier. So we'll say self.bytes to int, self.data length byte offset, and length byte offset plus 2, because we have 2 length bytes. And then we need to pass in our byte order and override the default value of little by passing in just big. And remember that we need to, once we get the integer value of that size, we need to then subtract 0x8000 to get the actual length. So that's if we have 2 length bytes. If we just have 1 length byte, our value, or the value of our string is just going to be 1 byte after. We're just basically going to skip over the 1 length byte. And then the size is just going to be the int value of that length byte offset there. And actually, I just realized a mistake I made here is we actually don't have to cast this to an integer, I don't think, here. I've just realized we only get a byte string back if you reference more than one value from self.data, which is just a byte string. But if you just get a single element like we are right here, I think it actually does return it as an integer. So let's try to run with that assumption, and we'll find out if I'm right or wrong here. So once we have the offset and we know the length of the string, we need to then add to our offset our length byte offset here. So basically what we're doing is we know, let's say we know for the port string, we know that the length byte starts here. We then need to add whatever offset here based on how many length bytes we have. So if we have 2 length bytes, we're going to add 2. If we have 1 length byte, we're going to add 1 here. In this case, we need to add 2 for the port string because remember, it's a longer string. So we're skipping over these 2 bytes and we're starting right here. And then we're going to just read in as many bytes as the length we were given here. So this is just going to be usval equals self.data val offset to val offset plus val size -1 because the length actually includes that terminating null byte. So we're just going to subtract 1 to slice off this null byte at the end there, because that is not part of our actual string value there. And with all that done, all that math done, we can then return our US val, and that should be enough to get our values from that US stream there. So now we can go back to our translated config function, and let's go ahead and clean this up, and we'll add a debugger message here to say I found a config value, and then we'll report the field name equal to field value, and that way we'll read in our debugger output which config values we were able to successfully translate, and then we'll add them to our actual config by setting that name to that value in the dictionary there. And then let's go ahead and clean up our except here. We'll say except exception as E, raise a custom exception if something goes wrong, and say error parsing, or we'll say error translating RVA US RVA, and strings RVA, and then we'll report whatever other error actually caused that to happen. And then if we get through this, we can then put a debug message here that says we successfully translated our configuration. And we really hope we see that. And then we're going to, of course, return our translated config. Woo! A lot of math, a lot of work. Let's see if we're on the money or not by heading over to our test environment here. All right, after a little bit of troubleshooting, it didn't take very long at all to figure out what was wrong here. And you all probably saw it earlier and were screaming at your screens for me to fix these things. First of all, I switched our code around, by the way, to print the hex representation of these in the debug message. So let's go back here and I'll show you what I did there. First of all, I guess before we do that, I'll just show you what I did wrong here. There's two things actually that were wrong. Number one, I accidentally appended another 0 here, so our calculations were off because that value was completely different for our strings base. That was the main problem. The other problem is, real quick, here's where I just added in those hex wrappers around in our exception message. So now we're getting the hex representation of those RVAs when we get an issue. The other problem is right down here, I added the length byte offset right here, but I didn't assign it to anything. So I actually meant to do val offset plus equals there to say that val offset equals itself plus the length byte offset there. So those two things I think were our main issues. Let's see if I'm right here and copy in our new code and try again. And hopefully we get some successful output. And we do, and that is beautiful. I mean, it's not very beautiful to look at right now because what we're actually seeing is the raw byte string here. And that's good for debugging purposes. But because these are Unicode strings and we haven't tried to decode them to like a nice printable format, you're seeing each character followed by the null byte in the value of each of these config strings here. But we can see that we are correctly parsing the name of the config key and the values in Unicode. Now, when we get to the end where we actually report this to the user, we'll put these into a much nicer format where it'll actually render those values to the screen. In fact, actually, I don't know why I'm saying that. We don't even have to worry about that because the user's not going to see the encrypted and encoded value. They're going to see the decrypted and decoded value, but we will have to still translate that from Unicode, but we'll worry about that later. For now, we need to celebrate a little bit that we have a successfully working translation of our configuration. We have taken care of our, our third objective? I guess second, but I mean, we did a lot of work to get to that through that second objective. So that was a great amount of work. Hopefully you're keeping up here. The next thing we need to do, and really the last hard bit of work we need to do, is recreate that AES decryption in our parser here, then decrypt those values, and then present that to the user. This part will be easy. We'll just be rendering strings to the screen at that point. But it is going to take a little bit of upfront work to recreate this AES decryption algorithm in Python for our parser here. The good news is that because we did this in CyberChef at the start of the video, we now know and are familiar with how the AES decryption works. It's just a matter of getting all the metadata we need to get the algorithm to work, just like we did with our CyberChef recipes, and implementing that in Python. So let's get started. We're almost there. We're in the home stretch, guys. Let's finish this out.
All right, so on the path to recreating this AES decryption algorithm, I'm going to take a step here that is once again probably going to ignite a Python holy war. I'm going to create an actual inner class just to work on the AES decryption part of this parser. Now, why is that controversial? Well, you really, in Python, you usually don't need these nested classes so much. They're kind of, in some ways, they're redundant. We could do this without creating a nested class like this. But here's why I'm doing it. I want to try to defend myself here. I think it makes sense to kind of encapsulate all of just the AES related functionality into its own object or class here. Even though we don't have to, I think it helps kind of with the organization of the code. So I'm going to do this. You don't have to do it. But the way I'm going to implement this, you'll see I'm going to use this nested class to do all the AES kind of operations. So for this class, we'll go ahead and make a constructor here. And I'll clean this up a little bit. Let's just go ahead and pseudocode out what we need to do to recreate this algorithm. So first we need to gather metadata about AES implementation, all those things that we looked at in CyberChef. So that includes things like key size, block size, iterations used, the AES salt, and the AES key, which we need to derive with PBK df2. Did I get that right? I did. I can't believe I nailed that the first time. I usually mess that up. So we need to gather that metadata, and then really, I guess I don't need to put this as a sub-block. We're going to write functions for each of these steps here along the way. Some of them will combine together, but this is basically going to be the core functionality of our AES Decryptor inner class here. Is we want to gather all this metadata and then derive the AES key. And then one important part is actually offer a decryption function to our parent parser that can be called to decrypt our config, basically. So offer a decryption function to our parent parser to be called when decrypting a config. Something like that. So that also means we need to pass in our parser object, our outer class here, as an argument here. So we'll say parent parser because we need to be able to access from each one of these inner class instances. We need to be able to access all of the functions and data from our parent parser, which has, self.data, which has all of our file data in it. So again, this is why it's a little controversial to use this nested class, because it does introduce these weird relationships, but I, again, think that it makes sense code-wise just to keep it organized to just do it this way. So let's go ahead and when we instantiate a ASyncRAT AES decryptor, we'll pass in the parser for our particular file as self.parent. And then let's go ahead and make our first function, which is let's find where the metadata is stored in our executable. So we'll say get AES metadata flag. What does that mean? That means we need to find some kind of flag in the file that we can look for so that no matter what ASyncRAT payload we're looking at, we can have a reliable pattern or regular expression we can look for to find the AES data. So what I'm going to look for, what I chose to look for here, is this argument exception hard-coded string right here. Not the string itself really, but if we look at the instructions here, let's go to edit IL instructions. We see that there's a little bit of a unique sequence of instructions here. There's a new object to create that string that's up there, and then to throw an exception here. This is one of the few times that the throw operation is used within the rat payload itself. And then we have, later on right down there, we have where the salt is initialized. And if we look at the instructions there, the added benefit of looking at that is we're going to see
that the salt value is actually stored in this field right here in 0400002C. So we're actually also going to be able, if we find this section here, we'll know, number one, that we're in the AES file where we need to be. We can also parse out the salt value right here and the iterations value, which follows directly after the salt there. So we're going to start by making a flag where we can find this section, and then we'll use that flag to derive these two values right here. And we'll also use it to look for other values like the size of the key and the block size, which is all down here. We're going to have to get a little bit more creative when it comes to that. But let's start by making our function to actually find that AES metadata flag. All right, so let's start defining this here. And you'll notice I didn't give you a minute to do this yourself because I think this part in particular merits actually talking through together and working through together. And the rest of it, after we get the metadata figured out, you can probably implement yourself. But if we're going to go down this path, I think this part really needs to be done in tandem here. So as always, we're going to make a debugging message here, extracting AES metadata flag. Dot. And let's go ahead and try to make a pattern here for finding that section right here that we were talking about. So we saw in the instructions, like I said, I'm going to use these sequence of instructions right here, reading up to where the salt is initialized, because I want to also, while we're here, grab where that salt address is, because later on we can look up that salt value in our table and we can see what the value should be there. So let's go ahead and switch over to the hex editor here. All right, so I'm going to use this section right here. Let me zoom in a little bit so you can see that a little better. So this is the pattern I'm going to be looking for, is this 0x73, which if we go back to our handy dandy CIL instructions, that's the new object command plus 4 bytes for this field right here. We don't really care what those 4 bytes are. We just need to account for their presence there. And then followed by a 0x7a, which is the throw operation. And then followed by 0x03, which is the load arg1 operation. Again, we don't really care about these. We just care about finding where this spot is in our file. But we do care about what comes next, because this next one is a 0x7e, which is the loads LDS FLD, and then the field value there. And that is the instruction. If we go back here, back to settings, AES 256. The VM restarted, by the way. That's why I had to cut out there for a second. If we go here, this is this command right here, which loads in our salt value. And the reason we want to capture that address is because that's going to give us, if we go back here, that's going to give us that 0x04. Oh gosh, where did it land me? I really just wanted to look at, let's start from here. Okay, I'm with you now again. This address right here is going to be our salt value, which if we look in our fields table at what that address is, let's go ahead and do that just to see. We'll see that it is 2C, so that's this guy right here. And we can see that that is indeed where our salt value is in the fields table. Now, why do we want to capture that? I'll explain that in just a little bit. No spoilers yet. For now, just know that we're going to use this flag to find this section right here, and then we'll use this section as kind of a base to get all the rest of the metadata we need, and we'll come back to, we're going to capture that salt address, the RVA there, but we'll come back to that in just a little bit why we're capturing that. So let's go back to our code now, and let's get this AES metadata flag. We got our debug message, and so let's make our pattern. We'll start another series of constants here. We'll say pattern AES metadata equals, and we'll set that to the byte string 0x7e, followed by, again, 4 bytes. So just any 4 bytes, or I need to do it like this. So we don't need to capture because we don't care what 4 bytes they are. Followed by the 7a, that's our throw command. The 03 is our load arg command. And then the 7e is our LDS FLD command. And then a capture group to capture the next 4 bytes, which are going to be our salt RVA here. Capture salt RVA. All right, so now we have our pattern. Let's go back down here. We're going to go ahead and use that pattern to search through our data. And to do that, let's just say metadata flag offset. We're going to use the regex search command, and we're going to pass it our pattern. And remember now that we're not looking at self.data, we're using self.parent.data because we're now in our nested class here. And then remember to specify .all so that our bytes string will work with that regular expression search command. And if that turns out to be a none value, which means that search did not find it, we'll raise an exception. And remember now we have to raise an exception from the parent object here. ASyncRAT parser error. And we'll say could not identify AES metadata flag. All right. And then if we're successful though, we want to say AES metadata flag found at offset, and then we'll do the hex version of nd flag offset, and actually we want to do the start of that match because the offset object itself is just the match object. We need to call .start to get the file offset where the match was found. There we go. And then of course we want to actually return that to the calling function. So let's see if we are even able, oops, I need a parentheses right there. Let's just test this part real quick and make sure that we're able to collect that AES metadata flag and all of this is working as expected. It'll just be a quick test. Actually, we won't be able to test that yet because we first need to actually create an object, an instance object of this, and we'll do that back in our ASyncRAT parser class. We'll say AES Decryptor equals self.asyncrat AES Decryptor and pass in ourself, our parser object, as the parent for this Decryptor object here. So now that that's done, we should see the debugging messages. You can see here, I was trying to do it and I was like, why isn't this working? That's why. So right now we're getting an error, so something is wrong. We could not identify the AES metadata flag. So let's see if we can troubleshoot this. Yep, I see it now. I put 7E here. This should be 7.3 for that new object command. I accidentally put the wrong opcode there. So let's try that. See if that clears up this error. Sure does. So we found the offset at 231E in the file, and that should match up with what we see in our hex editor right here. And it does indeed. That is awesome. So we found our metadata flag. Now we need to use that flag to actually parse all the AES metadata values that we talked about right here. So let's start creating some functions for those. All right, for the key size and block size, actually, we don't need that AES metadata flag. It will be helpful in the rest of these, but the key size and block size we can actually get independently. So let's say key size and self.block size. I'm going to do a little combining here in this function because they are right next to each other in the executable. And I'll just call it get AES key and block size, and it will return two values, the key size and the block size here. So let's go ahead and try to implement this. We'll just set up a definition here. Get AES, I'm just going to copy it actually. There we go. Pass in self. And the way we're going to do this is if we look back at our assembly here, we can see that the key size and block size are defined right here like we looked at earlier. So we really just need a pattern to extract these two numbers out of the assembly. Let's take a look at the instructions just like we did with the metadata. And we can see that these calls are fairly similar. There's going to be a LDLOC1, load location, LDCI4, call virtual, rinse and repeat for the block size. So the first one was the key size, the next one's the block size. So we really just need to look for the pattern of this going on here because this will be the only time this occurs in our payload, most likely. We could search and verify that. So let's look at what this looks like in hex. So we see 0720 and et cetera, et cetera. If we look up 07, if I can type it out, that is our load location or load local variable one on the stack. So that's our first operator. The next one should be, what was it? 20. So that's going to be our load integer 32. And then the next 4 bytes are going to be the value of our key size there, right here. So that key size is represented in hex as 00000100, which is 256. And remember, that's in bits for our key size. So we'll capture that. And then right after that, we have a 6F. That is a call virtual. So that's calling, if we go back here and look at the instructions one more time, that's that call virtual to right here. That's setting the key size right there. So that's a call to that set key size function. We don't really care. That's going to be followed, I think, by 4 bytes. We don't really care what 4 bytes that function's address is, but we do care what comes after that because the next part is going to be the same command and then the block size right there. So let's make a pattern using those opcodes here. Bring this back up and we'll put it right up here underneath our AES metadata. We'll call it pattern AES key and block size. Very descriptive. And we'll say the 0720, that's our load local variable, and int32 operands there. Then we want to capture the next 4 bytes because that's going to be our key size. And then the 6F is going to be the call to the call virtual to the set key size, and that's going to be followed by 4 bytes for that function address. We're not really caring about that, so we won't capture that. And then another 0x70, 0x20, 20, and then another 4 bytes, and that'll be our block size. So that's fairly straightforward to capture those 2 pieces of metadata without even using the AES metadata flag here. So let's go ahead and implement this. We are going to put a logger message here just to say I am extracting the AES key and block size. And then we're going to do that by using our trusty search again. Except not with that pattern, but with AES and block size in our parent data. And then make sure we specify .all. If hit is none, let's go ahead and throw another or raise another exception. To say, we don't need a format string, could not extract AES or block size. And then if we are successful here, we'll get the key size by using our parent's bytes to int function. And that search pattern, because we specified these parentheses here to capture both of those 4-byte sequences, we can access those by using the match objects groups function. So when we call groups, we're going to get a list of matches back. And so the first element of this list is going to, or the 0th element, I should say, is going to be our key size value. And then the first element is going to be our block size. So the way we want to do this is convert those 2 values. Here we go, back up here. Using bytes to int. So just like that, and we want to convert that to an integer from bytes. And remember, this is in bits, so we actually, for our AES decryptor, we're going to need this in bytes. So we need to divide by 8 to get the number of bits. Why did I use a double slash there? It's because in Python, when you do in fact, let me do this. Let me start a terminal here, and I'll show you right down here. If I use 8 divided by 3 here, I get a floating point number back, a decimal number. And then if I do an 8, I hesitated there because I said decimal, which is actually a different type in Python, but you understand what I mean. It's a number with decimal points in it. But if I use a double slash, I get that rounded down to 2, and that's what we want for our bytes there. So we can go ahead and close that. Just wanted to explain the double slash usage there. Same thing for block size, except this time it's going to be the first element of our match object, which is that second 4-byte sequence. And I need to change the name to block size like that. And then we will quickly log that we found them. So I found key size, and block size, and then return key size and block size. You can in Python return 2 values from a function, and that's exactly what we're going to do here. Once again, I didn't have you pseudocode that one because that one also required a little bit of pattern making to find those values. But for the next one, you are on your own because you now have all the information you need to get the iterations. Before we get there, I guess let's go ahead and test this and make sure that we're getting the expected key size and block size. But after that, we'll go back to pseudocoding and you can test out some of these other functions here. So let's first test, and we see key size 32 bytes and block size 16 bytes. Awesome. All right, let's next find our iterations and our salt value. And I will give you a couple of hints here. Actually, the salt one, we're going to have to go through that one together because I want to describe a few intricacies of the way .NET handles how the salt is represented. But the iterations you can do on your own. Just a reminder that the iterations was located right after we got our AES metadata flag, right here after the salt value is defined. So go ahead and take a shot at implementing a function that retrieves the number of iterations from that section using our AES metadata flag. I'll give you that hint if you want to try to tackle that on your own. And you can just call it something like we'll say get AES iterations equal, or sorry, I don't know what I'm doing here. Self.get or AES iterations equals self.get AES iterations. So you can try your hand now that I've got that fixed at parsing out those iterations if you'd like to. All right, let's go ahead and knock this one out real quick. This one's actually a pretty easy one. So let's do get AES iteration self. And if you remember our AES metadata flag, let's go back here. We captured up through the address of the salt here. So in the hex editor, we captured all the way up through this guy right here. This is where our match ended. So to find the iterations used in the AES algorithm, if we look at the instructions here, we really just need to look right after that LDS FLD command in the salt address. We need to look for this value right here, C350, which if we translate that from hex is 50,000, and that's our number of iterations. So what we need to do is go to where our match object ended when we found the AES metadata flag, go to the end there, skip over this first byte here because this is the operand to actually load the integer right here, and then parse these 2 bytes, which contain the number of iterations that we need there. I don't know why I struggle so much with remembering the word iterations. And notice that this is in little endian format, so we need to account for that. So let's implement that here. We'll go ahead and throw a little debugger message. It says extracting AES iterations. And then we'll say iterations offset start is going to be our AES metadata flags end, again, plus 1 byte for that operand, that operator that says that we're loading in that integer there. And then the next 2 bytes are going to be the number of iterations. So we'll say iterations val packed equals self.parent, dot data at iterations offset start and iterations offset start plus 2. I used a D there. And then the actual iterations value is going to be the bytes to int value of that. Bytes to int iterations val packed. And then we're going to say we found AES iteration number of iterations. So we know that everything's working. And then we'll return that here. And again, we'll do a quick test before we move on, just to make sure that that's working as we expect it to. We should get an iterations value of 50,000 back here. And we certainly do. Awesome. So everything's working so far. All right, so getting the AES iterations, that was pretty easy, right? You could probably do that yourself fairly easily without much guidance at this point, given everything else we've done up to now. The AES salt, on the other hand, is unfortunately going to be the exact opposite. This is going to be the most complex function we build out in our parser because of some .NET isms, and as well we need to account for a few variations of how people have inserted a salt into their ASyncRAT payloads. So let me go through, we'll take a detour and explain what I'm talking about here and why I've been hinting that we need the FieldRVA table and why I've been avoiding talking about why we collected the location of the salt in the fields table. We're going to shine a light on all of that right now. So first, let's get back to the AES 256 and look at where this salt value is defined here. And you can see it's defined in this particular sample as a byte array. And you can see each byte, this is in decimal form, each byte of the salt value here. Now, if we look at how that's represented on disk, you'll see that the salt value is, well, let's first of all, let's go back here. Let's translate this using CyberChef to its hex version first so we can actually find it in the hex editor. That'd probably be a wise first move. So let's clear this out and we'll paste this in. Let's do 2 hex. And I think we need a comma delimiter there. Or first we need a front decimal. I always forget front decimal first, delimiter, comma, 2 hex, and then we'll use a space here. So if we look in the, where we looked at here, when we go to the hex editor, we see 1F208D, blah, 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 blah. That is not our salt value. We would have expected, oh, you know, it's defined right here. We see it. But actually, if we search for this salt value here, let's just get rid of that. There we go. Let's search for this in our hex editor. It's actually way up here at 0230, whereas before this declaration or this initialization is going on somewhere around 02 or 04 actually, 60. So what is that all about? Why is this stored somewhere completely seemingly random in our hex editor, and how are we supposed to find this byte array value if it's not where we think it's supposed to be right here? Well, this comes down to how hard-coded static byte arrays and other arrays are represented in .NET executables. If we open up the IL instructions here, we actually see not just like a load field for salt here. We see a call to initialize array and a load token operation here with this weird private implementation details object, which has an ID right there. That ID might look familiar to you because it was in our field table following right after the salt. So if we look at where the salt address was at 2C, right here, that little designation that's generated from .NET for that array is right here. What the heck is that? Well, that is sitting at token 2D in our field table. If we go down to the FieldRVA table, we can see there are 2 entries. One is mapped to field 2D, one is mapped to field 47. That field 47, if you go back to our field table here, that's just the last byte of our address here, or token right here. 47 is this guy right here. And if we look for where this is used in our program, let's just search for that sequence here. Or I need to actually go up here. Search assemblies is what I was looking for up in the edit menu. I don't know why it took me so long to find that. So if we search that value and look at where it's defined here, let's go ahead and right click it down here and use analyze to see where it's read. And go there. That other value is another static hard-coded array with a period and a slash and a double slash there. So that's just another hard-coded array. The point being that this FieldRVA table contains an entry for that static array, and this actually contains an RVA in the FieldRVA table to show us where the contents of that byte array are stored. And to make this even more complicated, unlike the other RVAs that were like from streams, this virtual address is based off of where the text section of the executable starts. So the text section's virtual address is 0x2000. So this, the byte contents start at virtual address 2050. So that makes it really complicated because that means in order to derive our salt value, and of course we could cheat and we could say, we could assume that the salt value is going to stay the same every time, but it will not, I guarantee you, and I'll demonstrate that for you in a second. But in order to find this value, we first need to find, which we already did, the field entry for the term salt. And we did that before when we found our AES metadata header flag, and we found out that that was stored at 2C. We then need to move to the next entry in the table because it will always precede that salt value in the field table. And then we need to then go down to the FieldRVA table, use the last byte of this 2D here, to look up in the RVA table our field, and then look up the RVA for that field, and then subtract the text section virtual address to find the offset in our file. We're going to cover that later on. I'll leave that for when we get to that point. But you can see that this is going to be a little more work than we might have anticipated. The other wrinkle here that's going to add even more work is we have to also account for if they specify a string salt value, which is totally allowed. And so I have loaded in a real world ASyncRAT sample here. It's called Cheat Minecraft. So be careful, kids, where you're getting your Minecraft cheats from. And if I open this in dnSpy, I can see, first of all, that they have modified some of these setting strings, probably an obfuscation tactic. And that's where we're making our parser not assume that these are all going to stay the same all the time. But more importantly, if we go into AES 256 and look at the salt value here, they're actually getting it from deriving bytes from a string here, which looks completely different than just a hard-coded byte array there. So we need to account for all these edge cases in order to make sure our parser stays robust against all these different configurations we might have. So let's work through this together. Let's go ahead and create our skeleton here. And we'll start working on the implementation and pseudocode this out in just a moment. Hey, Jeff from the future here. I just realized I said that we were going to look at the field table and then look at the value immediately following the salt in the field table to get this kind of token address here and then use that in the FieldRVA table. That's actually not guaranteed to always follow the salt in the fields table. So we are not going to do that method. I had it in my head because that's actually the first approach I tried and it does not work all the time. And so what we're actually going to do here as we start our get AES salt function is develop and use a pattern to find the salt initialization. And then we're going to check if a load token or load string operation is used. So like I said, if this is a hard-coded array right here, we're going to see a load token operation right here to load that byte array and initialize it. And if, on the other hand, like this other module we're looking at, they have a string here, we are going to instead see a load string operation here, followed by a call virtual to get bytes. So we'll look for that pattern, and then we'll determine from there if load token, we're going to need to reference or grab the FieldRVA, or I'll say grab the field address for the salt byte array identifier. I'll call that, what I'm talking about there is back in this guy here. Go to the fields table. I'm talking about this value right here. This is the salt, we'll just call that the identifier, byte array identifier. and then pull the offset of the byte array contents from the FieldRVA table, and then read those contents and return them as salt. And on the other hand, if it's a load string, we just need to find the string at the address or RVA given and decode it to, or I should say, encode it to bytes, because the salt value needs to be a byte string in the end, because when we use it in our AES decryption, the AES decryption is going to expect it to be a byte string. So we need to convert it, whatever it is. If it's a string, we need to convert it to bytes. And if it's a byte array, obviously it's already in that format there. I think that about does it. Obviously, the pseudocode hides a lot of the implementation details here. So let's get started with actually implementing this. So let's start by developing this pattern that I'm talking about to actually find the salt initialization, because we're going to use that. And what I mean by salt initialization is the section right here. What I mean by that is we want to look for the instructions here where we see the call to initialize array and then the STSFLD into salt. If you remember, we identified earlier with our AES metadata grouping the RVA of the salt, and that is this guy right here, 0400002C. And so for our pattern to find this initialization, we really just have to look for that address alongside a 0x80 opcode, which is the STSFLD, and followed by a return opcode, which is 0x2A. So that's the pattern that I decided to use because it's fairly unique to find the AES salt initialization, we'll call it. And that was 0x, what was it? I need to bring my VM back up. 80 followed by, come on, there we go. 80 followed by a actual wildcard string here, because we're going to actually insert in the RVA for the salt we found so that we know we're finding the exact place where the salt is being initialized and not anything else being initialized. So that's why we captured that salt RVA, is so we could insert it in here. And the way we're going to do that is just to put a %B here. This is a formatting placeholder for a byte string, and then follow that by 2A right there. And back down here in our salt get AES salt function, the way we're going to use that pattern is, well, let's set up our usual stuff. First, we'll put a debugging string here. And then we'll also need to get the salt RVA from our AES metadata flag groups. Remember, it was a capture group, so we just need to reference that 0th element. And then we need to find the initialization by looking for self.parent.data.find self.pattern AES salt init, except we're going to insert our RVA in there by doing a %. That's the formatting string that will actually insert this value into our pattern. And that should be what we need to get the salt initialization offset. So let's recap that, because that was very complex there. We developed a pattern, this guy right here, to look for the salt initialization. And we left a placeholder for our salt RVA, which we gathered back when we looked at this AES metadata pattern. And we inserted that in there using that % operator to insert that in. And then we used that, oh, I went too far. We use that to look in our data and find exactly where that occurs so we can get an offset in our parser here. Once we have that, well, first of all, let's make sure we do some error checking here. If that fails, let's go ahead and put a raise ASyncRAT Parser error could not identify AES salt initialization. That means something went wrong. We couldn't identify where it was being initialized. Otherwise, we need to then look at what operation we're looking at. Is it a load token or a load string? And the way we do that is if you look at these instructions again in the hex editor, we should be able to see if it's a load token, we'll see a D0 operation followed by 4 bytes. So let's take a look here at our initialization. There's our D0 that shows the load token, and it's followed by 4 bytes showing the token there. So that is our identifier. I guess I could call it token as well. You can see it's not 2C, but 2D, which is the field we were looking for. That's this guy right here, and that's what we want to reference in the FieldRVA table. So if it's a load token, we can determine that by looking at, let's see, where's the AES salt address? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bytes behind. We can look to see if that is D0, or if it's a load string, that will be a 7.2 instead of an 8.0. So that's how we'll identify whether or not we're looking at a load string operation or a load token operation, and then we'll handle each of those in turn there. First, let's go ahead and implement that check. So we'll say the salt operation offset is my salt initialization minus 10 bytes. And actually, we need to convert this to bytes here because we're going to compare this against another byte. Right now, this is going to be an integer. And so to convert that to just a single byte string, we're going to do something like this, bytes, which is a built-in function, .data salt op offset. So the syntax of this is a little odd because the bytes function expects a list or an iterable of integers, and since we only have one that we really need to cast to a byte string, we just pass in a list of one integer here, which is the data we read at that spot, and that converts it to a byte string. The reason we convert it to a byte string is we're going to compare this to those two opcode strings. Let's make some constants for that. We'll use opcode load string, which is going to be if I remember, that's the D's, no, that's not D0, that's 7.2, 0x72, and opcode load token is going to be 0xD0. So these are byte strings, and that's why we need to cast our integer that we read in for our salt operation to a byte string right there, and that's one way of doing that in Python. And so if salt op is equal to self.opcode load string, that's actually the easier case. We just need to retrieve the address. Let's go back to our sample here so I can show you what this looks like in our sample. Let's go to AES-6 salt, and let's look at the commands here. So if this is 7, what did I say, 7.2 for load string, which is this guy right here, then all we need to really do is read these next 4 bytes, and that is going to be actually an entry into the US stream table. So if that's the case, we just need to use the function we already defined, US RVA to US val, and pass in the RVA, which I just realized we didn't actually pick up that RVA. We should do that here. So once we find that operation, regardless of if it's a load string or a load token, the next 4 bytes are going to give us the address that we need. And so we'll capture those into String-RVA packed, and that's going to be parent.data from salt op offset to, or salt op offset +1, because we're going to skip over the operation byte itself, and then salt offset +5. So that's going to give us the 4 bytes following the operation right there, whether it's load string or load token. And then, of course, we need to convert that to a integer using bytes to int. To int salt strings RVA packed. So let's look at that in the code here, and I'm going to use the load string version of this. So to recap, we're looking for the salt address, which is this guy right here. We're going back 10 bytes and checking this byte right here to check if it's D0, which means it's a load token operation, or if it's 7.2. And sorry, I just realized I'm very zoomed out here. If it's 7.2, that means it's a load string operation, and that the next 4 bytes are really just going to be a relative virtual address into the US streams table. And so we can, again, reuse our US RVA to US val to translate those 4 bytes, or that RVA. And then we're actually going to write a helper function to help us here. But what we want to do is decode that from UTF-16 little endian, which is how it's stored in the RVA or the US stream, and then encode it back to bytes. The reason we're doing that is we want to remove all the null bytes from that string before we try to make it into a byte string with the salt, because the salt doesn't care about if the string's Unicode encoded or not. When the call to get bytes is here, it's called with ASCII, and so we're going to basically translate that to its ASCII representation, remove all the null bytes, and then cast it to a byte string. We'll worry about that in just a little bit. And we're going to write that helper function in the parent class, actually, because we're going to use that decoding function later on when we need to decode those strings for our output. Otherwise, if the salt op is equal to load token, then we need to actually do that whole translate RVA to FieldRVA table and find offset of byte array contents. That's going to involve another helper function as well, because that's going to be intensive. And then otherwise, we're going to raise an exception, because that means that we didn't find the salt value that we were looking for, the operation that we were looking for. Unknown salt opcode found, and then we'll show what that is in hex. And then if everything is successful, I need to do a pass here because I'm getting an error. If everything's successful, we'll just log that we found the salt value of whatever it is. And then we'll return that. And it's giving me a squiggly there because we haven't actually defined what salt is yet. We're going to do that in these sections right here. Am I missing something else, or is that the only problem? Let me just see if this solves the squigglies I'm getting here. Oh, it's because my indentation is very off right now. I need to just tab these over. There we go. That's better. So now we need to get to work. Now that we have a skeleton here on first working the helper function, which is going to decode that string from the US stream from UTF-16 little endian, which is how those are stored, and then encode it back to a byte string. Why are we decoding and then encoding? Again, it's to decode it from UTF-16, get the representation of that string without those null bytes in it, and then encode that back to a byte string. If we didn't do that decoding first, our byte string would include all those null bytes, and we don't necessarily want those in our salt. So let's go ahead. Like I said, we're actually going to write this in the parent class here. I'll just stick it wherever, and we'll call this decode bytes. And then we'll pass in, I guess we'll just call that byte string. So this function is going to serve two purposes for us. Number one, right now we're going to use it to just decode a string from UTF-16 little endian and return back the representation without those null bytes in there. The other way we're going to use it, I should say, is if you remember when we ran our parser and we saw these debug messages, we got our decrypted or our encrypted string values back here. And these are all stored in UTF-16 little endian because they're in the US stream. and they have these null bytes just sprinkled inside of them. They're really hard to read. So when we report back to the user our decrypted config, we want to decode this to a more human-friendly way of reading this, which basically means removing these null bytes and decoding it into a regular string. Same thing over here, except for our config key values. Those are in UTF-8 and they don't have those null bytes, but they're still byte strings and we would rather have them in a nice printable string. And by calling decode, we can just decode that byte string into a regular printable string like that. It won't have those byte symbols or any weird characters in that string there. So the way we're going to write this is we're going to account for those two cases. Let's start by just initializing a result and setting it to none. And then we're going to check to see if there's a null byte in our byte string. If it is, that means we're probably looking at, we're definitely looking at a UTF-16 little endian formatted string. And so our result is going to be bytestring.decode. And then we have to pass in the value UTF-16LE. This decode is a string function that's built in Python. You just have to pass it in what in character encoding you want to decode from. So that's what that is doing right there. Otherwise, we're looking at a ASCII or UTF-8 string, and so our result will be the result of decoding that byte string to UTF-8. And if anything should go wrong, as usual, we will raise an exception. Oops. Error. And then we'll say error decoding bytes object to Unicode, and then show them the byte string that failed. And then otherwise, we're going to return the result if we were successful here. So what that means is, let's just really quickly use these as an example. Let's say this is my string here. And let me just start up a Python shell. Let's say this is my string. Oops, except I want a Python 3 shell I would prefer. We'll just do a quick experiment here to see how this works. If I use s.decode UTF-16LE, I get a much nicer readable string like that. And same thing if I have another string that's in bytes, a byte string that says ports. If I just print s, it's going to print it with that prepended b, and it's going to look like this, and it's very not nice to look at. So what we do is instead print s.decode UTF-8, and we get a nice printable string. So that's what we're looking to do with this helper function here. We're just kind of using it for multiple purposes. So let's get back to our code. Now that we have that function all written out, we can go back up to our salt function here, to the load string operation. And the way we want to do this is we want to say salt, oops, there we go. Salt equals self.parent.decode bytes, pass in our encoded, oops, I just realized I didn't assign this to anything. Let's assign this to a variable called salt encoded, and then we'll pass that in. And that's going to get us, again, this nice clean string. And then we're going to, I should have kept that open so I could demonstrate the next part, which is actually encoding it back to bytes after that. So if I do this again, and I decode from UTF-16 little endian, and I encode again, I get now the byte string equivalent of the cleaned up with string without those null bytes in there. So that's what we're doing here to obtain our salt value in the case that load string is being used. And that's all we need to do there. Now we need to handle this complex load token case here. And so to do that, we're going to create another helper function. You guessed it. And we'll go ahead and try to pseudocode this out. So get a AES salt LD token method, we'll just call this. And we're going to need self and salt strings RVA and salt op offset as well. Why do we need that? Because if we're looking at the load token method, we actually need to obtain the salt size from where that salt offset was. What am I talking about with that? Well, let's go back to our VM here after I boot it back up and I'll show you. All right, with that booted back up, let's take a look at the salt initialization for the load token method here with the byte array real quick. We need to know how long this byte array is because we need to know how many bytes to read once we actually find where the salt is located. So if we go back and look at these instructions, I didn't talk about them the first time, but if you go farther up here, right before load token is called, there's also a load of an integer here and then a new array of system bytes. So it's initializing this byte array. And this is our length right here, 20 in hex, which is 32 bytes in decimal, of course. So this is 32 bytes long. And if we go in the hex editor here, we can see that if we start at our match group where the salt operation offset was, or actually right here, I guess, and backtrack 7 bytes, 1, 2, 3, 4, 5, 6, 7, that gives us our length of that byte array there. So that's where this calculation is coming into play here. So let's pseudocode that out. Actually, we already kind of worked through that, so let's not even pseudocode that part. Parent.data salt offset minus 7 bytes. That's going to give us our salt size. And since it's just a single byte we're reading from data, we don't need to, oh my gosh, I just put Darter there. We don't need to do any conversion there. It's going to be an integer already. Now we can do some pseudocode after talking through that. The next thing is that we need to get what I'll call the field ID. So that is, if we look back here and go to our fields table, we now know how to get the address for this guy right here, this identifier. We want to get this 2D off the end of the token there, because if you remember, that's what we're going to use to reference in the FieldRVA table to find the entry for that and the offset for this value, this byte array right here. So to do that, what I'm going to do is take my salt, let's just call it identifier field ID equals salt strings RVA minus the strings RVA base. So in this case, it's going to be 0x400 or 0400002D. Did I put another extra 0 in there again? I totally did. Minus 0x04000000. And that's going to give us 2D. And that's going to be our, what I'll call our salt field ID. And then we're going to look that up in the FieldRVA table and then look up the offset there. So let's do salt field ID equals salt strings RVA minus self.parent.RVA strings base, or have that defined. And for these next two operations of actually going into the FieldRVA table and getting that ID or the RVA from that table and then translating that to an offset, let's go ahead and use some helper functions, but let's pseudocode it out. So first is, once we have the field ID, index into FieldRVA table and find, or I guess the best way to say it is go to FieldRVA table and find entry for salt field ID, and then take RVA for byte array content from FieldRVA table, translate RVA to file offset, and then retrieve salt value from that file offset. You can try to implement this yourself if you want to at this point, but I think we're probably going to have to go through together to find this. So let's start by making two helper functions. One to go to the FieldRVA table and get that entry for salt field ID and get the RVA out of the table. And then a second to take that RVA and translate it to a file offset for us. So we'll call the first one, let's just put it right here. We'll call it salt field RVA equals self dot field ID to field RVA. And we're going to pass in our salt field ID to this. Let's go ahead and implement it right here. Just copy and paste. There we go. And then the way we're going to write this is going to be pretty similar to how we did the get table start function, except instead of working in the field table, we're going to be now working in the field RVA table. So field RVA table start, we can use our predefined function to get the start of the table. Oops, get table start. Let's go ahead and make a constant called table field RVA, and that's going to be just field, or it doesn't have to be a byte string, just field RVA like that. And I am right here. There we go. Self.table field RVA. And we're going to set our field RVA value, the value we're going to return to none for now, just to initialize it. And we're also going to make a Boolean here called matched. We're going to set that to false. And I'll show you why we're going to use that in just a second. We're going to use that as a kind of flag. So just like the get table start, we're going to set our current offset to our start of the field RVA table. And then we're going to iterate through every row in the table. So in self.parent.table map, self.table field RVA, num rows. So for each row in that table, we're going to try to extract the field ID and the field RVA from that table. Because if you remember, there's only two fields in each row here, and there are two fields really besides the token and offset, and that is the RVA and the field itself, the field ID here. So we're going to extract both of those. Oops, close too many or minimize too many things by extracting the field ID, and that's going to be self.parent, again converting to an integer here, self.parent.data current offset plus 4, because if we look at how these are represented, the RVA comes first, and that's 4 bytes, so we need to skip over the RVA to get the field ID, which is also 4 bytes long. Or I'm sorry, that's 2 bytes long, not 4 bytes. So current offset plus 6 will give us our field ID. And then our field RVA is going to be self.parent.bytes to int self.parent.data current offset, and then that one is definitely going to be 4 bytes, just like that. So once we have those two values, we're going to check if field ID equals to the ID we're looking for. So actually, let me just rename this to ID here, to ID. Then we're going to set matched equal to true. That means we found the field ID that we were looking for, and we're going to break. Otherwise, we're going to say, okay, or actually we don't need an else here. We're going to say, okay, we didn't find it in this row, so let's go ahead and increase our cursor by adding the row size for this particular table, which we can get from our parent table map again. So the reason we have that matched flag there is if we get to the end of this, well, first of all, let's make an exception. If anything else goes wrong here, we'll just say raise self.parent.ASyncRAT parser error parsing field RVA corresponding to ID, and then show them the ID. And we want to make sure that comes from E. Otherwise, if we're not matched at the end of that, if we've gotten through the whole field RVA table and we're not matched, we need to raise an exception. So that's why we're using that match function there, is if that's not true, we know that we never actually matched our field ID there. we didn't have to worry about that in our fields map because we just got the whole table. But in this case, we're not pulling out the whole table. We're pulling out a very specific row here. So we'll go ahead and raise an exception. I'll just borrow from right here. And we don't need a formatted string, or I guess we can. We could just say could not find field RVA corresponding to ID. So this is separate from our exception above. This means we just didn't find it. The other one means something probably went wrong with the field RVA table itself. It might be corrupted or obfuscated or something. And then we'll do return field RVA if everything went right. And there we go. So we've got that part down pat. So that will return to us the value 0x2050. So now we need to make another helper function to actually get that RVA translated to a file offset. So we'll call this one, we'll write it right below here. We'll call this one get, or we'll just say field RVA to offset. Self, and then field RVA. So the way this one's going to work is we need to get the RVA in reference to the text section RVA, like I said. So let's go back here real quick and refresh ourselves on that text section. It's right up here. This is the section of the executable that contains all of the instructions basically, and it's alongside the resource section and the relocation section here. You don't need to know too deep in the details about that. What we're concerned about is this virtual address field here and the pointer to raw data. Why those two fields? So the first one, the virtual address, we already talked about. We're going to take the RVA from the field RVA table for our salt byte array. We're going to subtract the RVA of the text section from here. So 0x2050 minus 0x2000. And then we need to add that to this value right here, which is actually the file offset where the text section begins. So let's break that down in some comments here just so we can see how that looks. So let's say our field RVA, in this case, which it is 0x2050. That means in our text section RVA is 0x2000, and the text section offset is 0x0200. That means that our byte array offset is going to be equal to our field RVA minus our text section RVA plus our text section offset. So in practice, that looks like 0x2050 minus 0x200 plus 0x0200, which will equal out to 0x0250. A lot of math for just a quick result, right? So our salt byte array should start at 0x250. And if we go back here and look at the hex editor and go to position 0x0250, that is indeed the start of our byte array. If you remember, I think I still have it pulled up. Yeah, it's this BF, EB, etc., and that is where that array is stored. Why are things designed this way? I wish I knew. I wish I knew why we had to go through so much pain just to extract the contents of that byte array, but hopefully now you understand the math there a little better. So let's go ahead and do that. Let's say text section metadata offset. What I'm looking for here is where is this metadata located in the file? And the way we can find that is just by looking for the presence of this .text string. And then moving forward, what is it? 12 bytes, I think it is, to find the RVA. And then another, well, from the start of the text section, 20 bytes down to here to get the offset there. So let's do that real quick. And let's also write or let's do a constant here to look for that text. We'll just call it section identifier text. Ooh, identifier. Did I spell that right? Yeah. Text equals, and then we're looking for the byte string dot text, which is going to tell us where that section begins there. And back down here, we will say equals to self.parent.data.find self.section identifier text. And of course, we need to go through and say if that is equal to -1, we're going to raise another error. I'm just going to borrow from up here. And we'll say could not find text section or something like that. Could not identify .text section metadata. That shouldn't ever happen unless something is really wrong with our executable, but we will keep it in there just as a check to make sure we're covering ourselves. So next we want to then, as long as that's not equal to -1, that means we got a successful offset, and the text section RVA is going to be equal to self.parent.data text section metadata offset. Like I said, plus 12 to that plus, 16 to get the 4 bytes to get us the RVA. So again, to recap, if we start from where we find this value at 178 in hex and add, what did I say, 12 to that? Sorry, I just realized I typed that in hex, the 12 in hex. It's going to be C, and that's going to bring us to 184, which is our virtual address there. And then we just need to add a few more bytes to get to our offset. So that's going to be our text section RVA, and then our text, section offset is going to be self.parent.data. I'm just going to repeat this line here, except I'm going to change the numbers around 20 through 24. That's the 4 bytes representing the actual file offset there. And so our field offset, and actually we need to convert both of these to integers, don't we? So let's go ahead and call self.parent.bytes to int on these. We'll do the same thing right here. I could have double typed that in VS Code. I don't know why I didn't. It's because I'm tired, actually. It's 2 o'clock right now. That's why. So we do that, and then we say field offset is going to be equal to field RVA minus that text section RVA. Whoa, sorry, hit a hotkey there. Plus our text section offset. So we recreated the math we described up here to get our field offset, and then we're going to return that. Are you still with me? Because we're almost there, guys. I promise we're almost through the thick of it, and we're going to be in a good place here once we get the salt value figured out, because then all we have to do is put everything together here. Congratulations, you figured that out. Let's go back up to our salt section and just end this misery finally. All right, all we need to do to finish this off is just say salt equals self.getAES salt load token method, and then pass in what it asked for, which was the salt strings RVA, and then the salt offset here. And that is it. We have now accounted for all those weird edge cases, and we can successfully extract our salt. Well, we think we should be able to at least. Let's go ahead and check that hypothesis before I'm going to say that. So we'll refresh our code there. We'll go back up and we'll run this. All right, we do get an error, but it looks like it's because the salt came back as a none type. Okay, so let's troubleshoot here, and we'll be back here in a second to see what went wrong here. Oh, yep, I can tell it's getting late because I forgot to finish not the salt section, but the get AES salt load token method. We actually didn't finish this out. You probably knew that and were yelling at me again. I'm sorry, it's late. I'm going to use that as my excuse. And we're going to just fill this out with the rest of our code here. We already created that function, and we just need to take that offset and receive the salt value by looking at that offset, looking at the bytes from that offset to salt size. And that's where we're going to read our salt value from, and then we're going to return salt value. And that should hopefully fix the errors we were seeing there. Let's go back and test again. Clear it out. That is a beautiful thing. We are extracting our salt value successfully. And just for giggles, I'm going to run this against that sample I showed you all that uses the load string method to make sure that it's working correctly. Let me clear that out. And that is I have a ton of ASyncRAT samples. I'm going to talk about that in a little bit. And I believe this is the one. Okay, so what this is saying is that string object has an attribute hex. I just realized we did not ever encode our value back here. We decoded it, but we need to encode that back. And that should fix that error there. And let's run this one more time with that sample that uses the load string method. There we go. So this is the hex representation of that string that we saw earlier. If I bring this into CyberChef and do a from hex, we can see that that equates to that string. So that's great. That means everything is working as expected, and great job. You guys have made it out of the thick of it. That was the hardest part of what we'll come across here, was getting that salt value and accounting for all those edge cases, and we did it. That's done. All we have to do now, and it sounds like a big task still, but it's not going to be because we've done it before, is derive our AES key and then write the function that's actually going to provide the decryption for our config. So let's get started on that next. All right, so let's go ahead and set up our skeleton here. We'll just say AES key equals self.get AES key, and we'll go ahead and implement that right here. Get AES key, and we're actually going to be able to cheat with this one. It's going to be wonderful. All we need to do for the key is find out where it's initialized. So if we go back to our settings, we really just need a pattern to find where this initialization takes place, because if we look at the instructions here, we're going to be loading in the value of the key from the result of this get UTF-8 function here. But in the hex version of this, these instructions are going to show us the location in the fields map that key is. So that 04000007 should be the field where our key is stored, and sure enough it is. So we already know what the address of the key is just by looking at these instructions. And since we already went through the trouble of building out our fields map, we already have access to all those values in our translated config. We can just take that address, do a couple of conversions, and convert the value in our translated config to our key value and use that to derive our key. Let's walk through that in pseudocode, and then I'll give you a chance to actually go through and do that yourself, because we've done this same kind of programming pattern a couple of times in this parser now. So the first is develop and use a pattern to get or find the key initialization, and use it to find the address of the key in the fields table, or I should say, I guess, the offset. And then once we do that, we are going to then translate the offset in the fields table to its value in the translated config. Because if you remember, the translated config already has our key value, which is not encrypted because it can't be, because we need the key to do any kind of encryption. So in our translated config, we already have the keys passphrase. I keep calling it the keys value. It's not actually the keys value. It's the passphrase we're going to use to derive that key. So then we just have to use some math to say, let's say our key RVA is 0x0400000007. I think it was. I think I have too many zeros there. 1, 2, 3, 4, 5 zeros I should have. 5, 7. That means in our field map, the index is going to be 0x04, 1, 2, 3, 4, 5, 7 minus 0x04, 1, 2, 3, 4, 5, 6. Yeah, 6 there. Minus 1, just like we did earlier. What were we doing when we were doing that calculation? We were finding strings RVA to strings val. Yeah, we're basically doing the same thing right here. We're just replicating it in this function and doing it slightly differently while we're finding our AES key. That means our key value or key field name is going to be located in field map index 6. And for this sample, it's just the field name is just the word key, but that's not necessarily the case for every single sample. And this one's key, and the other one down here, I think they actually use key. Yeah, okay, this is the other one that was, or no, this is, which one am I looking at? Oh yeah, I reloaded, so I don't have that sample anymore. But sometimes, the moral of the story is that sometimes this may not just be the word key, it may be something else. So we have to reference our fields map to actually get the name of the field, and then look at our translated config at the same, or not the same index, but we're going to take the value of field map 6, which is going to be the name of our field, and reference that in our config, and that's going to give us the keys value in our translated config, which for this one should be this value right here. So that's what we were trying to do here in this function. And then we're also going to derive the key using pbkdf2. And we saw how to do that in CyberChef, and I'll show you how to do that in Python, but I'm going to give you a chance to pause if you're really feeling daring at this point and want to try to figure out how to do all of these operations, or at least through the part where we get the key RVA and the key value here. All right, so as usual, we're going to start with a debug message, extracting encoded AES key value. And we're going to do a hit again, and we're going to search for a pattern. So first we need to develop that pattern here where the key is initialized. So to get that pattern, let's use this guy right here, because these instructions are going to be a LDS FLD with key and then a new object call here. So what that's going to look like in hex. You don't have to use this particular one, but I think it's unique enough that we can here. So right here. So 7E is our LDS, or yeah, LD, did I get that right? LDS field. Let's just look it up. 7E, LDS field, yeah. LDS FLD, or whatever you want to call it. Followed by 4 bytes, which will have our keys, address, or RVA, and then a 7.3 for that new object call there. So I'm going to use that for my pattern. So let's go back to our code here, and we'll make it right up here. We'll just call it pattern AES key. You'll notice I'm kind of being sloppy with my code and organizing things right now. I'm going to clean it up in the final version, but for right now I'm focusing on the functionality here. 7E, like what I mean by that is like I usually alphabetize and make sure everything's in order in these constants, and I'm just not going to do that right now. And we know that this is always going to be an address in that 0x04 space, and so we just really need to put a wildcard right there, and then just look for 0x04 right here to get the final value of where our key is going to be in that field mapping there. So that's the pattern I'm going to use right there, just like that. And let's go back down to our search call here, and we'll say self.pattern AES key and self.parent data and .all as usual. And again, if hit is none, raise self.parent.ASyncRAT parser error, and just say could not find AES key pattern, something like that.
Hello, Jeff in the future again. After editing this video, like I said, I jumped in here around the time we wrote that strings RVA to strings val function to update this, and I'm going to update this piece as well because I did the exact same thing. I made this so inefficient in the video, so I just wanted to update you all here. So the astute of you, if you had seen this snippet in the video, I'm going to overwrite most of it, but you might have caught it in some other piece of the video, I guess. This is how this was originally written in our get AES key function. I was trying to get the offset and then convert that bytes to int. That's fine. But then I was doing that subtraction on the string space again and trying to get that from the field map. We already did all this. All the values are already in the fields map, so you don't have to do this conversion like I'm doing here. It still works, but it's overkill. All we have to do here really is go key field RVA equals self.parent.bytes to int hit.groups 0. That's our AES key pattern there, and we're just getting the match object from that. Then key field name equals self.parent.strings RVA to strings val key field RVA. Because we're using the strings RVA, or is it strings RVA to strings val function, because that does all this conversion for us. So we don't need to redo that conversion. We just need to get the RVA and pass it in the function. That's why we wrote that function in the first place. So apologies on behalf of past Jeff that he made those mistakes. Hopefully you forgive him, and this will be the last time you see me. There are still a lot of mistakes in the video, don't get me wrong, but none of them require a time traveler to come back and fix them, so they're not terrible. All right, enjoy the rest of the video, everybody. Thanks.
And then finally, the key value is going to be self.parent.translated config key field name, just like that. So that key value is going to be this guy right here that we're going to get. So then we're going to, let's go ahead and make a logger debug message here that says AES encoded key value found. And this is key val. This is going to be the base 64 encoded string. That's why I'm saying encoded value here. Need to add my parentheses. What's going on up here? Oh, I meant to use subtract there. So that means we've got the base 64 version of that key value. And then, like I said, the next thing we need to do is use pbkdf2 to derive our actual AES key from this passphrase. So we're going to do a few more imports here. Again, this is all using the Python built-in modules. So I have quite a few I'm going to import here from the cryptography library. And we will go over each of these in turn. The first one we're going to use is this pbkdf2hmac import here. So let's go back down to get AES key. And let's go to here. And the first thing we need to do is find the base 64 decoded value. And actually, I did all that work, and I have to go back up and import from base 64, import B64 decode here. Because we need to decode the key value first, as they do in the payload right here from base 64 string, and then pass that into the pbk function so that we derive it from the decoded string there. So let's do that here. We're going to do a try passphrase equal to B64 decode key val. And if that fails, and this time we are going to say if that, extraction exception as E. This time we'll say Parser error decoding key value key val. And let's see, if we're successful, we want to say that we found the passphrase and put the decoded string there. All right, so if all that's done, then we can move on to the actual key derivation. So to do this, we're going to create an object called KDF, the key derivation function, and we're going to use that imported pbkdf2hmac function. And that requires a few different arguments here. So we first need to specify our algorithm, which we know is SHA-1. It's always going to be SHA-1 for these, unless someone really modifies the ASyncRAT payload, which I would argue at that point we're looking at a variation of the payload that may not fall into what we call ASyncRAT here. So we also need the length of the key, which is stored in self.keySize. We already got that. We need the salt. Already got that through our strenuous efforts. and we need our iterations value, which we already also have that. So that's why we collected all that metadata so we could use it here. We're then going to try to call the derive function with our passphrase. And of course, we're going to log if there's an exception and say for this one, I don't know, we'll say error deriving key from passphrase. And if everything goes well, we then want to debug and say, we freaking got our AES key, and then render that in hex, because at this point, the key is going to be now in bytes. And so we want to render that in hex. All right, so let us return key here and test out our code and make sure we don't have any weird errors or anything going on here. So we'll update our code, run it again. Okay, looks like I just missed a self somewhere because it's saying there's no value called salt. And sure enough, self dot, oh, yep, I did. I called this salt. It's actually AES salt here. Or maybe AES salt is there. So that should fix that error. Try again. And then we also have, I also probably did the exact same thing there. So self.aes iterations. Let's try that again. Third time's a charm. And it sure is. We got our AES key derived there. There's our AES key right there. We have everything we need set up for AES decryption. The only thing we need to do now is going back up to our objectives for this inner class is offer a decryption function to our parent parser to be called. So the constructor is actually done. We just need to define a decrypt function here. And we'll do that right here. We'll pseudocode this out, and I'll give you a chance if you want to try to take a stab at it, but you'll probably need to read into the cryptography library's internals if you're doing that. So the decrypt function is going to be pretty straightforward. We're going to create an AES cipher with our AES key. Also, I should have mentioned this before. We called this last in the constructor because we saw it relies on all these other metadata being present. So if you're wondering why the order is important here, that is important in this constructor here. So we create it with our key. We then need to decrypt, or we need to use the initialization vector to decrypt the ciphertext. We'll talk about how to derive that initialization vector in just a little bit. And then we need to unpad the decrypted output. What I mean by that is AES 256, the algorithm we're using, will sometimes pad on bytes, or there'll be bytes padded onto the decrypted text. And there's a nice little unpadder function in the PKCS7 object we imported, or the module we imported, that will unpad that data. And then we're, of course, going to throw an exception if anything goes wrong. So if you want to take a shot at this, go ahead. It should be pretty straightforward. You just might need to read into the cryptography library documentation if you're going to try to go this alone. All right, if you're back, let's go ahead and do our debug message, and we'll say decrypting ciphertext, which is going to be I didn't add my parameters here. I need to add those in. We're going to take in an initialization vector and ciphertext here. This is going to be provided by our parser in the parent class here, so we don't need to worry about that. We just need to say that it's going to come into this function with key, self.key, and IV, and I really should, I guess, put this into, or no, it's already going to be at that point, oh no, I can put it in hex, I think. There we go. And IV like that. ... And so let's go down here and make our cipher. We're going to use the imported cipher object to do that. And we're going to use the imported AES to say, hey, I'm going to use an AES cipher. I'm going to pass in our key. And we're going to use cipher blockchaining. And we're going to pass in our initialization vector to that function there. and that's going to set up our cipher for decryption. And to get that decryptor, we're just going to call Decryptor. Next, we're going to make an unpattern object using our imported PKCS7 module. This needs to know the block size, which we have captured already. And then we're going to call the unpattern function to generate an unpattern object. And what we're going to do with that is we're going to try to get the padded decrypted text by calling decryptor.update ciphertext. That's going to do the actual decryption. And then you also want to do a plus decryptor.finalize. That's going to kind of bring our decryptor to a state that it finalizes the decryption and outputs our decrypted string, but with padding. And then our unpadded text is going to just be calling that unpattern object.update on the padded text and doing the exact same thing, unpattern.finalize. And if anything goes wrong, we'll raise an exception here and say raise self.parent.ASyncRAT parser error. And we'll just say error decrypting. I'm just going to copy what I wrote up here. Error decrypting this time. Ciphertext with key that and IV that. And we need to take off there. But as long as that was successful, we can debug and say decryption result and display the unpadded text and return that unpadded text there. Now, before we can test this, we actually need to write the parent function that's going to call this. And again, that's going to take place back in our parser parent object here. So let's go all the way back to our objectives here. We now have the recreating the AES decryption algorithm. We need to kind of finalize that by grabbing our config and calling a function called, we'll call it decrypt config, which is going to utilize our AES. I just realized I typed decryptor here to decrypt our config, and then we're going to report that to the user. Actually, we don't need to do that in the constructor. They're just going to call the report function. We just need to remember to implement that. So let's make this decrypt config function. And we're going to walk through how to generate the initialization vector and basically recreate what we saw back when we initially analyzed the AES 256 decryption algorithm in our payload. All right, so let's pseudocode this out and I'll give you a chance to do this. This is going to be our last function besides the report function, so we're almost there. So first we need to loop through our translated config. For each config key and value, let's check if it is base 64 encoded. That'll tell us if it needs to be decoded first or if it's encrypted. If it is not, leave it alone as is. Otherwise, we'll go through, decode it from base 64. We will extract the IV from after the HMAC hash. Remember doing that back when we did CyberChef. So that's going to be from bytes, 32 through 48 for the IV. And then extracting the extract ciphertext, which is going to be everything after, or 48 after. And then call decrypt function on ciphertext, passing in IV. And that's about it. So after we're done here, we're going to add that to our decrypted config and finally return our decrypted config to the user, or I guess to the constructor here. Config to our instance, we'll say. So if you want to, go ahead and take a stab at this. It should be fairly straightforward at this point, especially if you walk through the CyberChef section, but if not, we'll walk through it again in just a moment. All right, as usual, let's start with our debug statement. Decrypting config, And then we'll go ahead and make a dictionary to store our results. And we'll say for kv for key and value in self.translatedconfig.items, we'll say decoded key value or decoded k. We'll go ahead and decode the string values now, because in our decoded config, we don't want, like I said, these byte strings that have different null bytes or look like they have the prefix of B or anything in there. So we're going to go ahead and use that decode bytes function to decode whatever k is, and we're just going to store that in a variable to use later on in our decoded config. We're going to use a flag here called base64 exception to see if our base64 decoding fails, and if that fails, that means that we're probably looking at something that wasn't meant to be base64 decoded. And then we're going to say decrypted config. We're going to say in our decrypted config at, we're going to use the decoded key name as our key here. We're going to set that to self.decodeBytes value at first, because if this value is not base64 encoded, we're basically just going to leave it as is. So we initially set it to just the raw value of whatever is in our translated config there. So now that that's done with, if length of the value is 0, meaning that we have an empty value, we're just going to continue and iterate through the next part. Otherwise, we're going to try to decode with the base64 decode our value. And if there's an exception here, we're going to set that flag to true. Base64 exception equals true. That tells us that, hey, maybe this thing is not meant to be decoded. Maybe it's not a decrypted or an encrypted string. So if there was that, if that flag is present, or if the length of the decoded value is less than 48, which is the minimum we need for our ciphertext, that means that we might be looking at something that is a base64 encoded string, but maybe not encrypted. Then we're just going to leave that as is and continue on. Otherwise, we know that we have a good chance of looking at a piece of ciphertext. So we're going to extract the IV and ciphertext from that value using, just like we did in CyberChef. If you remember, the first 32 bytes are going to be the HMAC hash, so we can skip over those. And then the next 16 bytes are going to be our IV. And then everything after that 48th byte will be our ciphertext. So that's how we would drive those. We actually don't even need parentheses there, really. We can just do something like this, I think. Yeah, we don't even need those parentheses there. And then we'll say decrypted config decoded k equals self.decodeBytes self.AES Decryptor.decrypt and pass in our IV and ciphertext. So to break this down, you're using our AES Decryptor, the decrypt function we just wrote up there. We're passing in our IV and ciphertext, and then we're decoding that back into a readable string and storing that in our decrypted config right there. As long as the decryption is working, we're going to go ahead and log a message that says key decoded k and value decrypted config decoded k. There we go, right there. And actually, I just realized I do need to include this also. Sorry, I just cut away there because I realized I actually need to add a debugger message here and here as well, because if we continue, we'll actually skip over that logger message there. So let's make sure those are in place. And if everything goes right here, then we can just return our decrypted config. Decrypted config. So before we test, let's go ahead and write our report function. I think we still have a skeleton here somewhere that I just have, and it just returns the word report. Let's go ahead and actually make this a real reporting function, and then we will be all done for this one, guys. So report is going to return a JSON dictionary, actually. So I'm going to go up here and import from the JSON module, from JSON import dumps. This is going to dump a Python dictionary into a JSON object. So it's easy to parse for, I'll say a lot of malware analysis tools use JSON. So it just makes sense to put this dictionary in JSON format. And even if they don't use JSON, it's just a nice format to use. It's used quite frequently and widespread, and it's easy to manipulate. So I'm going to put this in a dictionary at first, but then we're going to dump our dictionary to JSON. And this result dict is going to have a few different keys. We'll use file path. We'll set that to self.filepath. We'll set AES key to self.aesdecryptor.key.hex. We'll set AES salt to self.aesdecryptor.salt, AES salt, that's salt.hex. And we'll lastly do our decrypted config, which is going to be stored in self.config. Whoops. I'm so excited, but so tired at the same time. It's such a weird jitter I have right now. So we're going to return dumps result dict, which is going to dump it to JSON. And that is what ultimately is going to be reported back here in our main runner program. I don't know about you, but there's electricity in the air here. After having worked so hard on this, we're finally going to be able to see the fruits of our labor. Hopefully no error messages. We'll see. Let's run this on our test sample first. Okay, there is an error. Don't panic. It just might be that our debug message has an error here. So self key, yeah, it's because I missed AES key again. 1 second. Anywhere else. That's what I get for trying to copy and paste or try to retype things. Try again. See if there's any other errors. Did I miss? Oh, I did AESdecryptor.key. Ugh, it's the same thing in just a different form. You're ruining the suspense. Okay, right here in our report here. It's called AES key. Get it together, Jeff. All right. Oh my gosh. Look at that, guys. So let's turn off. So first of all, we can see our debugging is working. So we can actually turn off that debug flag now. And let's just take a look at the output without all that debug messaging there. And oh, something has gone horribly wrong because we're only seeing the ports key here. So something's going wrong where our translated config maybe our decryption method is messing up because it's only catching the first one and then it's continuing. So let's check out our code and see if we can troubleshoot this. What did I mess up now? As I was scrolling up, I realized exactly what I did before I even got here, and you all probably saw it too. We are in a for loop here, and I put the return statement in the for loop. I need to put that outside of the for loop, or it's just going to return after that first iteration. That's why that's happening. So I didn't mean to create this much suspense, but here you go. So now what's wrong? I put a period where there should have been an underscore. More suspense, guys. Let's try to fix this. Hopefully, final issue, please. Is there anywhere else that okay, that doesn't show up anywhere else. We're so close. Error decrypting such and such and IV such and such. So this is interesting because this is actually a error in our decryption function instead of something else. So we might actually need to take some time to figure out and troubleshoot this one real quick. Oh, hi everyone. This took me forever to diagnose here. It's because the block size we pass in to our PKCS7 object is actually in bits, not bytes. So we do not need to do the division on the block size down here when we did the double slash. That is only on the key size. We do not need to do that for the block size. Holy cow, that took a long time to diagnose, but let's go ahead and make sure that that is the only problem that we have here. I'll pull over my screen here so you can see. And it looks like, let me rerun it just to be sure, and we'll turn on debugging. That was indeed the issue, because now we have a wonderful JSON decrypted config output. Let's take a look. Let's run this through using Python tech m json.tool. Run that through the JSON tool, and we get a little nicer, clear output here. Look at this. We've got our successfully extracted AES key, successfully extracted AES salt, all of the decrypted contents, the C2 server, the ports, the mutex, everything. So if we want to really be thorough with this, I have a collection of samples, ASyncRAT samples. And by the way, in the GitHub repo for this project, which do I even have that open here somewhere? If not, I'll just open it in a tab here. I do have a YARA rule linked that if you have access to some malware repositories, you can use this YARA rule to find ASyncRAT payloads. So please do check that out if you need some samples in the wild. I pulled these from VirusTotal because I have an account. And let's just direct the output to a text file because it's going to take a while. But there's let's see. I think there's something like 500 samples in here. Or just 50. I thought there were more for some reason. I've tried this on many samples though. I think I just chose a cross section of 50 here. Let's run it across those 50. And I'm going to redirect the output to a text file. Now, I will tell you that you'll see a few exceptions come up here in the errors because some of these payloads that I pulled are corrupted or they are like from memory dumps or something. But for all of the valid samples that were in that set of 50 samples, you can see our parser is parsing through all of them. And you'll notice like that first one, even when the keys are not the same as what we would expect, like they have the underscore or whatever in them, it's working that way as well. So if we do that, we can see all the way down through here, just so many awesome results from our parser. So we just scanned through 50 samples in what, a couple seconds maybe. So it was a ton of work to get here. But that is the fruit of our labor, is we now have a fully automated, pure Python parser. We didn't use any external libraries besides the ones that are just built into Python. We logged everything so we could test it along the way. We went through a ton of roadblocks just to make this resilient against the actor changing up stuff in the payload. And I really hope that if you made it this far in the video, if you're like me, if you're just exhausted, whether you're watching this like me at 3 in the morning or hopefully for you during better hours of the day, whether you actually coded along or not, or whether this is even your first time making a malware parser or not, I don't care. You should be extremely proud of making it this far. And if you did play along and build this out, I hope you feel that sense of accomplishment. And regardless of if you played along or just came through here and watched this, this whole, hours of content just to learn a little bit, I hope you really got your return on your investment. I did promise you that if you stuck around, we would make it through this and you would see the value in creating this thing. And I hope that I've accomplished that. So thank you for joining me. I'm going to go get some much needed sleep. Before we wrap up, I just wanted to reiterate that the YARA rules and the code and everything is available in the GitHub repo that I put in the description here. You can see the full code with, not here, but back here. You can see the full code for the config parser. It may look a little different. I'm going to make a couple of edits actually. One thing I noticed is that if you run this in Python 3 and some different versions, let me see, not this one, but let me open up the one that's currently in GitHub. If you do not include this default backend argument in the cipher and the pbkdf2 function, that sometimes throws some errors in earlier versions of Python 3, so I kept that in there for compatibility, but it is optional in later versions of the cryptography library. Other than that, the only difference between what we just made together and what is in the GitHub repo is just additional comments to remind you of what's going on, some references, and a lot cleaner code than what I just kind of threw together in there. So go ahead enjoy the fruits of your labor, use this config parser, make it better. Please leave comments and let me know if you found something that makes this more efficient, or if you found a really cool addition to this. Let me know what you thought of the video. I know it was a long one. Let me know if you like this kind of content, or if you would rather see other stuff in the future, or maybe smaller spliced up videos. And please leave me any feedback you have, constructive, negative, positive, whatever you've got. All I can say at this point is thank you for joining me. I hope you learned something, and I can't wait to see you in the next one. I hope it's not a year from now. I'm going to go kiss my kids goodnight and go to bed.